everything. Those you perverts. Colonel Muriel Clean here, and that's just a sort of grubby, nasty lavatory innuendo that's scraping the bottom. Shut up! There now follows half an hour of hideous, wacky smuttery and naughty, wobbling things of all denominations. So do what I do if you don't want it rammed down your throat. Turn over to the other side. Quick.
You know why we're here today?
Yeah.
Well, we're here to talk about Santa Claus. Well, Mama and I got something we need to tell you.
Santa isn't real.
Wrong. Santa Claus is real.
Have you ever wondered how Santa can be at every mall and all these different places at one time?
The more people that believe in Santa Claus, the more power he has to fly.
Oh. But do you remember one time you asked me, you say, why is Santa Claus come down from chimney, but he did not get a burn?
Every single person that celebrates Christmas does not like put their chimney on fire.
Okay.
Nobody wants to kill Santa Claus. Nobody does.
Well, Mommy really feel like we are a terrible person now because we are telling the truth. Santa Claus is not real.
You are not telling the truth.
What happens to little boys and girls that don't believe in Santa?
Well, they do Kwanzaa or Hanukkah.
Okay. Well, besides that...
Then what's your idea, though?
My idea is that that's a big fake, and no, Santa is real.
Well, I think we all have
Case
a little...
closed.
The Michael Jackson song we listen to all the time. I saw Mommy kissing Santa Claus. You want to know why Mommy was kissing Santa Claus?
And Daddy wasn't there. Daddy did not hear it. Daddy did not see it. What is
because
going on?
Daddy is Santa Claus, and that's the reason Mommy kissed Santa.
Okay, look. I could prove that you two, you're not Santa and you're not Miss Claus.
Okay, you prove it.
Prove it. Ask me a question that only Santa would know the answer to.
Tell me all the reindeer names.
Well, there's Dancer and Prancer and Cubert.
Okay, you're not Santa.
How many did I say? I think if Santa's real in your heart, then he should be real. And you should look forward to him on Christmas Day. While we're here being truthful, do you know who the Tooth Fairy is?
Oh, yay.
It's your mother.
Nope.
So you met Santa Claus at your school the other day at the pancake breakfast at your school. What did you
Yeah, but that's the fake Santa Claus. That's Santa Claus's helper, though.
How'd you know it was a fake Santa?
Oh, snap. That's a good question.
I'm going to hang up this phone, and then I'm going to show these people what you don't want them to see.
What's going on, everyone? It's Jeran from Jeranism back with another live video for you. Tonight's going to be a good one. It is live. I saw some people think that it's recorded. It's live. This is live. It is the 15th of September. It is 6:05 p.m. And it's time for Jeran and Dave and Sean and Austin to get schooled about living on the globe by Professor Bryant Meyers, BS MA Physics. I don't think the BS stands for what I think it does, but maybe it does. We'll bring everybody on. Let's say hello to everybody. First, we've got... Oh, we got to get rid of that real quick. Hold on. We got a bar in the way. There we go. We've got Whitsitt down in the corner. Austin Whitsitt, how are you, my friend?
Good. How's it going, man? Looking forward to it. Should be good convo.
Should be fun. And we've got to his right, your left, Sean Hibbler from Hibbler Productions. Sean, what's up?
What's up, everybody? Thanks for having me on. Enjoy the show.
Should be fun. And we've got, of course, Dave Weiss in the house, the man, the myth, the legend, the Jew. Dave, welcome to the show.
Thanks so much. That's all. How's it going? Welcome. I'm looking forward to this. Brian, let me introduce Brian. He reached out to me a while ago, and he came across like really nice, and he's like, I believe this and that, and he wanted to have this debate. And I said, rather than have a debate, let's have a discussion. And he agreed to come on with all of us. So it's not 4 against 1. It's 5 guys having a conversation about what they truly believe. Brian is not a troll. He is not a scammer of any way. He 100% believes what he believes, and he's going to try to school us. And, we're going to try to school him, and maybe somebody will change their mind at the end of the day. Now, we all know that we have all shown that we are able to change our minds because we were all Globers at one point. So we'll see what happens. And we're probably going to agree to disagree on many things. And we're going to let Bryant do as much talking as he can. We might get a little heated, but we're not going to call each other names because we're not little fairy boys. All right. And Bryant, what did I miss? What did I leave out? Say hello.
I'm glad to be here. Thanks for having me on. I look forward to just kind of going through. I got the full spectrum of topics on globe versus flat Earth, so I think we'll be able to cover a lot of ground. And I've spent a lot of time preparing this, so it's very efficient. And and I hope, at the very least, even if no one changes their mind, I think there's a lot of science that maybe could be like sharpened on the flat Earth side, because I've just heard so much that's so easy to, basic physics stuff that's easy to debunk. And then, we'll get into it.
One other thing which I wanted to say, which Bryant is on the same side of the fence as everybody else here on things that we shall not mention on YouTube. Okay, he is on the same side of the fence on everything. I said in a couple of emails to him, you're really pissing me off because I'm starting to like you. Right, yeah. And we differ on two things: flat Earth and the moon landings.
You guys don't think birds are robots, do you? Though.
No, we don't.
Okay. So yeah, it's probably just those two things. And yeah, okay, good. But there's a couple of really weird out there ones that I'm not into. But I've heard enough of your stuff to know that we pretty much agree on everything except the two little things. If we can, I would rather not get into the moon landing tonight, because that's just not an area I've spent time researching enough. So I want to focus more on just the science, more on.
Well,
we can talk about the moon. I want to talk about the moon, but
not the landing there.
Not the lunar module.
Can we not talk about the LEM?
Show. If you give me some time to do my own research, really be more thorough on that, I'm happy to do that.
It won't be a fun show because we'll all be moon landing deniers, and we'll be like, "Why are we here? Why are we here? What are we talking
chamber.
about?"
I've got a couple of doozies for that, but maybe we'll bring that up with the moon. I just want to bring up a couple things that I think are pretty solid proofs that we did land on the moon. But let's start, if you don't mind. Can we just start with the whole Earth? Because I hear flat earthers always, or people that believe in flat Earth. How do you like to be addressed? I want to be like,
we like to be called flurfs.
We 100% deny a globe heliocentric beehive model. 100% doesn't exist.
Well, people that believe in flat Earth. I it's easier to say flat earthers, but I know that's better.
What's a level and stationary plane?
Yeah. Okay.
Yeah. We're globe deniers is the most
open-minded.
If I do say this flat earthers, I'm not saying that in a derogatory way.
Okay.
It just kind of comes out quickly and efficiently.
You're good.
So that's one of the things that can I share my screen here now, or
you can? We're ready to go. Yeah. Whenever you want to do.
Go ahead. Fire in the hole.
Okay. All right. So let me make sure I'm. Okay. Am I shared right now, or I don't see it?
You are good. Go ahead.
Okay, I'm just not seeing it on the side. Oh, there it is. Okay. So, of course, a question that comes up a lot of, flat Earth believers that I've talked to, it's like, well, show me a picture of the globe. It's like, and then of course you get into what I feel are actual pictures. And before you get into the photoforensic speech, I actually spent a whole day going through photoforensics.com and Forensically, which are two online photoforensics tools. And I actually went and found the highest resolution images of blue marble and Earth rising and a couple others, and I also uploaded some digital pictures of myself. So just my own, which I know is true, right? So in these forensic tools, I was seeing some aberrations even in my own pictures, because digital pictures are always going to have some distortions. But I couldn't, and I'm not a photoforensics expert, but following very careful tutorials that are online, I was not able to detect any obvious, error analysis. There was just nothing obvious when you made the block size large enough that if it was a fake photo, there would be much, much more type of obvious things.
There's ways to cheat that though, right, Brian? Like for instance, if I take a photograph of a photograph, it will always be perfect on air level analysis, because there is no differential there. It's going to look like a perfect picture, even though I took a picture of a fake photograph. Right.
Well, but the point is I'm not claiming that these are proof of anything, but when you say they're not proof, it's the same for you guys. So your photo forensics analysis is just as unscientific as someone trying to prove that they're real, because digital photos, unless you get the actual original photo and you actually get a photo forensics expert, and you can see, let me just.
And it would be true that the only pictures of Earth that even science would claim to be true would be the ones from the moon landing. Right. Everything else cannot be a photograph because it would be a digital representation sent as data.
Okay, right, a digital, but again, we live in a digital age, so I want to get to some of the more current, and I don't want to focus so much on the moon landing photos, but just so you know, I mean, there is a lot to photo forensics. So when you just go out there and say that these are all, well, I've used photo forensics and I've shown that it's not true, or that it's whatever, I've heard you guys say stuff like that, you know, in a court of law, you actually have to hire. And I looked into hiring a photo forensics expert just to prove my point. They were too expensive, so I didn't. But they're expensive, first of all, that holds up in a court of law. And he told me that digital photos, there's really no way you can really prove it, but you do things like this. You got to go through many different sort of, there's like many steps. You know, you can look at the photo forensics, but then you got to like, okay, look at the metadata, look at, you know, there's like a lot that goes into photo forensics. So the only way that I would believe, or I think we all should be critical here, that what you're saying, that you've done photo forensics and you've shown the moon landing photos to be false, is that you have to hire a professional photo forensics expert. And I want to see those documents. I want to know who it is, and I want to see what their analysis is. Just for one of you guys to say it is not convincing.
Bryant, like that picture you're showing us, they NASA has a 24-hour stop motion, just a whole bunch of pictures where it's spinning.
Oh yeah, yeah.
How come they never show the moon in that? You know, the moon should come around, and you can't say it's out of line because it's a full Earth. The sun is behind the camera.
I mean, the Discovery has shown the whole moon. I mean, they had the image of the moon going right past.
Yeah, one time. Mm-hmm.
Well, still, I mean, you say that they
can
have.
Can we pull that up? Can someone?
Yeah. Do you think that one looks legit, Brian?
Right.
I've done analysis.
This one.
Yeah.
Right.
Well, listen, I can tell you something about that. The reason you see the red, the green, when you look at doing air analysis,
yes, the three colors,
because they had to take separate images because it's moving so fast and combine it into one. So again, you got to realize the moon is going really fast across the Earth. So what they did is they took 3 snapshots in 3 different colors and they combined it into one image. Okay. So that's why if you do an air analysis,
what do you mean really? Why would it be really fast though?
Right.
The moon is going pretty darn fast.
2,000 miles per hour relative to the size of the Earth isn't fast if you're that far out.
And also, why isn't the moon lit? Why isn't the moon lit? It should be a full moon.
There's the money shot.
Well, I've seen some of those things. I off the top of my head, I can't remember, but there's different. You know, the cameras that are taking the images, if you open the exposure too much, then you end up getting overexposed on the Earth. If you do it too little, then the moon gets. You got to find a compromise.
So, but look, we have a full Earth, and the Earth is lit up. The moon is closer to the camera, only a quarter of a million miles closer.
I'm not a photographer, Dave, so
right.
I do know enough that when you guys say, "Oh, no stars on the moon," I mean, you guys know. Come on, you guys know that that's overexposure, right? The reason that you don't see stars when the moon landing photos is because if you open up the exposure, you're going to end up with it's going to be too bright. I mean,
I hear what you're saying there. I just throw in my 2 cents. One of our guys in Thailand, Phuket Word, he went out with his iPhone 4, an old iPhone, and he stood underneath a street light and he aimed the camera at the street light, so it was blinding the camera, and he could see stars behind the street light. Well, how come when they're on the moon facing away from the sun into the dark sky, they couldn't see a single star?
There are, again, you can do similar experiments and show different results too. So I'm not going to take just one n equals 1 experiment. See, I don't like these as a scientist. N equals 1 means I got a scientific study, then it's just one person in the statistical. You're basically doing statistics on one person.
But pretty much anybody,
like you said, it's not proof.
15. You need at least 15 for a good statistical study. I used to teach statistics, so I know that.
I'm pretty sure anybody could go on their street with street lights, point their iPhone camera at the sky, and pick up the stars. I don't think. Well,
again, you can do that, but you can also, if you're trying to. But street lights are not. It's not. You can't say that that's the same thing as being on the moon.
Yeah, fair enough. I agree with you.
Okay.
I actually agree with you. So like you said, it's not proof of anything. To me, that's one of the fakest looking things I've ever seen in my life. So it doesn't cut it for me.
That's fine. That's fine. I mean, you can. And again, I'm not a photo forensics expert, but I did spend a fair amount of time going through as much as I could. It's like, okay, there's not convincing evidence that it's not real. Can I prove it's real? No, I'm not a photo forensics expert, but I'm not convinced that they're unreal. Is what I'm getting at. And
there are many experts that said that the pictures from the moon landings weren't real, and they went in depth and did.
Show me the experts. I want a list of those names.
You can go to allus.com. They're all PhDs. AUL.
Okay, well, send me the link because there's plenty of people on the other side that.
Yeah, sure. Of course. But you asked for people on this side.
Okay, so again, this is the whole picture thing. But what I want to get into now is something called, with the new satellites that we have now around the world that are able to take whole disk images. Again, we say disk because you can't get a 360-degree image of the Earth, but they're taking these now every 10 to 15 minutes. Okay. And they're getting what's called truth observations, guys. So you can actually, like the Himawari 8 has been able to detect fires from space and to help with sort of the direction of the fires going. So we're getting now live images from these satellites.
Hold on, they're not live though. They're not live.
Oh, no, they're not live, but they're taking every 15 minutes. Yeah, you got to wait. There's a delay, right?
So can I interject here for?
But you're telling me that hundreds of pictures every day are faked?
But why are they taking? Why would it take any amount of time?
What's the point? I mean,
but what's the point of taking 15 minutes to get us an image?
But you can.
But no, hold on. Answer me that first, though. Why would you ever accept 15 minutes late for an image of the Earth? How long would it take?
It's got to take. But listen, you can take a picture with your clock at a certain, a really unique cloud formation. You can go on Himawari 8 or Go 16, and you can see that same cloud formation.
Agreed. Yeah. So
you can get truth confirmations like this from space.
All right. Yeah. So I'm gonna break your paradigm on this. You have to let me talk on this one. Okay. So we're gonna show you some research that we did on the Himawari 8. How come that's hiding there? Hold on. Transition. Here we go. So we found a server. Jeran, jump in at any time.
Yeah.
Either whistleblower or somebody found us an FTP server with tens of thousands of folders on it with images from the Himawari 8, and they had a blue marble, a regular blue marble model, and then it had flat images of world radar. And it was showing how they wrap it around a sphere. This is a NASA FTP server. I'm just going to jump forward a little bit here. And so here's one of the maps they use with the weather on it. These are images that were on these servers. And then, so check this out. This one is, they got the blue marble. They wrap the weather data around it. Okay. And we take it a little farther. This is the folders that we got it out of off of their FTP server. And then they added a terminator line, right? They added a terminator line. So here's the question for you. If this is a real image from the Himawari 8, how did we see the clouds over here? When we go back here, there are the clouds.
Yeah, I know you do a lot of this kind of stuff, Dave. I would have to see the files and everything before I can comment on that because I'm not
understood. But let me ask you a question. Let me ask you a question.
Yeah.
If we showed you the server, the NASA file server, where they're loading these pictures every 10 or 15 minutes, would you be willing to concede that yes, it could be faked? It
could be composite. Composite.
So hang on.
Composite,
here's my question.
Sure.
You agree that there's radar stations all over the world that could map out on a flat map all of the weather patterns in real time. So they can take that data, and no human has to be involved with this, wrap it around a globe, put a terminator line on it, and send it over to NASA every 10 or 15 minutes.
I don't know, Dave. That would take 10 or 15 minutes to do that.
No, it wouldn't. It would take 1 second to do because AI now can draw a picture from a description that you make and make it look photorealistic.
Yeah.
So this is nothing.
But they're coming from the wrong direction. This is looking straight down on the Earth. I mean, I don't buy that.
Brian, can I ask you a question? Genuinely curious. So, like, because everyone says it's live and it's not, right?
We just discussed live. It's every.
But wait, Mike, I just got a question for you. So, if it's say every 10 minutes, right? Say it takes that long to send it and receive it. How come sometimes when we go check it, it's like 25 minutes late?
Yeah.
I don't know this. I've checked that too. I don't know the servers, but I mean, you can do truth observations. I don't buy that the radar on the ground can take these 11K quality photos. I'm sorry, guys. I mean, these are 11,000 by 11,000 pixel photos.
Hold on. There's stitch lines. You can see the stitch lines inside the Himawari 8. So they're not.
You zoom in, you see where it's stitched together.
They're purple stitch. I can show you if you want.
Yeah, zoom in. Someone zoom in on it.
I'm going to show you.
Jeran,
can you see this?
Let Jeran bring it up.
Can you see my screen now?
Yeah. That's your screen.
So this is Himawari. It's live. I'm just going to find a full picture of the side. Okay, right there is pretty good. So now if we zoom in here, we're going to see that as you get really close, come on.
Okay, so I can see that on any Himawari image you're telling me, or is it just this one?
No, everyone.
Yes.
Everyone.
Every single one.
This is
every
right now.
single one.
This is the live. So if you go in here, you have to get real close, and I'll show you where.
I'll look at it. I'll take a look at that myself. But I'm
Yeah,
See
well,
right
let's
here?
take a look now.
See right here,
And
this
see
right
what
here.
we
I
see.
can't really see.
Well,
Oh,
you
you
can.
can't see that
Because
I'm
it's
sharing
real
my
small
screen.
for him. Yeah. Do you? Yeah.
Oh, I can. Yeah, see right here. Oh, wait, am I not sharing on the share screen? Oh yeah, no.
But
No.
You can
but
see that
guys
line.
do know that even I mean,
You can see this line though. Yes, there's a purple line. Right here.
I can't see it. I mean,
It's
that's
really
the problem.
small for him.
That's the problem.
Yeah, but it's small for me. I can see. All right. Well,
Okay,
you
well,
can see
well,
right here,
I-
and look at right here and here. So there's just go along the edge, and you'll see there's another one there.
Okay, well, just leave that as an open.
The other
top.
thing, just one other thing about Himawari that I find extremely questionable is if you find on any count, whatever the full moon is,
Yeah.
you should see the full moon come around the back of the Earth, and you never see it. And you never see it. Of course, you're not going to see it cross in front, but behind.
There's probably again. I'll look at. There's probably a good reason for that. But
Well, I mean, we could always say that about anything, but there's not.
just move.
What could possibly be
No,
a good
of course.
reason why they wouldn't show you the moon going behind the Earth?
Well, the big question that I always bring up with people is like, we have these high resolution images that are hundreds and hundreds are coming in every day, and the flat Earth, there is no full flat Earth disk from space photo. So
Of course
if
not.
you guys place these standards on. Hold on. I mean, those high elevation. I want to go through the high elevation.
We don't think Earth's a disc in space.
Brian,
man. That's wild.
Brian, do you think that we think we're a disc in space, floating in space?
I'm just saying, even getting to a high enough elevation to where you can see the wall. But let's get into that later.
We don't think we can get up high enough to even get a couple states in frame.
And we don't think there's a wall at the end of the Earth. We don't think there's a wall at the end of the Earth.
The Kobayashi map is real, which is actually from probably a fictional.
I'm not saying the Kobayashi map is real. What I'm saying is we live on a plane. Antarctica, as far as they let us go, we don't know what's beyond Antarctica.
We'll get to Antarctica. Can we just move on? Because I mean,
Yeah, these are
just
showing
showing-
pictures, so we can move on.
Just
It's
real
like
quick.
showing me.
I looked up. This is September 10th. There's no moon.
Sometimes Dave does the witch ball thing, and I think Dave, that you can get a camera and different angles of fields of view. You can get different the side. I took this myself, so I've seen this in my own eyes with my own camera. So I'm not lifting this image from anybody. This is with my own little globe. And just by using a 15 millimeter and a 45, I was easily able to show that depending on, Discover's 980,000 miles away, some of like the Apollo shots are maybe 28,000 miles or whatever it was miles away. You're going to get different, the continents are going to look different sizes. You guys get that, right?
I totally get that, but not to the extent that they show us. For example, right here, Jeran, if you can make me big so he can see.
Yeah, I'm just doing this fast.
This is the United States right here. And so this circle represents about this much land. And you're saying just because we don't don't see the whole side, all of this other land is on the other side. Okay. Now we could argue, oh, that's what you do think it. But then we see stuff like this from NASA. Right. And people are like, well, that's the globe. Well, that's not the globe. This is clearly a fisheye lens. We're not going to disagree on that. You got that. But this is the one that gets me right here. Where let me just pull it up. Hold on. Give me a second. It's got to resize this real quick. So whether we're seeing the full edge or not, because we're close, it's looking big. So maybe we're looking at that close one that you have. We can measure this because we can drive across Mexico and go across here and measure this. And it's 934 miles. Well, the diameter of the Earth, right? The diameter of the Earth is 7,917 miles. This little red line here, I should be able to fit 8.5 times in between these two lines. You can't claim that is because we're closer or farther from the Earth.
Look at Africa right here. I mean, this is obviously, we know the diameter of the Earth and the radius, and obviously Africa looks like it's taking up the whole side of the hemisphere.
Yeah.
Because of the field of view. Walter Bislin has some very careful tools that you can use to get views of the Earth from different fields of view, from different distances. And you see, when you use this tool, it's very mathematical, you get all these differing sizes and proportions.
I agree. He's right. Flat earthers are wrong whenever they say that that some of the pictures look like they're different size continents, that it proves they're all fake because you can't get the same effect on a sphere. You're correct.
Yeah, correct. The same thing with the color, Jabe. I mean, that different cameras can take different perspectives. So just because one looks one color,
I never claim the color. I just say they all look horrible. But
talk about different colors.
I never claim that. I say they're all different. Which one do you like?
Which one's real? Like it's just a joke
yeah.
because they're all fake.
I mean, which one do you like? It's because they're different perspectives, different cameras. I mean, they just
different cartoons.
Well, so okay, let's just move on. So I don't think we're going to get much further than that on this point. So
we agree it's just not proof either way, right? We gotta.
Okay, now listen. I do know your model. I didn't mean to say you going beyond the dome and taking a picture of the whole disk. What I meant was if the sun, and again, I don't know. I hear different things. Robotham and Eric Dubay say 3,000 miles is the sun above. I've heard Dave say that the sun is somewhere else and it's a projection. So I get nobody seems to know.
We don't know.
We don't know.
Yeah,
and again, imagine if
I know, but if the sun is 3,000 miles up, why not just send something up there to take a look at it? I mean,
because nobody's ever been 3,000 miles
up. You can't even get the jet fuel to go 60 miles up. The government has to approve you to even shoot a rocket 30 miles up. You can't just go 3,000 miles up. I don't even
go I've studied rocket propulsion at Georgia Tech. You can go 3,000 miles up.
It's illegal.
I'm saying it privately, maybe, but I'm just saying there's probably ways to if this was really
maybe the government will let us.
Yeah.
But you should be able to get high enough. So anyway, so is this kind of I mean. Now I know you guys think there's maybe other lands outside of the wall, but just can I agree? Can you agree with me? This is kind of the map that you guys use.
Sort of. I wouldn't base the continent sizes. I wouldn't say they're correct.
Like you guys can't seem to agree on like which map you want to use. I mean,
so when you say that though, hold on a second. Do you realize that when you guys discovered the globe or whatever, that every single mission, every single map that was drawn was government funded, completely and totally. There's no private research going out there and figuring out what the shape of the continents were. It's all government funded. So to come at us and say, well, you don't have everything mapped is ridiculous. And yeah, we don't have any government assistance. So
I know, but we've mapped the world. I'm not trying to be
you think you've mapped the world.
When you say we, who is we? You said we mapped the world. Who is we?
To just disregard like everything that history has told us. I mean, I agree that maybe
not
there's
everything.
Some distortions in history. But I mean, science and I'm not a cartographer. I'm not a map expert. I just want to know like what map you guys use.
Well, here we don't have an exact map. For me, I'm a fan of the Gleason's map. This is a representation of the Gleason's map on my clock app. And what's that? Here, the one thing I want to say is, whatever time of day it is, if you look at where the sun is, so when the sun's over here, I can call my friend PK up and say, hey, what time is it? Where's the sun? He'd be like, oh, it's noon and the sun's right above me. And then 6 hours later, I call somebody over here in Africa and they'll be like, oh, the sun's right above me, right? So there's something truthful about this because the sun goes around and this shows you where the sun is at noon for each location.
Right.
But the thing is, that's not accurate because you can point like Wolfie 6020 did a video where he shows your app.
No, he's wrong because Wolfie doesn't understand how east and west work on the globe. So.
Well, I mean,
I can show you.
I think anybody can find a way to go outside and point and see that the sun is not exactly.
Let me ask you a question.
Yeah, but you might think that.
Can you point west right now?
Well, if I had we can get a compass and do a test.
You can't point west. West is right where you are. Anything past that is south.
Okay. Well, I don't know.
Do you want me to show you? Do you want me to show you? Because I know you want.
Let Jeran show you a quick demonstration, and then we'll go right back. Is that okay? Or you want to press on?
I just want to show you why.
I don't want to press on. I don't.
Let him press on.
Right.
Okay. Yeah, let's let him get a little bit more.
So we can just go. So I mean, the Gleason map, and I know you guys. I mean, the point that I have is this is an azimuthal projection of a sphere, and I've heard Dave say that no, the sphere is a you can't. It doesn't go that way. Projections from higher dimensions to lower dimensions, you lose information when you have 2D. So you can't just say, oh, we took the 2D. And
wait, so you're saying if let's say we discovered a flat Earth and we all got together and said, hey, let's make this so it's a sphere. You're saying it's impossible for us to put that on a sphere?
This is a perfect azimuthal project.
Well, of course. Wouldn't it be though? Hold on, you're not listening to what I said. If we showed up, saw flat land, decided to put it on a sphere, then if people later in life took the sphere and laid it out as a flat map, that's all possible.
Okay, but you guys do know that there's been globes around. I mean, I've heard you say that
the oldest globe is 1492.
Okay,
oldest
fine,
globe.
but I'm just saying that I've heard you guys say. I mean, I've studied a lot of flat Earth history, so I do know the fact that.
But Aristophanes and those guys, they knew that the Earth was a sphere, and they just nobody ever decided to make one.
I know, but the geocentric model and the Ptolemaic model was even in the darkest of the dark ages, the educated world embraced the globe, even though they thought it was the center of the universe. And this is a very well documented historical fact. And I disagree when you guys say, "Oh yeah, it was taught in schools."
So why were we taught about Columbus sailing the ocean blue and discovering the Earth was round?
Well, listen, that's actually based on what's the author's name that wrote the book? That's actually a fictional account. He actually fictionalized Columbus's. There's this really good.
So why one guy wrote a book? One guy wrote a book, and then it showed up in schools and it showed up in textbooks.
No, I know that is an unfortunate thing that happened, but he never sailed across to discover the world was flat. I mean, they knew the world was a globe. In fact, what they thought, though, because this is before Newton, they thought that they had to go over the hump, and they actually underestimated the size of the globe.
But so Aristophanes knew it.
They did believe it was a globe. Well, I know, but maybe they didn't have
1,700 years later, they didn't.
Well, no, they had the idea of the globe, but they thought that they were going to have to go over the hump, to get to the. So they had this idea of the antipodes, which they didn't understand the South Pole. But then, of course, when Newton came along, that we understood it was gravity. So, but I mean, but there's pretty good historical evidence that the educated world since Eratosthenes.
So educated that they thought they were going over a hump. That's pretty educated.
All the proof they needed back then.
No.
That was the only proof.
Now wait a minute.
Going down.
They didn't have Newton's equations. You got to realize that they didn't have the science to understand this yet. And yes, we can look back and say, well, why did they believe in antipodes? It's because they didn't know gravity at this point wasn't known. Okay.
Yeah, it was a religion. It was that the perfect shape was a sphere. So the Greeks proposed it philosophically. It was an ontological premise that the perfect shape was.
There hasn't been a time where we've embraced the flat Earth since. You got to go back.
Brian, hold on a second. We don't know anything past the early 1900s, right? There's no one left to tell us. You've seen my interview with Ruth, and there's people that say they were taught flat Earth and globe Earth in American public schools in the 1950s. Right? So this is not what we hold on a second. We didn't have instant communication. We had barely, back then you could barely make a phone call across the state. Easily. So when they were switching over, what people believed, like if they did it here in Connecticut, some people in California, they wouldn't know what's going on. It could be a decade before they found out.
Oh, what's the name of that town? There was one town in the 1800s that did embrace what's it?
Zion.
Zion, yeah. That historically was the only town I could find that was well documented to have embraced the flat Earth in their education. I don't think that the educational system, I just don't buy it. We have been teaching the globe Earth for quite some time, and it didn't start in the 1900s.
All right, well, that doesn't mean anything.
I saw the interview with that lady, but she was 102 years old, Dave, and I mean, it wasn't very convincing.
This doesn't mean anything. If they were teaching the globe for 7,000 years, that doesn't mean it is a globe. So it doesn't mean.
Okay, I agree, but you guys that say that it's they've been teaching flat Earth up until the 1900s, that's just patently false.
Yeah, I don't say that.
Okay, well, yeah, they were a minority whenever Aristophanes supposedly existed. There's no primary documentation for that, so we were just going to move on to.
Okay, we can move on. You already agreed that this is not like a real map.
We did.
So I just want to talk about. We want to talk about that.
I don't know. I didn't know we agreed this.
The Kobayashi. Well, you bring up Kobayashi in the documentary Next Level, so that's the only reason why I put it there.
So it's been proven that it's a fake.
Well, you got to take in the context of the art. This is the article in the Hawaiian Gazette. Is that this was kind of the lost world sort of? It's kind of the time of that era where the lost world was a big thing to talk about, and everybody was fascinated by it. So you had some of these fantastical accounts that sounded real that were published in newspapers, but yet were still based on a fictional thing. So
maybe it was real. Sometimes ancestry passes down real stories.
This was the brother of the Kobayashi that drew this, and he did it just by hand. I mean, so it's when you really look at the evidence, it's just not very convincing that it's really based on anything real.
But Aristophanes with no primary documentation is convincing.
Actually, the Eratosthenes, we can get to the sticks and shadows experiment, which I know you guys like to make fun of, but it's actually pretty darn convincing. But
it's not that we're making fun of it. It's that you're bringing up to our attention that this article in this newspaper, which, by the way, is hidden from the masses. Let's not act like everyone knows about this, okay? So this is hidden from the masses for a reason. But you're going to sit here and say, oh, you know what? This isn't real. It's just in some stupid paper. Well, everything you're reciting so far is in a stupid paper written by some stupid guy. So
the Rockefellers.
Okay,
yes.
Right. And again,
real.
You know that we've already established how I feel about the Rockefellers. We don't need to go there.
Okay. Well, you know, the globe idea was disliked. I mean, the teachers were fighting teaching this in school.
Again, I don't believe that history.
So newspapers, okay. So let's throw all newspapers out.
Is if you're going to say something like that, you have to have more evidence interviewing a 102-year-old lady.
No, there are newspaper articles posted at the time that talk about them. So it's all, this is all sort of like not real concrete anything.
I looked, and all I could find was Zion. Was the only place I could find that was teaching flat Earth. There is really no evidence that it was being taught at all. Going back,
who cares? Doesn't prove either way.
Who cares? But you guys do say that, so that's the only reason I brought it up. So,
yes, because that's what my research led me to.
Yeah, there's evidence that that it's not as old as the mainstream portrays, and there's no primary documentation for Aristophanes, etc. But who cares either way?
Actually, Pliny. There is actually historical evidence when you look back. I will.
One guy out of the whole world.
It's still a story that you were told.
So hold on. Let Brian.
All of history is a story.
You get to choose to believe it or not believe it.
When stories don't make sense, like talking about how they got the distance to the sun by just guessing that the Venus was the same size as Earth. That's pretty lucky.
No, the distance to the sun, you can find the elongation from Venus during its orbit. You can actually look for the elongation where it's at its longest point. And then you can take that when we actually have done radar, bounce it.
No. You're missing what I'm saying. I'm talking about when they first got the distance. How did they figure it out? They figured it out by guessing that Venus was the same size as Earth. And they got lucky that it was.
To the casino.
So,
okay, but I'm saying, we've been able to accurately.
Again, this is what we're saying is that their stories are just stories. Like, for instance, the same thing happens with how they got the distance to the moon, or how they tried to get the distance to the moon back in the BC era, where they say, they saw a half moon. They knew that there must be a 90-degree angle to the sun, and then they just estimated what the angle from the Earth to the sun would be. Nobody could do that today.
Right. Well, we've got more accurate ways to measure it now, but
allegedly,
but the story is that they did it back
I don't disagree that there's been a lot of things through history where they didn't understand what was really going on. I mean, this is why we evolve and we learn things, and we.
Not evidence either way.
The thing I really want to bring up now is
Aristophanes, please.
Not the Aristophanes.
Let's talk about things that aren't hidden and buried. Like,
so wait a minute. You wanted to talk about Aristophanes, and then I had something. We have a few things we want to say in that. So do you want to bring that up now, or you want to go somewhere else?
Well, I wanted to talk about Aristophanes a little bit later, but if you really want to talk about it now, we can talk about it now.
No, just go with whatever you want to do. Whatever your order is.
If it's in your order, just go with your order.
The only thing I wanted to say is about Eratosthenes really was that if you have 2 data points, I agree, you can get it to work on a flat Earth. I actually am in agreement.
Okay.
But if you get 3 or more locations, especially like this one study that was done in 37 places around the world, what you end up with, if you map it out mathematically, and this is one of the points I want to get across, is mathematical models can be confirmed. You guys don't
but
have
back then, but Sagan tells the story of Aristophanes proved it. Everybody talks about Aristophanes proved it. This is why the world knew that the Earth was round. But you just said right now, but it also works with 2 data points on a flat Earth. So you can admit that.
I know, but
they didn't do 3 data points. They didn't do 3. They did 2. Right?
So that story's a lie, right?
The story. I mean, Aristophanes did 2, and that doesn't prove anything.
I mean,
and Carl Sagan in Cosmos drilled it into every kid's head.
Wait. 2 does work. All I'm saying is, if you get a local sun at the right distance, you can also get it to work on a.
Right. So you're telling me Aristophanes believed, even though he believed that the sun went around the Earth, he thought it was an infinite distance away?
I like to stick more with like the here and now. An experiment by 37 people around the world, where and here's the thing: when you do the mathematical model of flat Earth Eratosthenes, is you end up with what's a linear curve versus a power curve. So it turns out, and when they did this data, when they mapped 37 different places, it matched perfectly, almost perfectly, what would happen when you model this on a globe versus a flat Earth.
You have to assume a distant sun. You have to assume the sun's 93 million miles away?
I didn't even want to get into. I mean, that's just more than I wanted to get into. But that's
part of the base assumption.
I'm saying there is no way you can get 3 or more data points to work on a flat Earth. It just
there's
doesn't
no
work.
way.
No, but there's no way to triangulate the sun today anyway, right?
No,
it actually does work.
Can you triangulate? It actually does work. Can you triangulate the sun, Bryant, today?
You can. Well, I'm not. I mean.
Well, the answer is no, but they can't triangulate the sun today, so they also don't have the ability to triangulate. Now, their excuse is it's just too far, so they can't get the.
Again, accurate. You can measure the distance to the sun through knowing how far Venus is away. And then you can get the angle.
How do you know how far Venus is away?
Tell me how you get that.
They have done it. They bounced radar off of Venus.
Who's they?
Okay, you've seen it? haven't seen that done.
Again,
Wait.
you guys disregard everything.
Do we have
science
background
says.
radiation coming from the sky anyway? How do you differentiate between what you sent and what's already coming?
And Brian, you're taking that. You've never done it, and you're taking the word of NASA, a government-run agency that you know that they're lying to us.
You guys don't even know how far your sun is away. I mean,
yeah,
we don't make claims we can't prove. That's the point. We're falsifying that
model. The thing is with science is we have a mathematical model and we find the results fit the
doesn't
model.
mean it's true.
Science isn't math.
I mean, what I mean by that is when you look at the distance away, it all matches perfect with the heliocentric model. So it's not that we're just using radar.
It does. They made it match perfectly to teach it to you in kindergarten.
And actually, they change it all the time.
Teach it to you. Yeah.
They change it all the time. They just changed Polaris. They said it's
just
100
one
light
thing.
years closer.
And now the moon's in our atmosphere.
Okay, I'm not going to be able to get through any of this if you guys keep.
But just about the moon, real quick. When they launch a beam at the moon to get a reflection beam, they say they send 1 quadrillion photons and they get 1 back. One photon out of 4 quadrillion.
But again, the distances we have, if you understand, Kepler's laws, you can actually see that it all works perfectly on the heliocentric model.
All right.
Yes.
We can maybe move on because I don't think we'll ever get through it. Like just reifying the model isn't proof of it. Mathematics, I can show you a Superman equation.
My initial plan was just to kind of go through the slides and have open for discussion because we're never going to get anywhere near through any of this.
Yeah, I agree. I think we kind of let him present some of his stuff.
Go ahead. We can agree to disagree on that.
Yeah, let's agree to disagree. So this is something that, I mean, I've yet to hear. I've heard you guys try to explain it. But there are direct flights. You guys realize that, right? There are direct flights by 2 airlines, not just the one which you claim is like government. I've heard some of you say it's like government people and 5 coats of paint on the plane. Didn't you say something
7.
like that, David?
7.
Okay. But I mean, you really, because you guys do realize that if these direct flights exist, which Wolfie 6020 is,
which they do. And you can actually go to you can see the Great Circle route, and you can, if you're a pilot, you can load this in and see that it does follow a Great Circle, and you can calculate the time that it takes. Of course, they have all this in their flight plan, and you can download this flight data at flightaware.com. So you can actually look and you can actually see for yourself like the flight data at flightaware.com.
Yeah, so we
get that from a free account. And so, but if you map this exact route on the flat Earth, it ends up going this absurd distance. Because if you go, again, you guys say, well, it stops in Los Angeles. But then if you do that, we can actually see the time it would take to go to Los Angeles and back again. And I mean, you guys agree, right? If I offered to pay a ticket for one of you to come with me from Los Angeles, and we all take our own GPS, right? And we're able to time how long
the global positioning system. We want to know where we're at on the globe.
Radius value.
That's going to help us.
Okay, so, but again, you can do visual proof. There's a lot of things you can do. So basically, you're going to deny everything, right? That's pretty
no, we don't deny
just
anything.
Don't believe reification fallacies. If you're begging the question, it's useless.
But how can you explain this? You guys can't.
I've explained it. We've explained it many times.
We can.
Explain it then.
Okay, so here's one thing you need to tell me. So on a trip from Sydney to Santiago, if you're talking about on the globe, that when you do the mathematics on it and it comes out to say 500 miles per hour the plane's going, then you look at the winds aloft, you look at the jet streams there, and you realize that they go 150. Hold on, they go 150 to 200 miles per hour. So that means the plane was going 300 miles per hour and taking a 200 mile per hour jet stream to get there in the amount of time. Doesn't it make more sense that the plane would go its maximum speed of 500 to take advantage of the extra speed and actually be going 750?
Well, they know the time. It's like it's 14 hours one way and 12 hours the other because there's wind. The world has wind currents where. I've driven back and forth across the coast. I know it's faster one direction than the other. I mean, but not twice the time though. I mean,
Who said twice the time?
Why would it have to be twice the time?
No, it would be twice the time if you map this exact route out, which again you can download the flight data and put these coordinates into the flat Earth map. You end up with a route that goes like this. And this,
okay, so it's the GPS uses the globe in contention, bro. It's well documented that planes can go over 800 miles per hour. It's documented mainstream that planes have been clocked going over 800 miles per hour. That little app you're using doesn't actually get ground speed. It gets airspeed, which is relative to the static pressure around the plane. So it's begging the question.
Well, the air moves with the Earth. I'm sorry, but we'll get into that later.
Okay, no, that's not what he was saying. Because that's not what he was saying.
The atmosphere, we'll get to that.
Hey, wait, Brian, let me just interrupt for 1 second here. We're going to let you talk as much as you want. But when we interject, let us just get our quick point across without interrupting, and then you'll go right back to you. Okay?
And let me just say one real quick. You also say like, oh, you guys are just going to reject everything. But you have to realize from our point of view, everything we're telling you, you're rejecting without even thinking about it. You're not even entertaining our thoughts.
Okay, but how do you explain this?
I just did.
We just did.
I just did, and you weren't even listening. What do you mean? What's wrong with what I said? So the plane that takes, hold on.
You can map this distance on the flat Earth, and you get a ridiculous arc.
Why do we have to fly all the way out?
Yeah, why would they fly
based
out
on
there?
the software you're putting this in? Who
this
made
is
all
not
this?
The software. You can go.
This is not the flight route that we know happens. With these two.
So we had Bryant. We had somebody take that flight, and they did it live on my channel. They live streamed their flight.
Right. I'm sorry. I'm showing right now. Max. This was Max Egan. He did it, and he clocked. He said his compass. He was expecting to be heading south or west. But he was going northwest, and then west, and then southwest, and then south. And we checked it out on a flat Earth map, and it makes perfect sense. Here's the plane right here. And it's just going northwest, and right there, west for a split second. Then it's going southwest, and south. And his compass readings, his actual physical compass readings, matched the flat Earth map.
But we're way off.
Did not match the globe map.
No, it didn't match what was on the back of the seat in front of him.
Okay, well, send me his information. I'll take a look at it. But I've seen a lot of contrary flights that have been done and been documented very well.
And just one more thing, 40 seconds. We don't know how fast airplanes are flying. It is very well likely that, to hide this information, on one way they're going 400 miles an hour, and the other way they're going 800 miles an hour to make these times. I always notice a plane is like, oh, we took off an hour late, but we're going to make up that time in the air. They have the ability to make up that time in the air. The last thing is, think about this. On a globe, northern hemisphere on the top, southern hemisphere on the bottom. Go find a flight route between any two northern airports that dips below the equator. You won't be able to find one. They go north to north to north, and they never dip below the equator because that doesn't make any sense on a globe. But
there's cabotage laws, right? I mean, you can't. If you're an airline in the northern hemisphere, you have to go to the southern hemisphere to go back to the northern hemisphere.
No, there's all of the flights. At least I haven't found one yet. It doesn't mean that there aren't. But they all make the line, the pretty much the line you would think. But in the south, deep south, going across the globe, they go all the way up into the north many times and all the way back down.
Well, that's because of cabotage laws, but they also have direct flights. So like I said, this.
No, I'm talking direct flights, but they'll go. Some of them are direct, right? Some of them stop, but they go these ridiculous routes that make no sense. And just in the south, not in the north.
Okay. Let me say one thing, Bryant. Let me just show you one thing. So the other thing that's weird to me is there's always these cases where I'm like, well, if they have this, it would be hard for us to explain. One of those was undersea cables running from Australia or New Zealand to South America, because when you go look at the map of all of our undersea cables, there's no cables that run across there. So then I said, that's peculiar. Why wouldn't they have cables running there? Then I went and looked at, well, let me look for cruise ships. There's no cruise ship that goes from New Zealand or Sydney to South America. Why? Because it's way bigger of an area than we've been told. So if a cruise ship went out there, they're going to you can't make a cruise ship get a jet stream like a plane. A plane can grab an extra 200 miles per hour. A cruise ship can't.
I have to research it.
Okay, well, I'm telling you, so don't just dismiss it, but think about it and research.
That's a great answer. No, that's a great answer.
Let's move on.
Good answer.
Great answer. Yeah. You have to research it. Great.
I didn't create this little. Again, to me, it's an impossible flight. I've looked at it many times. I don't buy your explanations. There's just no way on the flat Earth you can follow the actual coordinates that are in a flight log, and when you actually enter them, this is not made up. This is actually entering when you actually enter the coordinates on, not here, but it comes out something like this.
Yeah, but a plane just is put in.
You
just put in the GPS route.
You just put in the route and it just goes. The plane just flies itself. So it's like dead reckoning.
Right?
Now, if you said the planes are going supersonic speeds, then that could possibly make up the difference.
They literally do. Admittedly, mainstream, they go over 800 miles per hour in the north.
That's what we're saying is the way that they can.
That's it.
The jet streams down there in the south.
But again, you got to show me proof that they're going that fast.
The jet streams,
it's public information. Okay.
Yeah, the jet streams go 250.
Then you'd be, it's a sonic, there's a thing called a sonic boom that, you have.
But they can do it over the ocean. You won't do it on the ocean.
Happen in jet streams because of static pressure around the plane.
People above will hear it though. People above will hear it though.
Above what?
Not out in the middle of the ocean. Someone's out in the middle of the ocean. A plane goes. those, they're not going to hear anything.
If they
Called static pressure.
If they got to do these speeds, then there's going to be places where they're going to be going over land.
Above water. No, you could get out. You could get out over the water. You would get out over the water and then take off fast.
All right.
Okay, let's just move on.
Let's move on.
Okay. We're not going to make any headway here. So one little thing I just wanted to, again, I hope we can move on because I don't think that we're going to come to any type of consensus on that. But send me some stuff. I'll take a look at.
That's a good answer.
Yeah,
we like it.
No, I look at stuff.
But you have to have an open mind. If you look at stuff with the already preconceived.
I do have.
Well, we're saying things and you're not even listening. We just gave you an explanation for how a plane can do it in the South, and you're just like, no, I don't think that it's impossible. I think it's impossible. We're like,
I spent a lot. I don't know how that. I mean, the faster speeds is the only way it's possible. Then
that's what we said.
Everyone knows that happens in real life, though.
It's openly admitted.
Supersonic. I mean, like 1,400.
No, it's not supersonic.
No,
if the wind,
1,400,
and if the
800 to 900 would do it. 900
would do it.
900 would do it.
Well, not when you do that distance. You do it.
850.
You're drawing a big U. You're drawing that line. So nobody who flies in that route ever sees Antarctica. You would see Antarctica from that route. Nobody's ever seen Antarctica from that.
Actually, they do. Actually, again,
no, they do not. Go look at the globe. Wait. Go back to where you had the data points and tell me how somebody sees Antarctica from those data points.
Not on that.
Now you're changing it.
You see that when you look at these two.
Hold on, that picture on the right. Nobody's ever taken that flight route. What is that?
This is not drawn as it should be drawn. This is not the Great Circle correct drawing.
So what are you showing us?
You look at his story though. He fly.
Great Circle routes on the meridian are impossible anyway.
This might be. It's just the perspective of the.
No, that's not.
So
what's that white thing on the bottom? What is that there? No, like the white circle. What am I looking at? The top picture.
Well, let's just move on.
Is that supposed to be Antarctica? Okay.
Yeah.
Looks like a cartoon. All right.
It's not a cartoon.
They should have a real photo.
I know, but
you think so, bro?
Dave, your app has Antarctica on it. You do realize that, right?
Around the outskirts?
How so?
I have your app, and I went to Antarctica to look for someone, but it kept loading and loading. Somebody told me that they found some people in Antarctica that downloaded your app.
Yeah, absolutely.
Yeah, NASA.
We have two guys in Antarctica. Okay. One of them at KC Station, and the other one was out in the middle of nowhere. Here he is, right here.
Right there, yeah.
Yeah.
So right.
And I was communicating with him for a while, and it was quite interesting.
Okay. So I mean, again, what I want to just go over some high altitude stuff is one of the things I've noticed that flat earthers or flat earth believers don't seem to understand. Oh, I don't have my drop with you.
Oops, sorry guys, I didn't know that.
Well, denier, whatever you want to be called, is the sheer scale of the Earth. Okay, so
sorry.
So I don't know if you can you see me right now, or am I?
We got it. Sorry guys. Good.
Am I sure?
Yeah, we can see.
You are now. I had the wrong screen up, but go ahead.
Okay. Well, anyway, the amount of water on planet Earth, and I did the math. There's 1/1000th amount of water as there's volume of land. Okay, and so that's literally 2 drops on a bowling ball. I'm not a bowling ball, a billiard ball. So if you take 2 drops of water and just smear it around, okay, that's not much water. Okay, the Earth is huge. It's not like this over here. I don't know if you can see my screen, where you'd have all this water fill in a smaller Earth, and it looks like it's a lot of water. So the
but it's a lot of water. It is a lot of water. Period.
It's a lot of water. If you think about it, you are agreement that 70% of the Earth's surface is ocean. Okay. All right. And let's say the average depth of that ocean is only 300 feet. Okay. So it's 70%. Let's just say we take half of that 300 feet and put it on the land. Right. That's 250 feet of water covering the entire globe. That's a significant amount of water.
I know,
and it goes down to 7 miles.
No, you're missing my point here. The volume of the Earth compared to the water there's only 1/1000th the volume of water. Because when you take, just do the math. You can do the math and see.
All right,
you're talking about the whole Earth construction, the whole Earth construction.
The relevance is because when you get into these Earth from space pictures, in images like this, when you guys talk about the atmosphere is incredibly thin. It's actually only. This is to scale.
That's a cartoon.
This is not a cartoon. Okay, this is. If you draw,
that is a cartoon.
What are we looking at?
That is a cartoon. That is a cartoon.
No, this isn't meant to be an actual. This is meant to show you that.
Why not? Let's get some real ones. Do you have any?
Okay. But fair enough. Go ahead with the visualization.
Let me just go through the slides and then we can have discussion.
Sure.
Yeah,
for sure.
So this yellow line here is the Kármán line. This means that over 99% of the atmosphere is below this line.
Mm-hmm.
So pretty much when you have images like this that show the atmosphere looking so big, and then, how could the atmosphere be going this fast up here? And so, well, it's not that big. It's actually only relative to the size of the Earth. It's only this little bit. So the point I'm trying to make is that when you got these, these pictures at high altitude, you're not going to see much curvature. I mean, the curvature is there, but the Earth is huge, right?
You're not going to see any curvature.
So I agree. The Red Bull skydive, that was a fisheye lens. It's clearly way too much curvature. So
right.
It goes both ways. And then,
you agree if the Earth was flat, you wouldn't see any curvature either?
Well, no. What you guys do is you cherry pick images from, and I actually have looked at the actual originals of all of these, and you can actually see. If I can just load this here.
That's a simple question, though, Brian. If the Earth was a flat level plane, there would be no curvature, correct?
But I know, but you guys don't have any actual good images to show no curvature, except these ones that are cherry picked.
All the hot air balloon ones without a fisheye lens show no curvature.
And also,
it's actually the opposite. I'm sorry, it's actually the opposite. The ones that are done very carefully, when you center the frame on the horizon, you guys realize that,
that
right?
happens a lot from a balloon. They center the frame.
Let him finish.
You center the frame on the horizon, and you always see a curvature. And and the cool thing about Walter Bisland's calculator is that you can use a mathematical model that validates what the actual curvature is. So we know how big the Earth is, and we can model how it should look from a certain altitude. And what we see is what we get when we properly center the camera frame on the horizon. So you guys do realize fisheye lenses are not.
Yeah, go ahead, Dave.
In the middle of the actual photo, or the middle of a fisheye lens, it's straight is straight and curve is curve. And right down the middle, same thing. But above and below, that's where it gets distorted.
Have you seen any of these without a fisheye lens? That's what I'm asking you.
Well, the fisheye, without the Mage project.
Without.
There are.
There's no curve.
Let's say this too. That you do know that every single camera and every single eyeball is spherical and has problems with that, right? You're never going to get a flat image, period.
I've heard Bob say that. That's when I threw my hands up and just quit debunking flat Earth. When they said, "Oh, if we go out to space and there's in the window and it's my eyeball's always going to see a curve," it's like, okay,
no.
How can you debunk that?
No. He's saying that you see in a circle, so you would see that, and then also it's called Rayleigh scattering. You get circumference of light, a radius of light over a flat surface. You would potentially see that, and in addition, Neil deGrasse Tyson tells the whole world that you wouldn't see curvature from 60 miles up.
No, hold on. Neil deGrasse Tyson was wrong.
63 miles.
All right. I don't know why you guys think Neil deGrasse Tyson is somehow the mouthpiece for all of
because he's your
spokesperson.
All right, guys, hold on.
Yeah.
So Brian, do you realize that on a flat Earth you wouldn't see curvature? We can agree on that. And on a globe Earth, if you think you see curvature like you're showing us in those pictures, you have to follow that curve around, and by the time you turned around, you'd be pointing at the ground. But that's not on a globe how you would see, because it would remain at the same level. So we see in the same distance in all directions.
Radius.
So whether it's 10 miles or 100 miles, we're seeing that same distance at 12 o'clock, 1 o'clock, 2 o'clock, all the way around. So we see in a circle, right? So here's my guy standing here, and this is where he sees. This is the limit of his vision, where the sky meets the land, and he's seeing in a circle. And if you carefully look at that, draw a line across it, here's the curvature that you're seeing. It's just the limit of your vision. You're drawing a line.
Hold on. I want to know why he shakes his head at that and says no. So what about what Dave just said you don't agree with? You don't think we see in a circle?
No,
this is what
you
you're
can't
seeing.
just say no when he,
on a flat. Just think of this: if the Earth was flat, and we see, where the sky meets the land, that's the limit of your vision. Well, if it's 10 miles or 20 miles or 50 miles, whatever it is, at 1 o'clock, 2 o'clock, 3 o'clock, I'm seeing that. But you draw a straight line. You're drawing a straight line, and the point right in front of me is the 50 miles away. And as it goes out, it's getting farther and farther and farther away beyond where I can see. So you're drawing an imaginary line like this, and this is your curvature of a flat Earth. And by the way, this doesn't prove the Earth is flat. This is what you would see on a flat Earth, and it's also what you would see on a globe Earth.
But that's a fact.
What law of perspective is that, though? I mean, what
do you mean law of perspective? Are you telling me you can see further?
You're telling me that if that's a flat Earth, you're gonna see curve on a flat Earth like that?
This is
yes.
You can. So let's say there's a cumulus cloud day, and all those clouds are sitting there, 5,000 feet above your head, and then 20, 30 miles in the distance, those clouds are touching the ground. Well, that's the limit of your vision. Okay. because you can't see. It's the convergence point. So that's the limit of your vision. So whether that's, so it's 30 miles that way, it's 30 miles that way, it's 30 miles that way. And if you connected all those dots, you're drawing a big circle.
I'll tell you where I know where you're getting this. It's the 0.02 degrees of angular.
No, I'm not talking about that at all. I'm talking about.
But that's the vanishing point, Dave. The vanishing point comes from the 2.02.
Okay, so
you realize that, right?
No. I'm not talking about. I'm talking. That's.
Not listening. I'm not listening.
That's you trying to squeeze in between the sky and the ground. I'm not talking about that. I'm talking about in these images, the farthest you can see the land is the farthest you can see the land, and it's in the same distance in all directions. That is a circle. You're looking at that because of your programming and saying, "Oh, that's the curve of the globe."
Sphere.
It's not the curve of the.
No, but you guys do know what Rayleigh scattering is, right?
Yeah, I just brought it up.
The Rayleigh limit. I mean, the Rayleigh criteria. I'm sorry.
Yeah, I literally just brought it up. One that brought it up.
So the Rayleigh criteria says that even though our angular resolution can only make out a certain level at 0.02 degrees, light is still hitting photons are still hitting our eyes. So we are still receiving light beyond that. There is the vanishing point of perspective is not a point. It doesn't end there. It's just, that's the limit of our vision. We can get a telescope and extend that further, but we're still getting light beyond that. Yes, we are. This is the Rayleigh criteria.
So, okay, but
the
you would have
a
to block light
of
from
light
further.
with a local light source, and then you would literally actually be able to see a curvature, or like imposed with the convexity of your eyes, you would see a slight convexity. And you can replicate this in Blender or whatever you want to do. It's just like objective. And
and if the Earth was flat, Bryant, and you were looking across the Atlantic Ocean, let's say from the east coast of the United States to Spain, you do recognize that it doesn't matter what telescope you have, you're not going to be able to see through the atmosphere.
Well, again, but you can see if you're on and then that's another.
Well, you didn't answer my question. Would you agree that you would never see across the Atlantic Ocean, whether it's a sphere Earth or a globe Earth?
I would say that on certain conditions that are very clear, you should be able to.
Wow, we can't see 500 miles, and you think we could see 2,500?
I'm not saying we can see 2,500 miles.
Well, that's how far it is across the Atlantic Ocean.
If the conditions, I don't know. I mean, the conditions.
Continuation of light, bro. Come on, man.
Light keeps going. You do realize that.
Not through an atmosphere.
No.
My goodness, it's called attenuation of light.
Just like sound, man. Sound travel.
Light spreads out. Light has to fill. Light is going out in a. Let's say its radius becomes a sphere. It's going in all directions. It's getting thinner and thinner and thinner to the point where you can't see it.
Dave, I've done the calculations with the star. Let me just go to that point now, since you're bringing it up. Because I actually did an experiment where I proved that I could see further than my angular resolution. And I did it right here. And I bought this little bulb here, and I measured the radius of it, and I figured out exactly what the limit of how far I could see it, which would be about 30 meters away is where my angular vision disappears, right?
Yeah, you can see light further away. Yeah,
you can see light a lot further away. And I've heard Dave talk about this, and it's provenly. I mean, I did the whole calculations with Alpha Centauri, and there's actually right here. It's very easy to explain why we can see Alpha Centauri.
No, it's not. You have to. How do you know the mass and the brightness? How do you know the mass of that star?
Because guys have figured it out.
Alpha Centauri. Again, this gets into like many decades of astrophysics and astrology where they've mapped out. But again, if you can make the easy assumption that, and this is based on good science, not an assumption, but even if you don't believe, I'm talking to you guys, you don't believe mainstream science. That Alpha Centauri is about the same size as the sun.
How do you know that? How do they know that?
Again, it's the equations they use.
How far is Alpha Centauri?
Equations are not
Alpha Centauri is
reality.
4.4. Right. And again, Dave, just look. I did the calculations here, and we know that the sun, because by your argument, even if it wasn't Alpha Centauri, if we put the sun where Alpha Centauri is, you would say that we couldn't see it.
So you
would say we could.
Can we just walk it?
The calculations are right here.
Hold on with the calculations. Just one question, then you can keep going. Do you believe in the inverse square law of light?
I've actually done videos on the inverse square law.
Yes or no? Is it a real thing?
But I'm showing you that this thing takes into account the inverse square law, and what the conclusion is we actually have. You can do the calculations. The amount of photons that hit your eyes.
No photons hit anybody's eyes.
Stop with the photons hitting the eyes, man. You're tripping me out.
How do my eyes protect myself from that kind of speed?
I feel like you're threatening me physically or something when you say that.
It's the amount of light. Okay, you don't use the word photons. It's the amount of light. There is light hitting our eyes provably, if you say the sun is where Alpha Centauri is, you can do the calculations and show that light is hitting your eyes from that location.
To do the calculations, you need the mass.
No, you just agreed that we could assume, just for argument's sake, that we could put the sun where Alpha Centauri is, and based on Dave's rationality, we would not be able to see it.
We would not be able to see it.
Well, no, we would. You actually can prove.
But hold on.
So wait a minute. Wait, I just want to ask a quick question.
The actual amount. You know what, Bryant? You guys
If we went halfway to the sun, would the sun be 4 times as bright as it is?
I've heard this argument. That's what I'm trying to.
I'm asking a question. Do you believe? Am I wrong or am I right?
Him. Yeah, disprove him.
I've heard all that, so I'm trying to explain the answer to that.
He's asking, would it be 4 times as bright?
Would it be 4 times as bright as the inverse square law dictates?
This is why I didn't want to go 4 against. I mean,
No. I'm just asking you one question. That's it.
We can be quiet. We can be quiet. Let Dave do it.
I've actually taught the inverse square law. I understand, like your balloon analogy, how the balloon thins out. Okay, that's not incorrect, but you've got to realize that if you're using light, it would have to be a ridiculously thick balloon, because the amount of energy coming out of, well, again, we could say the sun or Alpha Centauri is, and again, this is based on many decades of astrophysicists doing lots of careful research to map out the stars. And again, when you study this and get appreciation for the predictive power, but if you don't study science, you don't really appreciate how all these things can be predicted, how everything falls into place. But if you can just take this amount of actual luminosity, which is the brightness of Alpha Centauri, and take that inverse square, yes, it does drop off by an inverse square, but there's still.
What does luminosity as constant mean?
Luminosity is constant. Brightness diminishes by inverse square law. But the luminosity, the power output, is this. Here's the power output. Is like, let's say 6 times 10 to 26 watts. So that's a lot of light. That's a real thick.
Luminosity is constant. What do you mean by that?
The luminosity is the brightness. So that's the amount of power that's getting radiated out. Okay. The brightness is the inverse square. This is what's called a radiance. So a radiance is measured in watts per meter squared. So that's what spreads out by inverse square, okay?
Okay.
So when you get to the Earth from that distance of Alpha Centauri, you still have measurably 2.7 times 10 to the minus 8 watts per meter squared. And we know the minimum detectable amount of light for our human eye is actually, we can detect that perfectly fine, because we can detect as little as 10 to the minus 10 watts per meter.
So you did the math on the closest star, the very closest star that there is,
I know, but
right?
the closest star, but there's more than enough. But you do realize there's only 5,000 to 6,000 visible stars. So it's not like we're seeing like the whole galaxy. We're only seeing our local vicinity.
You don't know the distance to the stars. They just changed Polaris distance by 100 light years and admitted they were off by 100 light years, over 30%.
I've got the data from Polaris, but we can.
But yeah, the data that they changed already.
They changed
which version do you have, Brian?
Brian,
I
do want to ask him though, Dave. Let me do this one, because I just want to ask him.
You guys think that Polaris is staying in place, but it's provably moving.
But wait, that's called a diversion, right? Because you're bringing up something that requires the distance to the stars to make your whole argument. So I'm like, but you don't actually know those distances. For example, Polaris.
This is where science comes in.
For example, Polaris was just they come out and admit that they were off by over 30%, and it's 100 light years closer at least. So you admit that. We don't actually know for sure that these distances and masses are correct.
But I'm saying the actual movement of Polaris, we map very carefully.
Okay.
Okay.
You're changing it now to a different conversation.
I was trying to explain before that light, the reason that we can see light, there's a good explanation why we can see light so far away, and it doesn't drop off.
Brian, can I ask a question?
Can we just walk him through the distance thing? Because I want to know where he thinks that we're wrong.
See, I can't debate 4 people.
No, it's not debate. I'm asking you a question.
We're
it's a conversation.
asking a question together. We're having a simple conversation.
I just get into one thing and it's like,
no, we're still talking about the sun and whether we would be able to see it far away. But
yes,
Dave,
you would be able to see it far away, provably.
But hold on,
so
Dave always talks about the sun if it were right above our heads and still 867.
I've seen him do that.
Okay, it would take up the whole sky, right? So then we move it 93 million miles away, and now it's the size of a dime, right? So if we did it again, doubled that distance, then it would be smaller than that dime, right? Let's say half as big.
Going by angular resolution, though. I already know where this goes. And when you get down to the 0.02 angular resolution where we couldn't make out details, but remember, our eyes are photon receptors. It's not about, and this is why I did this. This is why I did this little experiment, because I could show that even though my eyes could only see it 30 meters away, I was able to see this light like 300 meters away.
Yeah, but if
It's
we keep
our eyes are photon receptors. It's not about angular resolution for stars.
no, but we didn't bring up angular resolution. We're just talking about the sun. If it reduces in size at 8 minutes,
Yeah, but
it
is angular resolution though. When you reduce it and reduce it and reduce it to the point.
Okay, but
where
then you
it
have to
vanishes.
multiply it by just to get to a light day. You have to multiply it by 24 eventually, and then you have to multiply by 365 just to get. You're talking about the sun reducing, doubling its distance 365 times.
That you're going by size of like something like when we look at angular resolution on the planet, we're looking at things that are reflecting light. Stars are incredibly
It's the same thing,
powerful.
though. It's the same thing.
It's not, no, it's not.
Wait, the inverse square law. Hold on. I want to ask him though. The
It's
inverse square law.
absolutely not
Are you
the
saying
same
the inverse square law only applies to light sources, not reflections?
No, the inverse. But it's well, it applies to that. But the thing is, the light sources have a lot more light than the reflections do.
Okay.
It's the number of photons that hit our eyes, guys. It's not how far something away is.
All right. So can I just ask a question and you can school me?
This is easy to do if you guys can just follow the math. It's easy to show that the sun could be visible to our eyes. I mean, the light from the sun could be visible from our eyes if it was an Alpha Centauri distance away. Meaning, it would look like a little point in the sky with light, but it would hit our eyes because it's not about how big it is. It's about the photons hitting our eyes.
So at what point would it stop being seen?
Again, I know that when I've done the calculations with like say Pluto versus Alpha Centauri.
Never.
And if you look at the size of Alpha Centauri versus Pluto, Pluto would be like 10 times smaller. But the reason we can't see Pluto and we can see Alpha Centauri is there is just an enormous amount of output of light and energy coming from stars.
Can I ask just a couple questions as not a scientist?
Yeah.
There's a certain amount of I could be wrong. Is there a certain amount of photons coming off of a star? I mean, there is a certain number. If you could calculate what they are, it would be what it is.
It's ridiculously high. Yeah.
So yes, forget the number. It doesn't matter. So as you increase the radius of that those photons are going to be getting less and less and less, and that's where the inverse. Hold on, let me ask my question, please. So that's where the inverse square law comes in, where every time you double the distance, it's 1/4 of the brightness. Right. So when you get so if I went halfway to the moon, would the moon be 4 times brighter? Yes, right. The answer is yes. Would you agree?
The moon is not a star, Dave.
Okay, so it doesn't matter. Just hear what I'm saying.
It actually does matter.
Wait. So the inverse square law does not apply to the light coming off of a full moon.
Again, it's not about the inverse square law. It's about the number of photons. That's what.
But okay, so the number of photons is 4 times as many when I'm halfway there in the same square foot of space.
Okay, right. Yeah, when you got.
So is that a yes?
Right, but there's a lot less light. A lot less.
So hang on. I'm not comparing the amount of light. So I got a square foot box. I'm looking. Okay. I would be done with this in 30 seconds if you just hear me out and just answer. And then I want to throw it back to you because this is about you getting your information out there. We don't want to stop you. So I got a square foot. I got moonlight coming in. I go halfway to the moon. Now there's 4 times the amount of moonlight in that square box. Agreed? Halfway again, there's now 16 times. And if I go all the way to 100 miles from the moon, it should be over 60 times brighter than the sun, according to the inverse square law. No, according to math.
The surface, you do know the inverse square law goes by the radius.
Just leave your camera on, Nelson.
Right?
Sorry.
When I take, for instance, a gravitational drop off from the Earth, the 1/r squared is not r from the surface; it's r from the center. You got to take the center of celestial bodies to do the 1/r squared drop off.
All right.
It's a very big R that you're doing 1/r squared. You can't. I see what you're doing, but you're going to the surface. You got to look at the r squared as the radius of the moon. Okay, that's a big radius. So when you, I mean, this is gravity, but the light holds the same way. The surface area is going to be related to the curvature, space, time, and gravity. So it's the same kind of thing. You got to look at the radius. And you got to go the other direction from. Okay,
so we're off the inverse square law. We're onto the radius. Go ahead. The next point, wherever you want to go.
But all I was trying to get at with that is I've heard your discussion of that, and it's the flaw with that thing is it's not angular resolution. It's actually light that we see. That's why we can see distant stars, because the amount of power, the amount of radiance, the amount of luminosity is just unfathomably large.
But we don't see some stars, right? We don't. Some of them we can't see.
No, yeah, some we can't see, but I'm saying there's, again, like I'm showing these calculations here, if you do the 1 over r squared from the luminosity, if it drops below 10 to the minus 10 watts per meter squared, then our eyes won't pick it up. So right, that's why we only see 5 or 6 or 7,000 stars in the night sky.
And I think, isn't it true out of all the 5,000 stars or 6,000 stars, whatever it is, that the sun is the third smallest? They tell us that it's an average sized star, but it's actually the third smallest out of all stars.
I have to look it up. I don't know the answer.
Well, of course they need them to be bigger because they need them to be bigger because they need to explain why we can see them.
It's not about that. It's about luminosity. It's not about the size. It's about how much light it's emitting. Because that's what's dropping off 1 over r squared. It's not the size of the orb. It's the amount of light that's dropping off 1 over r squared. That's what that was the mistake in your Alpha Centauri argument that I heard.
If you do the math, the closest star, how many times brighter than the sun would it have to be for us to see it?
Well, I mean, it's over 100 times more. And but you know, like Polaris is like 48 times the size of the sun. It's much bigger than. I mean, Alpha Centauri is about the same.
It's 48 times the size of the sun, and it's like 900 quadrillion times farther.
I know, but again, you got to take the again, this is why when you don't do math, you can't see it.
Wait.
For you guys,
Dave, could you just repeat everything you just said, Dave, your last sentence? Maybe he didn't hear you.
So
I did hear him because I can do
how many times brighter is Polaris than the sun? Is it twice as bright? Because I can't imagine something twice as bright as the sun.
It's not.
It's way more than twice.
I know. I'm just saying I can't imagine twice as bright.
So that's unfathomably bright. It's very.
We'll agree with that. I mean, that it would have to be unfathomably bright.
Well, but again, you got to realize that astrophysicists map out the stars and have very precise equations where they do very.
But
I'm not an astrophysicist, but I mean, I look.
But all the stars don't move, right? All the stars relative to each other don't move, so they could legitimately make up any number that they wanted, right?
They do move.
No, they don't move in relation to each other. So I'm saying you could
actually do. The apparent motion of the stars does move. But
apparent motion?
I'm skipping over.
But do you recognize that if we all got together before anybody got here and we assigned distances and luminosity to the stars, that we could just assign to them? How is somebody going to disprove it?
Do you guys understand how astrophysicists work? It's a lot. It's like years of careful looking through many observatories.
And they're off by 100 light years.
They look real careful.
Polaris.
Real close.
I mean, it's not that they don't make mistakes. It's just that I don't know about that, so I have to look it up.
Trust the science. Don't question the science until they tell you the science is wrong.
Questioning the science is that a lot of things fall in perfect alignment and make a lot of sense when you study it.
And if I made a model about Superman flying, and then I saw a shooting star, and I said that's Superman flying, and the math matched, but that means Superman was flying.
You guys pick like one. You guys look for the one flaw and then ignore all the other things that are making excellent predictions. You know, and then
because excellent predictions doesn't mean that it's true. It doesn't mean that we just accept it then.
Who's the scientist that said that
they made predictions about the eclipses before that they knew the Earth was round? They knew about eclipses back.
Your model can't even predict eclipses. I mean,
what do you mean?
NASA's using a geocentric model in the Saros cycle to this day. They don't have a 3-body equation, but this is the problem. Everyone says predictions, but that's not true.
Geocentric is still a spherical Earth.
But Bryant, but it's not moving. And so, but the problem is it's not predictions, it's post-dictions, okay? We make observations and then we take the math and we make it work in our model. It doesn't predict things that aren't already known. It takes what is known and then it reverse engineers the math.
You guys have no model. You can't even predict why things fall.
So that means that it must be not true.
Well, hopefully we'll get to that and I will show you you're drastically wrong about that.
Oh yeah, I can't wait to get to hear what you guys have to say about gravity.
That's why I'm hoping we just move on past all the reification fallacies and the, you know.
Okay.
Yeah, we all went to kindergarten. I mean, we know the basic stuff that you believe, you know.
Easy, Sean. Easy.
I mean, this is why I wanted to do
Pope number 1.
No, Brian, I'm just playing. Brian, it's a joke.
I know,
man.
but
Brian, and by the way,
I can't have a discussion with 4 people. It's
just we're all making the same. It could be one person saying all of the same stuff. This is just a little more efficient.
I can agree to be quiet. I got a toothache going.
We'll be quiet.
I'll be quiet.
Everybody mute. Go ahead. Good, Brian.
This is what I feared was going to happen, but anyway.
No, don't. What are you fearing? We're having a great conversation. Come on.
Yeah.
You were afraid that maybe we'd make some sense. Maybe that's
not. It's not making sense. I just can't explain. I mean, I've heard all your stuff, Dave, and everything I can. You know, it's not difficult to.
But you're just dismissing everything outright. You're not.
I'm not dismissing it outright. I can do. I spent hours doing these calculations and doing experiments
Okay,
so I can show to myself that this is not true.
Okay, so show back the image you had before this. You just had the sun above the flat Earth.
Okay, yeah. So again,
but hold on. Go back to the image you had. You showed us the sun above the flat Earth. You had arrows drawn to it or lines drawn to it. Said, "Can we?"
Yeah, I mean, this again. I know. Again, I know you guys get this all the time, but I've heard your argument.
Do you realize how close the sun and moon would be to the Earth? That is ridiculous, right there. That the sun and moon, if they're 3,000 miles, is what?
Are they 3,000 miles?
No, I'm saying even if they were, right? A lot of people think it's much closer, and the sky is much closer.
If there's much closer, then we'd be getting hotter going up in altitude. I mean,
because the sun lights up, the sun heats up air. It doesn't heat up just because it's the sun. You can get closer to the sun, and it's not going to be hotter.
Really? You're going to really say that? But you can get closer to the sun, it's not going to get hotter? Really?
Have you ever been on a mountain at the equator? You think it's sunny and
right,
beautiful
because
there?
the sun is 93 million miles away, and the reason that it's colder at high altitudes is because there's less atmosphere.
That's what I just said. That's what I just said.
But I'm saying if you have a local sun, that doesn't make any sense going up in altitude for it to drop in temperature.
It does. It does the same. What?
If you have a local sun and you go up in altitude, you should be getting hotter, not colder.
Why? It's the same atmosphere being lit up. It's the same atmosphere being warmed up.
It's a lot. I know, but 93 million miles away is the light comes in more or less parallel, not exactly, and it's it's coming in at a much more uniform. If you have a local sun, you're going to have hot spots right below where what's floating.
And we say air is less dense.
All right, let's agree to move on.
Okay.
Okay, now sunsets. This is one I've seen in your documentaries where you have, and even Dave uses this sometimes, where he has the sunset fade back and disappear. Well, I lived on Siesta Key for 7 years, and I actually did sun gazing for a year, and I watched almost every day when it was sunny and I could do so, the sun sink all the way down. I mean, I was staring at it, and it really did look like this. It wasn't just vanishing or disappearing or getting smaller. The sun does not get smaller when it sets. It stays the same relative size. And anybody with a good solar camera and a solar filter, a solar filter on a camera, can see that the actual size of the sun does not get smaller.
And again, so if you've looked at certain people, they've shown that if you take 2 tennis balls and you take that camera up away from the tennis balls, then they don't reduce in size when they're away from each other. So
that's not how perspective works. I'm sorry.
It is how perspective works. So
no, it doesn't. Perspective works. You understand? The equation for perspective, 2 arctangent of x over d the distance.
Oh, that's how it works. Oh, I didn't know the math on it.
No, but I'm saying that what that equation is showing is that it's basically angular resolution. That's the angular resolution equation. Is that as we see things in the distance, they get smaller towards the vanishing point.
But not things on a ceiling that are far away from you. They would maintain. I can show you
everything.
I have it right here.
Oh, thank you.
I have an example right here. So.
Not listening.
Hold on, let me just show you.
You're already shaking your head.
You're making a claim.
But hold on.
You're making a claim.
Hold on, Brian.
You're saying you don't believe it. Let us show you.
Brian,
let us show you the example.
He says
then we'll move on.
But I don't understand why when you say you have an example, he just shakes his head and he's all upset. Like, I'm not going to look at anything. Why would you be like that?
Why wouldn't you look at? Let us show you what he said. Let us show you a physical example, not a calculation. An actual measurement.
He's already dismissed it. It's kind of like pointless. What is he going to?
I've seen it though. I've seen.
And what you've seen this.
So now, why are you just said how perspective works, and he's about to disprove what you said? So how have you seen it, and you still are saying the same thing?
A meme versus reality is what I'm talking about.
This is a camera. This is not.
This is a meme.
This is not how your.
This is exactly how your eyes would see it.
No, your eyes will see that ball getting smaller in the distance.
It is smaller in the distance. Look,
you see the ball in the distance right here. It's smaller because it's farther away.
Right.
That's how. But when something is already far away from you, so now we're up high. You could flip it over if you're looking up in the sky, and they're both pretty close to the same size. And as it moves, it's almost the same size. Okay. And when you said depending on a camera, good solar filter, the sun doesn't change size. Many times it has changed size. We show that the sun does change size, but it's a little different every day depending on the atmosphere, what's going on, and what you're looking at. Yeah, but it does clearly change size.
It changes sizes a little bit throughout the year based on our distance from the sun, but it's not much.
It changes over the same day.
Solarium says it changes throughout the day. It actually gets smaller and bigger throughout the day. Solarium data does.
Depending on the weather conditions and what part of the Earth you're on, in my opinion.
There might be some refraction, but in general, the sun stays the same size during the whole.
It also can magnify at times too. It's an optical illusion in my opinion.
A little bit.
And
Brian
Brian,
didn't do it at all.
I'm the same distance. I'm straight over this ball, and the other ball is pretty much the same size.
But that's not the perspective works. Perspective.
That's exactly how perspective works.
No, it isn't. Perspective is from your eyes going out, Dave, not from the top looking down.
Well, when you're looking at the sun, is it your eyes
flipped.
going out, or is your eyes looking up? Same thing as looking down. When you're looking at the sun, if the sun was right in front of you, literally in front of your face, and went away, it would get smaller. But because it's up high, so your sun's this would be their sun, and it would get smaller, sure. But because it's up high, you don't have that perspective.
Picture looking that in this. That's in the sky. Don't picture like we're looking down. Flip it up in the air.
I'm looking up in the sky. Here's the sun at noon, and here's the sun at sunset.
Yeah,
that's how perspective works. I'm showing you.
That's not how perspective works. But okay,
we're looking at it.
All right. Listen,
all right.
Listen, guys. This is okay. We can agree to disagree. Yeah. Everyone makes up their own mind on how that one worked out. Let's go to the next point.
I know, but this is okay. This is perspective. This is how perspective works. But okay, we'll just move on.
That's not. Hold on. That's not. I'm not going to let you say that. That's not how perspective works.
A meme,
not at all.
Reality.
No, it's not. It's a calculation of. This is angular resolution. It's based on this arc.
Okay, but nobody ever is seen from the side view like this ever. That's not how perspective works.
Well, it's not from the side. It's just trying to show you this is the equation for calculating how your angular resolution, when an object goes off in the distance, it gets smaller.
Halves and doubles, right?
This is a known perspective. This is how perspective works. When you look at something in the distance, it gets smaller by this relationship.
Halves. It's called halves and doubles when they talk about art. In art, perspective is halves and doubles.
The arctan is not. But this is just it's a pretty well known equation that even like opticians and optometrists know for angular resolution. And so when you take this idea, it's just a simple.
No, but that's not how we see things. That line that you've drawn there.
But the sun can never set and get close. In fact,
that's
you
not
have
true.
to go like a million miles away.
No. So imagine that you're in imagine you're in a big room that's the room that you're in right now. Now I'm picture that it's 5 miles wide. Okay, just picture you're in a 5 mile wide room like you're in. If that light above your head started to go away from you, would it not connect with the floor very quickly?
No.
What do you mean? So you're going to see
not on this. No, it's based on.
I asked you to take the room that you're in. Imagine that it's 5 miles wide. Okay. 5 miles wide in every direction. And the ceiling is still there. Now, the light that's on the ceiling, if it starts to go away from you, it's going to merge with the floor, hit the floor, and set. And it'll even get dark where you're at. In your location, it would get dark, and it would light up the other end of the room.
Okay, but again, the ceiling is very close to 5 miles.
So is the sky is very close to the earth.
Again, if in the brightness, the point is to the brightness of the sun. You're not going to get something as bright as the sun down a hallway. Because if you did, you would see it. Because again, it's photons that hit your eyes, it's not
Brian,
resolution.
Brian, is it possible that you've never seen my sunset kitchen?
It's possible.
Vamos a hacer de cenar rapidín, pin, pin.
These little.
But I have a question for you. Is it possible you've never seen it?
I don't know that I've seen this one. No.
Okay, so it's 1 minute, so just watch before you shake your head no. So this line here is the path of the sun, and I'm viewing it from a celestial point of view. And I'm watching, it's not playing. Oh, now it's playing. And so it's moving along. Now, this here can be mountains, it could be cloud deck, it could be just the atmospheric deck. I never go below it, and the sun moves along. Now, I have another camera on the deck, on the ground, on the other side, looking at that same thing. And when I look, the sun goes down due to perspective. And this opaque barrier right here, which is now at my eye level, but it's really not, but it looks like it is. The sun looks like it's going below it, but it's not. It's going straight. And when I look at it really close, look at this line. This is a level line. It's level. But it looks, hold on, I'm not done. It looks like it's going down. Now let's compare it to a real sunset. We're just going to compare. Here's the sun. It went down, 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 down. And now look what's going on. It's going behind this atmospheric deck or mountain ridge or whatever.
Okay, now that I can tell you is not the way sunsets work. I have seen countless sunsets on.
So what are you saying? That's a fake video?
No, this can be one sunset with a certain atmospheric conditions, but in general, what you get more than often than not is a hard And I used to sun gaze on.
But in general, you're going to get the same effect once it hits another tree line or mountain range or artificial horizon.
Wait, but also you see the space here between where it's setting. Hold on. Just let me make my point, and we'll go right back to you. I'm telling you, the space between here and the ground, you can't see it. It looks like it's the same. It's compressed. I'm zoomed in here. And if I zoomed out, this would literally look like it's going behind a hard horizon. But it's just because your eye can't see it.
You zoom in, and this is what you get. No matter how far you zoom, you're going to always get a hard cutoff with the
right. Yeah. And here's the hard cutoff right here. Here's the hard cutoff. If I put a solar filter on, you wouldn't see the difference between this water and this hard thing. You would just see the sun, just like you're seeing it in yours.
But that's not fully set. It's still
it is fully set if you zoomed out.
I know, but I can't see because you're so small. I mean,
well, okay.
I think I've seen this picture before though, and I remember saying to myself, "That's not really that's going behind some refractive effects or something."
So look here. It looks like the sun's going behind a hard line, but if we zoom in, it's really not even setting. Okay, so here we go. We're going to zoom in. Jeran, can you make me big so you can see it?
Yes.
As I zoom in, you look. Oh, look! It's not even touching the horizon.
No, because it hasn't set yet.
But it will set because it's going to go behind this opaque barrier. This opaque barrier is thousands of feet above my eye line, but it looks like it's at eye level. This opaque barrier is thousands of feet.
How can that be thousands of feet above your eye line?
What do you
mean? These clouds above my eye line?
That opaque.
Right. As they go into the distance, everything merges in. The clouds are all at the same height.
If you guys buy into a flat Earth, then how could it be 1,000? It doesn't make any sense.
So hold on a second. So when I'm looking down Long Island Sound here, the clouds touch the water 25 miles away. They literally touch the water. So the curvature in 25 miles is only a few hundred feet. Okay, so you're telling me clouds that are at 5,000 or 10,000 feet have gone over that much curvature and are actually going behind a curve, or is it just perspective? I mean, I just proved that it was just perspective.
No, you didn't prove anything. That's not proof of anything. That the sun
is it curvature?
Dave, the reason
I'm talking about the clouds.
Listen, I told you I lived on Siesta Key for 7 years, and I did sun gazing for a year. I watched countless sunsets, and I'm telling you, yes, there's some days where refraction, you got clouds going on and all kinds of different things. But almost every time the sun goes not behind, it goes down below the horizon. That horizon is not
beyond. Go ahead.
It's not 1,000 feet above my head. It's dipping below the horizon. That's impossible on a flat Earth.
What? It's going away from you.
What's going on? No, it's dipping.
It's exactly what would happen if anything in the sky was going away from you. What do you think you're supposed to be seeing if a local sun was going away from you? What do you think you'd be seeing?
You'd be seeing it. You wouldn't fall below the horizon. It's impossible.
So what would it do?
It's going to set way.
Dave, can you get your Legos out?
It's going to get smaller, and it's going to go.
No.
No. The video.
No atmosphere.
He just said that you can't drop something below a horizon.
If you have a local sun, that's perspective. It should get smaller. I've even seen.
And sometimes it does.
It has, in some conditions, it has, Bryant. That's what we're saying. Sometimes it does, depending on the weather conditions, depending on if it's dry, if it's humid, everything.
Wait, here's one where it was dry and humid, and the sun should just be dropping below, but it's going away. It's getting smaller. It's getting dim.
That's the camera. If you get the right filters and the right
filters,
it's always the same size. Any really good photographer that takes pictures of the sun knows it stays relatively, again.
Are you watching Dave's screen or no?
I'm seeing it, right, but that's through a camera. That's through, who knows if it's auto exposure or you're set to manual. I mean, to really get a true picture of the sun, you got to set to manual, because some telescopic cameras will, they like make things look distorted because that's autofocus is doing stuff like that.
I know you said you saw my sun fade out videos. I have a whole bunch of them. You have my app. I have them all on there. But the sun went down, 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 down. Forget the fade out. It went down, 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 and then it stopped. And it sat here.
It doesn't stop.
It does. No, it's not going down anymore. It's going away.
Oh, it's not, David. I've watched.
It's going down.
Are you talking to people that don't live on the beach? You must be talking.
No. Actually, during the filming of this one, I was talking to people on the beach. Hold on. I was on the phone with my friends that were at the beach, and they saw the sunset from the bottom up 10 minutes earlier.
Yeah, I mean, again, there can be exceptions when you have some type of refractive things going on. But you're never gonna. I've seen hundreds of sunsets, Dave, and they go below the horizon. They don't.
Well, you're seeing the same thing 100 times. You are seeing the same thing. You just don't understand the power of perspective and the power of the opaqueness, the opaque deck. It's just going beyond it. That's all.
Perspective makes things smaller. It doesn't keep them the same size.
And they sometimes get smaller, but when you're looking out over water, water is the thickest. The atmosphere, the non-uniform transition zone. I probably got that half wrong.
I'll tell you what, Dave. Take that picture of the fade out and go to Siesta Key or some beach and poll 100 people and ask them, is this what they see every night when they watch?
No, they would never see this at Siesta Key because they're on the ground.
It's from a drone, Bryant.
And this is not over water, and it's below freezing. No one's going to be on the beach because they're going to be freezing.
Even if you're high up at an altitude, you're going to still see the sun go down below the horizon.
Over the water, yes.
Right, but it just doesn't. I mean
that air column, as you're looking farther and farther, it becomes opaque. Period.
It's also magnifying.
You can't see through atmosphere like
the water.
It becomes opaque, and when the sun goes beyond it, it just goes beyond it.
Let's just move on. This doesn't.
All right, move on. No problem. No problem. Great to move on.
Can I show a video about perspective though, real quick? It's a short one, but I think that.
No, I don't want to watch any perspective videos.
All right, let's go on.
Okay, but
we're never going to get out of this topic if we don't just move on.
All right,
true, but people see perspective the wrong way, and everybody, like when you talked about those guys who did the test and they have the arrows drawn to the sun, then they draw the flat Earth arrow to the sun. They're completely off because that's not how we see.
Well, another thing I wanted to bring up, and I'm just getting a little kind of steamrolled here, but
we're not steamrolling you.
Is that one of the points I wanted to bring up? The common denominators is that we have confirmation that the sun and Polaris and many other things will have the same angular. They have a relationship between latitude and where you live on a sphere. So we see these different angles because of us living on a sphere in different locations. And it's really just really hard to explain. I mean, you can't really explain on a flat Earth that you got a different angle of sunrise and sun. The way that sun pass trajectory is based on us being on a spherical Earth.
That's based on perspective.
That's not perspective.
Why? I wanted to show you a video. I wanted to show you a video, but you won't look.
No, it's real simple. You can look up at high noon and you can see the
but that's not how we see things. If you need to watch a video where if you stand next to like a gymnasium, the bleachers, you can see how perspective actually works.
I don't even. Yeah, this is
the globe model claims we never see the actual position of the sun.
No, it's not. But I'm going to show you. I mean, this right here is what I was going to show you. Like this is how we see. When you watch this video, you can see that it's not. This is how the sun sets from different locations. Everything converges to the same point. You're talking about perspective like we can draw lines this way.
That's not how perspective.
That's exactly how perspective works.
All right, listen, Jeran, we're going to have to let it go because I showed him perspective with the actual physical thing. He says that's not how perspective works. We agree to move on.
Okay,
these are little models you're doing. This is not, these little models you can do. I've seen tricks with aperture. Like the camera when you open up the wide angle.
Do you have any models?
Bro, you're showing memes, bro. Like what?
You're showing memes and calculations. We're showing you calculations and physical things.
But these are based on things that you can see in the real world. I've seen sunsets, and I know that
we've all seen sunsets.
They don't
fade out.
We've also heard people say they see the curve from a plane.
But
most sunsets don't shrink. I agree.
I agree with that too.
Sunsets do not shrink in size, especially because most sunsets are like to be viewed over lakes and water. We can agree on that. Most sunsets we like to watch over water. So it's magnifying. There's a lot of factors involved. So we can agree to disagree. Maybe you just don't understand where we're coming from here, man. That's all.
Basically, Brian, it comes down to either the sun's moving away from you on a flat stationary Earth, or we're falling backwards 700 miles an hour in the United States or 1,000 at the equator, and it makes the sun look like it's moving. So we'll agree to disagree. I don't think I'm falling backwards during the sunset.
I know you're not
falling backwards. That's we'll get to that in high speeds and slow rotations. But let's just move on to gravity because I don't think you're just going to use the same perspective arguments for.
It's not an argument. It's reality. We're not giving you anything that's not
memes.
We're not.
I've seen some of your perspective like videos, and it's not.
Which video?
It's just not based on real. Well,
there's nothing that we're showing that's not based on reality.
I was watching were Nathan Oakley. I was watching some of his videos on.
Well, we haven't been watching him, so.
Okay. Well, anyway, I've seen like different flat Earth believers have different views on what perspective is. Where, in general, like an ophthalmologist or an optician, kind of it's like there's just one simple type of way to see perspective.
It's not simple. But
all right, listen. You have a lot of points to get through.
Okay, I wanted to go through the one that Professor Dave didn't answer, which was how you like to. All of them. You were talking about how the seasons where it should be arctically cold because the Earth, in the morning, the angle coming in is going to just be skimming the Earth.
Right.
So did you get an answer to that, or do you still buy that it should be arctically cold because of the angle?
I shouldn't be able to feel the heat the same way I can in the summer.
Okay, but you do know that the atmosphere stores energy, right? And that the ground heats up and stores energy. So in the summertime, what happens is that this whole latitude that's getting more heat is actually the whole band is heating up the Earth, like all 20, it's going around, and every day it's getting heated up. And the ground and the atmosphere contain and hold that. It's called specific heat. And it's the reason why you're always going to be warmer near a body of water than on land. That's why deserts get hot, cold, really like wild swings. Where live on Hawaii, you got the same temperature almost all year round. It's because the specific heat of the water holds that energy, and the atmosphere holds that energy too. So the reason why, and you're right, when it's colder in the morning, we know it's colder in the morning because the sun, the sun's been gone for a while, but the atmosphere is still holding a lot of that energy. So it's not going to be arctically cold when you wake up because the ground and the atmosphere are still retaining a lot of that heat from the daytime. I mean, does that make sense?
I do agree that the ground keeps radiating heat, and it stores it and it releases it overnight. Yeah. But when I'm looking at the sun in June, I could the heat's strong, and I'll get a tan. You can still get UV rays in the winter and get burnt, but you don't feel the heat. It's like far, and it's closer. But you say that percentage doesn't matter. At noon in December, I look at the sun and it barely has any heat. Okay, but at dawn in the summer, when the sun's farther, I can feel the heat.
Yeah,
it makes no sense. Now, again, listen, you have to jump to big hurdles to say, well, it's because of the Earth and the atmosphere is holding radiant heat and stuff. But it can't be that big of a swing. Here's the thing, though: on a flat Earth, the idea of a local sun moving back and forth, that works out perfectly. We could actually test that. We could actually test it.
But this is science too. I mean, again, it's a specific heat equation. Well, it shows that land, it gives you a way to measure and quantify how land and atmosphere hold on to heat energy. And if you can, again, it makes perfect predictions. And then, by the way, I did the calculations on the 91 versus 94 million, the difference of 3 million miles in the sun's trajectory. It turns out if you actually look at it's all based on the perpendicular angle that the sun's coming in. So when it's basically taking the sine, whatever angle is coming in, you take the sine of that, and it gives you the component that's perpendicular, right? So I did the calculations, and it turned out, even being 3 million miles away, you can calculate the irradiance hitting the Earth at a certain latitude. And because the angle is closer to 90 degrees, you actually, I wish I don't have the calculations here. I did them though. You actually end up getting a lot more energy, even with it being 3 million miles away. You can do, again, because the 3 million miles compared to 93 million miles is so small compared to how you can have these sharp angular differences from the seasons. And that's the reason why it can be hotter in the northern hemisphere, even though the sun's further away. And again, I did the calculations, and it works. Wow. It's actually significantly. I mean, it's not even close. It's very easy to show that.
And any one person want to make a comment? Maybe Austin.
Mm-hmm. So basically, you're saying that when the sun's 3 million miles further away, it's warmer.
No, it's again, anybody that's in
because of the angle, the perpendicular.
Oh no, it's the angles. If you're in my friend's in the solar panel industry, and I explained this to him, he understood it right away, because solar panels, they have to find based on a certain geography, right?
Mine's not working.
Just tilt the marshmallow, Charlie.
Still not working.
No, Charlie, tilt it 23.5 degrees.
Oh yeah.
There we go.
Warning. Ball, Earth, Logic. Ball Earth logic is highly contagious. If you encounter Ball Earth logic, immediately research Flat Earth.
Ooh, ouch! Charlie, that really hurt. Charlie tilted me. And that really hurt, Charlie. And it's still hurting.
What's the best angle for the statistically the time, like how many sunny days are there that whole year, right? And they'll put the angle of the solar panel to where it gets the most of it gets best direct hit, 90 degrees. So it turns out that the irradiance, it's gonna, you got to take the sine. That's like, it basically, opposite over hypotenuse, right? And it's
You're saying when they hit the Earth or when they hit the atmosphere?
It's the perpendicular component that is really what's heating things up. And again, anybody in solar panels understands this. So when you just take a simple solar panel analogy, you can see that you can calculate the irradiance, how much less it is in the winter versus or in the summer versus the northern hemisphere summer versus that 3 million miles does lower the.
Do you know that scientists don't know how solar panels work?
Well, they might not know, but you can still read how much heat is absorbed. Energy. You can look on your meter and see how much energy is getting outputted, right? So what I'm saying is the amount of energy, it's based more on the angle than it is on the distance away. And again, you can do those
more.
Well, again, if it's for the case of the sun, yes, because you understand 3 million compared to 93 million is a small percentage.
Not really.
That doesn't matter. 3 million miles.
But it's 93 million. That's what? That's 1/30.
Now it's 93 million, Bryant. In the past, it was 1 million. Then it was, I think, 10 million, then 36 million.
Yeah, it's pretty.
And it even went past 93 million.
I know, but again,
brought it back down for you. So
I know, but with the heliocentric model, we can see that all these distances perfectly fit with the equations.
With the new model, yeah. Again, it used to be
not a new model.
Yes, Bryant. It used to be a different dimension away. It wasn't always 93 million miles.
Newton didn't even
history,
know. Newton didn't have a clue how far the sun was.
No idea.
Yeah. It's changed.
I want to see the project or science experiment that shows how they proved the sun was 93 million miles away without telling me anything about other stars.
Equations.
I'm talking about the equation.
I showed you. Well, but you won't take. Again, I can tell you that they've shown where we can put radar on.
He's not talking about now. He asked you how they came up with it.
Yeah.
Well, that's
how they came up with it because they've changed it so many times.
That's how you can measure. They haven't changed it in the past couple centuries, hardly at all. I mean, it's you go back far enough and they didn't know, but since we've been able to get the measurements of Venus.
No, meaning these scientists at that time said it is exactly 36 million miles, and then it changed to 60 something, then it goes up to 93, then it goes past, then they bring it back to 93.
And the fact that they changed Polaris by a third, maybe they're going to change the sun.
A few years ago.
Okay, I'll look at that, but I mean,
sure. Thank you for
good answer.
You'll look at it. Thanks.
Good
Can
answer.
we get to this magical gravity? You got me all excited, man.
Okay, let's.
Gravity's real. Yeah,
it's real.
Okay, so.
It's a relief.
Well, anyway, I had a little experiment that you can actually. Well, you guys don't need to do it. You can actually calculate. This is kind of cool. You can calculate the 9.8 meters per second squared.
Sweet.
With just with a piece of paper and a pencil, and you're in your smartphone.
Are you under the impression that we contend 9.8 meters per second squared?
Well, I'm just saying there's a way that you can. It's just kind of cool that you can show. And for people out there that don't know that you can measure the acceleration of gravity, it's not hard. You don't have to get a ball and a meter stick and a stopwatch.
Yeah, your phone has an accelerometer in it. Yeah.
Well, it's just you don't even need the accelerometer. You simply you can kind of look at the frames.
Well, 9.8 meters per second squared is programmed into the phone.
So you guys agree that we all agree that things fall 9.8 meters per second.
That's an agreed upon average once things go down.
Yeah.
Well, it's pretty. The gravitational fields are pretty constant across the globe. Actually,
it's agreed upon average.
But there's also atmosphere here, so it's not going to be 9.8 meters per second squared anywhere on Earth.
Oh, it can be measured.
Wait. This doesn't prove anything though. Things fall down on a flat Earth too, right?
I'm getting to that. This is just the first.
Things fall
down is down on a flat Earth, Brian. You know that, right? Down on a flat Earth, down is down. There's no one upside down in Australia right now, hanging on for dear life. All right.
Okay. Down is towards the center of the Earth.
I know heliocentrism. I grew up with it. I understand. I'm saying
heliocentrism. This is how down. It's not.
No, this is a heliocentric theory.
Yes.
Correct. Yeah. Go ahead.
It's not the theory. It's a very well proven theory of gravity that hasn't been.
It's proven theory of. Okay, what is the theory of gravity?
Okay, again, this is.
I just want to talk about gravity, man.
I thought I was going to be able to go through some slides.
Give your presentation.
Go through the sides,
and
then we'll
interrupt you. Yeah.
There you go.
Go ahead.
Maybe next time we can just talk one-on-one, because this is.
Give your presentation on gravity, man.
All right. Well. Anyway, one of the things that flat Earth believers don't seem to understand is there's a difference between laws and theories. So yes, gravity is not proven, but yet it's a law because we can use it to make predictions and to build things. In fact, I don't know if you know this, but most of the world around us is built on Newton's laws of gravity. In fact, if you look at skyscrapers and bridges, and again, at Georgia Tech, I took classes on statics and dynamics, civil engineering type of classes, and you use Newton's laws of gravity to build and make all of these things. So this is one of the problems with the flat Earth. The flat Earth doesn't really have a model that can build or make anything. I mean, if you go to school, if you're a flat Earth believer, maybe you won't do that. But if you really want to make things in the real world, you use Newton's law of gravity. I mean, it works. It just works. So the difference between a theory and a law is that laws are analytical relationships that basically are true in their given sphere. So here on Earth, with low gravity and low speeds, relativity, if you got really high gravity and really high speeds, then you got to use general relativity. But for practical purposes, we call these things laws, is because we can use them to make very accurate calculations to actually make things. The Industrial Revolution was a big part of, because of Newton's laws of motion. That we were able to build steam engines and all these structures, and so it's very pragmatic. The thing about gravity is very elegant. I mean. Basically, well, it does. It explains all of these things. Everything kind of works because
no, it doesn't.
Okay. Well, just hold on. We can.
Good. Let him finish, and then we'll respond. No problem.
I just don't see what the point is. I mean, this is.
Well, just go ahead. Maybe we're wrong. I'm open to being wrong, bro. So let me know.
But yeah, I mean, the things that you're showing us are things that we've all had to obviously research through to be flat earthers. We have not. This is not new to us. We've gone through these things. And we haven't.
Maybe he's going to teach us. So maybe
we're
wrong.
Well, I mean, but the thing is, I've done the Cavendish experiment. I know you guys.
Oh boy.
You have your reasons. I've even got a Cavendish device here.
What's a Cavendish device?
A Cavendish torsion balance. It's a torsion balance. It's a gravitational torsion balance that you're able to calculate the gravitational constant.
In your house? In your house?
Yeah, he has one. He has one right beside him.
I don't see it. Oh. I've never seen that before.
We just maybe present your argument, and then maybe I can become a believer.
Yeah, do that.
And the little G or big G, I don't know which one I'm supposed to believe in that created everything, the big G or little G, but
it's about, again, we're able to make predictions. So we use Newton's laws of gravity to make.
You got a little quiet for some reason, Brian. Just can you get back towards your mic or something? It was really quiet there, just so people can hear you.
Okay, so
there you go.
So they have the Cavendish device, the Cavendish experiment I've done myself, and it gives you. I mean, if you do it yourself, you're not going to get a very super high level of precision. You can get within 2%. But the thing is that this has been done thousands of times in labs around the world, and even if it's off by a little bit, the fact that you're getting almost exactly the same answer every time, it's very, very good proof. In fact, and it's not just the Cavendish. There's other ways that you can measure gravity. The Schehillian mountain experiment, they're able to calculate G pretty relatively accurately. This is a Von Jolly experiment. So the bottom line is we have overwhelming proof or evidence that mass attracts mass. Again, when I say a law, I mean something we can use analytically to make predictions here on Earth, is that mass attracts mass. And there's no other way. And I've seen your electrostatic stuff and density and buoyancy. This doesn't work unless you invoke heavenly energies, and we have to look at what that is. But the point is these are gravity measurements. This is now mctune.net/G.
Oh, good.
You can just see. Well, but again, you can click and look at the studies yourself. So there's just, I mean, it's overwhelming the number of times that these experiments have been confirmed. It's not just one person or even just one experiment. They've been able to confirm it in many different ways, not just by Cavendish, but by doing other things like I told you with the Schehillian experiment and Von Jolly. It's just two examples. But so there's many ways that we can show that mass attracts mass. And it's typically, the force between masses is typically, the gravitational constant m1, m2 over r squared. And we can, unless you're in a really high gravitational field, like in a black hole, or you're going near the speed of light, these equations hold very, very accurately. And again, yes, gravity hasn't been proven, but no theory is ever proven. So a theory versus a law is something that tries to explain what the law is saying. So the theory of gravity went from Newtonian's theory and then Einstein updated it to a better theory of general relativity. And the interesting thing, though, is that Newton's equations weren't proven wrong. They actually are special cases within relativity where space is really flat and time is not so fast, and the speeds aren't really super high. So you actually get Newton's equation. So the new theory didn't, it transcended, but it included Newton's equations, but just as a special case. And again, with general relativity.
Wait, can we talk about one at a time? Is that cool? Instead of like, you're saying Newtonian and then go ahead. I guess just.
I was just going to go through the gravity, then we can talk about gravity in general. Then we'll get to the flat Earth gravity thing I have set up. So
we're not going to get to rebut all your claims right now about gravity.
No, we are. No, we are.
Gravity?
No. I said let's just get through this, then we'll have a discussion, and then
Okay, fair enough.
And I know you guys have seen this stuff before. So, there's a lot of validation for relativity. And, I'm sure you guys know with LIGO, which, by the way, the long interferometer arms did have to account for curvature of the Earth. Incredibly accurately confirmed relativity to like 8 decimal places. It makes it one of the most accurate theories as far as making predictions that we've ever had, along with quantum electrodynamics. So,
and is it true about LIGO? That LIGO, the amount of the string displacement was smaller than a proton?
Yeah, well, it has to be smaller than the diameter of an atomic nucleus, actually.
Wow.
It's not a photon. It's
amazing.
No, that's incredible. Exactly, it is incredible. It's incredible precision that has to happen to detect a gravitational wave. But this chirp that took place in 2 locations. They didn't just do one location. They did it in Washington and like Louisiana. They were able to confirm the exact same gravitational pattern exactly as predicted by general relativity. And it was just an amazing.
A couple weeks ago, I read a story. A couple weeks ago, I read a story that they first faked the experiment to see if everybody would agree with it, and they did. They faked it, the LIGO, the first time. Everybody showed up at the press conference, and then they were told that it was fake, but nobody knew. Nobody knew it was faked.
Yeah, but again, that's just conjecture.
No, it's not. I just told you I could give you the article where they write about it. It's called.
Okay, an article. Well, send me the article and I'll look at it.
Isn't that weird if that's true? Isn't that weird if it's true, bro?
I'll look at it. I'll look. I will look at it. I really will.
Okay.
So, but I'm not convinced until I can see it and take a look.
But if it's true, is that not really weird? That's what I'm saying.
That's it. We're just playing what ifs right now, though.
But just to be, it's an intellectual honesty thing, right? Like hypothetically, if they lied to everyone and just to see if they would believe it, that would be kind of weird, right?
And it would be weird if it happened to be 100 years to the day that 100 years to the year that Einstein predicted them. That'd be crazy. Like, what are the chances it would be on the 100th year?
But that's just a coincidence. That's a coincidence argument. That doesn't make.
It's amazing.
Doesn't
no, I didn't. It doesn't prove anything.
It would be weird. Okay.
It's just like Stephen Hawking being born like exactly a couple hundred years after Galileo or something. It doesn't prove that he's a reincarnation of.
They said that they faked it, bro. It's weird.
Well, I'll look at the information, but I've spent the Nobel Prize by Kip Thorne. It was a really big deal, and I've looked at it doesn't seem like it was faked. Everything that I've seen looks pretty.
Obama got the Peace Prize from the same people that
I put it in the chat, by the way. It's in the chat.
I know, but again, I'm with you with Obama, but with the pure sciences, this is where I disagree with you.
The same people.
Well, we'll see. But again,
the title,
this to me is just common sense. I don't know why you guys put like upside down boats like on the I mean, that's the old
because that's what's happening in reality, right? I mean, it's what's happening is if you were to be looking from space, there is a boat sitting at the bottom of the Earth upside down. Now I know you say no, it's not upside down.
You realize that the satellite's upside down, looking at it right side up. Though you're missing. The satellites go. You do get that, right?
Yes, but one boat is antipodal to the other boat. Or
the antipodal theory was from the Middle Ages. Like I told you,
no, there's antipodes now. Things are antipode to me on the.
Brian, so when they showed us the picture of the
idea-
Earth, right, and they showed the moon in front of the Earth, Brian, think about it, right? They showed us the moon in front of the Earth. If that satellite had zoomed in on the top of the ball and then zoomed out and then zoomed in on the bottom of the ball, it would have saw stuff upside down on the bottom of the ball from its outside perspective.
Yeah, but you can't get zoomed that far.
Well, we know that, but we're saying.
but we can zoom in on
newspapers from
trillions of
satellites.
miles.
The way that gravity works is that everything is getting pulled towards the center. That is a center of mass.
We know how they tell us.
We know that.
Okay, so again. Well, let's just go to. Okay.
So we just need to buy into. I mean, the problem I have with it is like when they go up in these high.
Whoa! What's this?
Can I address some of that?
We're going to discuss. No, I'm just pulling up. We're going to discuss.
So like a parabolic
some of what you said first.
If we dropped a bunch of Skittles, why don't the Skittles get together? Why don't they come together in a 0G plane or in the ISS? How come the Skittles just go everywhere? Why don't
the Skittles are very low mass. You understand how we.
So how did the Earth start then? How did any planet or star start if low mass doesn't do it?
You understand that everything is spheres because everything is getting pulled in.
Yeah, but you just said that if something is too small of a mass, it won't attract anything. So how did they start?
That's a massive amount of energy density.
Can I address your arguments, man? You made a few fallacious arguments. So for one, you're talking about mass attracting mass.
Yeah.
Please just give me a couple minutes, please. You're talking about mass attracting mass. That's way outdated, right? That's like superseded in 1905 by special relativity, then turned into general relativity in 19. Bro, you got to give me a couple seconds, man. You said a lot of stuff that's just all provably wrong. Okay. So then you brought up Cavendish. Well, when Cavendish did it, he didn't even account for the variable of electrostatics, which is an attractive force. And so the torsion part, like the actual mass itself, whatever, he had to run away and use a telescope and barely saw it move. And even if you use something to control for that variable, you can never eliminate the variable electrostatics, right? Because all molecular and intermolecular attractive forces are electrostatic in nature, and that's an attractive force, and you're barely getting any change, and it's not consistent. So it definitely doesn't prove gravity. You're claiming it proves mass attracting mass. That's not even the claimed model anymore. That's just really, really old.
No.
Hold on, let him finish. It's his turn. Just let him go. It'll be quick. Go ahead, Austin.
Yeah, and so then the whole relativity thing, you said that it's been proved, and then you brought up like the fifth of a proton, whatever. But the theory of relativity has been debunked on the cosmological and quantum scale within your own paradigm. It isn't accurate at all whatsoever. It's never been proven. And then when you looked at the Arthur Eddington thing, like, dude, they admit that might not be actual bending and warping of space-time. So simply put, there's actually no empirical evidence that's ever verified gravity. And then when you're talking about the downward acceleration, that's an effect that we observe on the Earth. It's not exclusive to the idea that we're on a magic spinning ball in a vacuum. Things go down on a flat Earth too, bro. On a stationary flat Earth, that's just the effect. You're claiming the cause of the effect. We want to prove the cause. The fact that we engineer things based on the downward acceleration agreed upon average isn't exclusive to the Earth being a ball or gravity or something. The fact we use 9.8 meters per second squared to engineer things has nothing to do with the Earth being a ball. So those are just fundamental misrepresentations of what's actually going on. We're questioning your cause claim, bro, and mass attracting mass isn't what your cause claim is anymore, because that was debunked a long time ago, and Newton did not even propose a mechanism for gravity.
I know, but that is you hear what I said about theory, the law of gravity. I'm saying that's empirically how we can use it to make things. And then I said that general relativity was warped space-time. Yes, that superseded it. And Newton's equation wasn't proven wrong. It was proven as a special case. But
no, they're different because Newton's doesn't work.
No, they're not. Newton is basically
doesn't work on the solar system scale.
You can take relativity. No, you can take relativity and take the curvature down to close to zero, very low curvature, and you take the speeds and you reclaim Newton's equations from general relativity. Newton's equations are in general relativity.
I'm trying to help you out here, okay? So downward acceleration on the Earth is not because there's mass attracting mass. That's not what your model claims. And electrostatics is 10 to the 30. Listen, man, electrostatics is 10 to the 36th power stronger than gravity even claims to be. And then you can look at Walter Lewin from MIT explain to you that all effects observed on the Earth is from electricity or electrics or electrostatics, that nothing to do with downward acceleration or anything observed with how your body is on the Earth or anything. Is anything other than electric. This is MIT professor for 4 decades within your own paradigm, astrophysics.
No, I watched that video. No, I've got his book and I've watched that video.
So it's 10 to 36 power stronger than gravity claims to be.
But if you watch his videos on gravity, he'll tell you that everything is electrically neutral, which is why you don't see that, again, why we don't get much large scale electrical.
Right. He says that out on the planetary scale, that gravity takes over. Okay. So when you're talking about all the planes and trains and automobiles on the Earth, and we couldn't even do anything on a flat Earth because we have to use gravity. That's patently false. That isn't true. Electrostatics is way stronger than gravity. It's just a fact.
It's mostly electrically neutral, though.
No, just because things cancel out doesn't mean it doesn't have electrostatic potential, and its resting potential is 10 to the 36 power stronger than gravity claims to be. All molecular and intermolecular attractive forces are electrostatic in nature. These are all objective things.
Let's go through that, because the electrostatics, I wrote a book. I understand the Earth's energies very well. So let's just go through, and I know you guys don't believe it. I'm just saying, if gravity was true, you guys realize it'd be ridiculous. Things would all go towards the center. But I know you don't believe it. I don't. Well, this is okay. If you had a disk and gravity was real, which you guys say it's not, the center of mass is going to be right here, right?
We don't believe in gravity pulling to the center. So why don't bother showing that? That's an old Vsauce video.
My whole point is that you can't believe in gravity because it's never going to work on a flat Earth.
No, we don't believe in that fairy tale of gravity. Gravity is nothing more than incoherent dielectric acceleration. If you want to get super technical, it's not point specific. It's incoherent electrostatic acceleration.
Forget all that. That's why I jumped over. That's why I jumped over. So I just want to show why it can't be density. You don't think it's density and buoyancy. That's the thing, is you guys can't agree upon, is it electromagnetic?
We don't group think like the cult.
No, the density and buoyancy sorts everything else out.
Exactly.
Density and buoyancy depends on gravity.
No, it doesn't actually. The Archimedes principle was long before the equation with G in it. So what are you talking about? It doesn't require.
Well, so let's start with density. Okay, so if I have two pails of water here, they're both the same density, but yet one is obviously is weighing more than another. So if things fall down because of density, shouldn't these be the same height then, as far as the balance goes?
You have to determine what causes weight and what gives something density. So you seem to be missing the point. So you're reifying gravity with mass times gravity as weight.
Density is mass divided by volume. It's not how density is mass. These two have the same density. This amount of water, this has half the volume, twice the volume, twice the mass, 1/2 the mass. They have the same density.
There's a different amount of them.
It's a different amount, right? But you say things fall because of density. They don't fall because of density. So
okay, first of all, you're talking about weight, which is if you have two. You're saying if you have 2 liters of water, it pulls something down more than 1 liter of water, but water has the same density. Yeah, it makes density is part of the thing that determines it going down, right? And then how much you have is going to have a certain amount of downward pressure.
Okay, but that's mass. Yeah.
Now you're okay, cool. I just explained everything that's material is electrostatic. So what gives something mass? What gives something its density? What gives something weight? Electrostatics is what holds it together. It's not gravity. Gravity's not holding the molecules together.
So at higher air density, things weigh more. So again,
what?
So you guys deny gravity, but so at lower altitude, the air is more dense.
Okay.
And things, and objects will weigh. Okay,
a helium balloon on either low altitude or high altitude is doing the same thing. A golf ball is doing the same thing. It's density and buoyancy sorting everything else.
And we have an electric gradient. We have electric gradient on the Earth, bro. So like 100 volts per meter. So yeah, we have an electric gradient, we have a pressure gradient. That's cool. There's a bunch of reasons we have a pressure gradient, which has to be contained, but I think you're going to get to that later. So anyway, the point is that listen, man, there's electrics that sets the up and down, okay, on the flat plane Earth. And then density and buoyancy, why does it not work? Because it's provable and measurable, and yours is a fairy tale that can't be proven at all. So
first of all, again, I know the electric fields of the Earth. So we know the gravitational field, again, we can measure this, is relatively constant across the surface. You can actually measure the gravitational acceleration. You guys call it 9.8 meters per second. You call it whatever, atmospheric acceleration, whatever you want to call it. I don't know what you
incoherent dielectric acceleration.
Okay, whatever. So whatever this number is an empirical number, whatever you want to call it, can be measured across the Earth. And it's roughly, by very high precision, the same across all of Earth. Again, this is empirical, measurable. You can
welcome to flat Earth. Yeah.
Okay, right. So you don't disagree. So now the problem with electricity, and when you guys use the 100, and I wrote about this in my book, so I know the global electrics very well. So the problem is that the electric potentials across the globe. There's a really good study by Carnegie. Well, I'm just trying to show you
globe, though, bro. I mean,
no. Listen, I'm trying to show you that this is very uniform and constant. The electric field across the Earth varies wildly. It's not a constant thing like gravity. So you can't use electricity to describe 9.8 meters per second squared. It just doesn't work.
You're not understanding. You're not understanding. For one, we don't live on a globe. Okay. For two, everything's electrostatic. The air is electrostatic. So we're saying that the electric nature of the Earth creates the down and up, the objective up and down, and density and buoyancy sorts the rest out. All matter is electrostatic. So if we want to say it simply, it would be electrostatic acceleration.
I'm trying, even if this was flat, whatever. This is a uniform acceleration across. I mean, if you want to use your disk, I'm just trying to show you on your model this doesn't work.
You're wrong, though.
No, I'm not wrong. I'm trying to show you that we have empirical evidence to show that the electric fields are very wildly across the planet, because lightning strikes, you do realize that during a lightning storm, the potential, the 100 volts per meter potential goes upwards to 10 to 20,000 volts per meter.
And during a lightning strike, sometimes things go flying in the air like they're weightless for a moment.
No, they're not going to go upwards 20,000 times stronger than normal conditions.
Wait, Dave,
I had a lightning strike the corner of my house here. No kidding. I didn't levitate up in the air. The electrical potential would have had about 20,000 volts the other direction.
Jay, I should have
levitated straight up. It just doesn't make any sense.
Hey, Brian, can I ask you a very simple question?
Yeah.
Can you explain why the clouds are not being forced down to the ground by your gravity theory? I just want to hear your version of it.
Well, I mean, the clouds, I mean, it's the actual density of the atmosphere at that level. It's going to be the similar.
There's millions of tons of water in the clouds.
It's spread out very thinly, though, over large distances.
Gravity doesn't make. Gravity has a mind of its own now.
Well, gravity's keeping those clouds. I mean, gravity is
the helium balloon too. Yeah.
Well,
it's electrostatics.
The helium balloon, things are, buoyancy is dependent on gravity. The gravitational acceleration is right in the equation.
That's not the right answer.
Well, it is the right answer. I mean,
no, it's admittedly in your own paradigm electrostatics that holds clouds together.
It is, again, we're going back to this. If it was electrostatics, then there should be a uniform electric field across the Earth giving us a downward acceleration of 9.8 meters per second squared.
Okay.
That is not what we observe. We observe wild variations of the electric field across the electric circuits of the Earth.
Okay, you're misunderstanding again.
No, this proves that it can't be electrostatics.
No.
How can it be electrostatics? Is everything?
I'm trying to tell you, man. I'm trying to tell you, brother. So we have an electric gradient on the Earth. That's cool. 100 volts per meter. There's some variance. There's some variance in different places. That's not relevant though.
That sets absolutely relevant.
Man, calm down, man. Calm down. I'm gonna help you out, man. It sets the up and down. Okay, so we have positive energy increasing. We have negative at the surface. It sets the up and down. Everything that falls is electrostatic. So that means it's electrostatic acceleration, dude. You can't have density, you can't have mass, you can't have weight without electrostatics. It's just what sets the up and down. It doesn't matter if there's way more positive energy up higher, positive charge up higher. It doesn't matter.
It does matter. Listen to me. The electric field falls off exponentially faster than the gravitational 9.8 meters per second squared. On the top of Mount Everest, it's like 9.73 or something, right? The electric field
think you
get it. No, you're not getting it. The electric field, beyond 30 kilometers, there's hardly any electric field at all. So how is it that we know gravity can still pull things down beyond 30 kilometers when there's no electrostatics up there? Because gravity doesn't.
There's no electrostatics where?
No, it's very low. I've researched these charts. If you look at how the electric field drops by altitude, it drops off exponentially faster than what we know the gravitational acceleration dropped. Yes, it does.
No, I'm saying you're not understanding it doesn't matter, because what the electric nature of the Earth does is sets the up and down because there's positive energy or electricity, positive charge, which is really just charge. There's no such thing. And then there's discharge at the surface, or what they call negative charge. So it sets the up and down.
Not listening. Not listening.
Everything that exists electrostatic. We can prove this with a test. We can use a Cavendish, right? We can use not a Cavendish, which we can actually. That is electrostatic too. But we can use a Van de Graaff generator. Listen, Brian, check this out. I'm going to stop talking so much. I just want to help you out here.
That's patently wrong, though.
Van de Graaff generator. Have you heard of that?
Yes, I've used them. I used to teach physics.
Okay, can we make things float with a Van de Graaff generator?
If you electrostatically charge them, you can get them to stick. You can get a balloon to stick to a wall.
Can you make something float though?
You're talking about the aero electrostatics, the research from MIT.
Electrostatics, you can make things float. Okay, we also see it in nature. Bumblebees, beetles, spider ballooning.
No, that's something. That's the new technology for this right here.
Bumblebees aren't new technology, man.
Bumblebees have lift. They have wings that generate lift.
But their wings aren't aerodynamic. Their bodies aren't aerodynamic. They use electrostatic resonance.
They're still generating lift.
No, and spider ballooning also uses electrostatic levitation. And we can this is what science is, Bryant. What science is that we manipulate an independent variable to prove the cause of the effect. And we can do this with electrostatics and make things flow.
You can't do it with electrostatics. It varies, and we know
David's literally showing it right now. He's literally showing it.
I know, but if you take that same charge and put it against the wall, it'll stick to the wall.
Okay. So you're making my point stronger, which is that the primary causal agent of the directionality of things going up or down or to the side.
You just agreed that it would stick to the wall.
Because you increase electrostatic surface charge, what happens once it runs out? It goes back down.
No, electrostatics is called the dispersion or the van der Waals force.
Yeah. Okay? What happens when it runs out of its surface charge that you added to it? It's going to fall back down to the ground.
Gravity's always downward. It doesn't go. You can't stick a balloon to the side.
Because gravity's not real, my man. I'm sorry. It's not like you're manipulating the bending and warping of space-time.
You can rebrand it into whatever you want. I spent a year studying electrodynamics so I could do a course on PMF. Because I've done energy medicine for 25 years, right? So I'm telling you that what we know as the downward acceleration on planet Earth, it's very uniform. The electric field and electric volt is not uniform at all. It varies wildly. And the
Can I say one last closing thing, and then I'll move on because I don't want to take over the whole thing. Okay, just check me out so you can know our position. You can decide if it's true or not when you look into it. Okay, let me say one last thing. All molecular and intermolecular attractive forces are electrostatic in nature. So all matter is electrostatic, like even insulators, right? Rubber, glass, you name it. Okay, now that's an attractive force. It's attractive or repulsive. And so listen, man, everything that falls is electrostatic. You can't find any matter that isn't electrostatic. If we manipulate that variable, we can make things float. Now, we can prove that. We cannot manipulate the bending and warping of space-time. Relativity is a theory that has never been proven. It's actually been debunked on the quantum and cosmological scale. Therefore, electrostatics is the only viable option.
Okay, but
I'm done.
It's just nonsense.
It's just a fact. It's all just subjective.
No, electrostatics does not have a directionality. You can stick a balloon to a wall. Gravity's always straight down.
I told you that positive energy increases above the surface. We have an up and down set by the electric nature on the Earth. It isn't complicated.
Okay, tell me where that comes from. Tell me where that positive energy comes from.
Earth.
So let me ask you a question, Bryant. Right here, this is MIT. They have the silent drone, and it has no moving parts. Is it defying gravity, or is it defying electrostatics?
I'll tell you what it is. It's actually what's called corona discharge. So the front part of it's a wire. I've seen this technology, and I've looked at it. It's basically shooting out a stream of ions from the front thin wire to the back thicker one, okay? Corona discharge. That movement of ions is actually moving air under the wing, okay? It creates a very, very weak lift, but it will move it a little way like that. Now, they even admitted this only works in the atmosphere. You have to actually have air for this to work. What you just showed will not work at high altitudes because there's not enough air up there for the corona discharge to shoot ions from one electrode to the other. And again, I spent a lot of time looking at this. This is how it works. It's called electro-aerodynamic thrust, Dave.
All right. So we could agree to disagree on half of what we said. The question now is, let's take gravity and the atmosphere adjacent to a void. Can you explain how the atmosphere stays on the Earth?
Let's get to that. Well, and first of all, we have to look at the rotation, which we didn't get to. So I wanted to explain the high speeds and slow rotation thing. And one of the things I've seen you guys share where'd it go? I think, I'm sorry, it's loading very slow. Oh no, wait, it's not here, it's rotation. Oh, I'll just go, forget it, I'll just go here. Oh shoot, what's happened to my internet?
It's the ether messing with you, man. Do you know that you can't fly north to south on the Great Meridian circle routes? You would have the Earth spin underneath you like thousands of kilometers over a 5-hour flight.
Okay, well, we can I can explain that too.
Okay.
Okay, so first of all, we have to understand the atmosphere. It's not a hard division. So you got this very slow gradient. It's a gradient that tapers off very slowly, and like I said, this is the Kármán line, right? The Kármán line is 100 kilometers above the surface, and it basically is like a thin bubble around the Earth. The atmosphere is not some big thick thing like I've seen.
Thick or thin? Go ahead.
Paper thin, right? So these speeds, I did the calculation. So you can actually calculate that with the atmosphere rotating with the Earth, that you end up with only like a 12-mile-an-hour difference between the surface and this altitude based on the whole radius. So these numbers are just way off. I mean, whoever shared this is just. So
forget all those numbers. We have an atmosphere sitting on the Earth adjacent to a void of no pressure.
So it's not, well, first of all, when you take this gradient, all right, you're going very slowly from a high pressure
to no pressure. I got it. And it goes until there's nothing left.
So
and now you're
like,
in
so
what's holding it down?
Gravity.
Okay. So here's a question for you, an experiment. I'm in a room and I have a shoebox and I suck all the air out of the room, an open shoebox. I suck all the air out of the room from underneath. So now I'm in a vacuum. Is the air in the shoebox going to stay in the shoebox? Is gravity going to hold it in the shoebox?
Yeah, but in that situation, you've got all the atmosphere pushing down on you.
No. I suck all of the air out of the room. So the room is now a vacuum, it's space. It has no air. The only difference from space is the room has a container. But that shoebox of air, according to you, the gravity should hold the air in the shoebox. Because if that doesn't work, if you say it wouldn't do that, then your entire gradient argument is off the table.
No, we're talking about a 6 sextillion ton Earth. It's a huge mass pulling. So that's a lot of mass pulling the atmosphere that's very paper thin, like you agreed on.
So it's holding the air down, but I can pull the air up and away with a straw.
No, you're not. What you're doing is you're sucking out the air, and it's the atmosphere pushing down from gravity that's pushing the water up. This is how the straws work. You're creating a partial vacuum in the straw. I used to teach this, Dave. I mean, this is what it is. What happens is, here's
But Dave, ask him again because I didn't understand his answer for this shoebox.
You understand that atmospheric pressure is 14 pounds, 14.7 pounds.
Yes.
Square inch.
Yeah.
We
all know that.
This is a 15-pound weight. So this amount of atmosphere, it's a huge. Try this experiment.
Mm-hmm.
Hold up a 15-pound weight. Okay. Every square inch is 15 pounds of pressure. So when you create a partial vacuum in that straw, there's 1 atmosphere or 14.7 pounds per square inch pushing the water down and up.
What about my shoebox?
I don't understand the shoebox.
So why doesn't water come out of the straw when you just put a straw and a glass in?
Because there's no partial vacuum. The air is still there. You got to actually suck the air out to get
that's what he's saying.
Push down.
So, and I guess the shoebox is the wrong example. Let's say
it's not hard. It's not hard to understand.
Hold on. Let's say that there's a box that is sealed. It's got air in it. Okay, we suck the rest of the air out of the room so that there's just the box there with the air in it. When we slide the top off the box, will the air then stay at the bottom of the box because of gravity?
I don't know what you're trying to say. Gravity.
Why don't you just listen for a second? Listen. If you're in a room,
I am listening.
Okay, then answer the question. If you're in a room and and we suck all the air out, but there's only a box in the middle of the room that has air in it, and then we remove the top of that box, where's that air going to be? Is it going to stick to the earth, or is it going to?
How does that relate to the?
I'm asking you a question. Doesn't matter how it relates. I'm just asking you. I want to know
because you said that the gravity holds the air onto the earth, and the air gets thinner and thinner and thinner. Okay, so we removed all of the air out of the room, so there's no pressure from the atmosphere pushing down on this box. We open up the box. Gravity holds the air in there or not.
Yeah, but do we still have gravity or not?
Yes.
Trying to
we have gravity.
On your Earth. Your gravity. Yes, on your Earth.
But have you actually done that experiment to get down to a zero vacuum?
Yeah, people have done that. People have put a chamber inside of a vacuum chamber. It's not that hard to do it.
Okay,
yes. But here's the thing, Brian.
A little bit.
If the answer is the air would not come out of the box, then the entire pressure gradient next to a void is off the table.
No.
And here's the other thing: there's nowhere in science, nature, or anywhere that you can have high pressure next to low pressure without a container. Nowhere, anywhere.
What do you mean
ever?
high pressure next to low pressure?
Any higher pressure next to lower pressure or no pressure in any orientation. It doesn't matter.
Listen, do you have a little app that can measure the pressure in your house, the atmospheric pressure?
I don't.
You can
why would you not answer his question?
No, listen, I'm answering his question. You can literally measure the pressure at one altitude and go up and higher and see that it drops at altitude.
Okay, but he asked you what would happen to the pressure in the box.
Next to higher pressure. That is lower pressure next to higher pressure. You can measure that provably.
What would happen with the pressure in the box?
The kinetic theory of gases says that gases are going out fast. So, but when you have the sheer scale of the Earth and the gravity well of planet Earth, they're not going to go outside of the gravity well. They might in that room scatter around because gases do that. That's the kinetic theory of gases.
But what's different about it? It's the same gravity
on the surface
of
the
Earth.
Earth.
Yeah, it's the same gravity is pulling.
Yeah.
I know, but you're not looking at the whole. Those gas molecules aren't going to escape out into space. They might. Gravity is actually pulling on them. But you have to look at, like, again, you have to do the calculations. You got to say, okay, here's what the kinetic theory of gases says, and gravity is going to pull down. And there's going to be some energy that may be moving them around, but gravity is still there pulling them down. But
isn't gravity stronger at the surface, though?
But there's other forces than just gravity. You guys realize that, right?
I'm just asking like a simple question. Isn't gravity strongest at the surface? Or technically at the center of mass, right? So the surface.
But it's a very slow. It goes off very slowly, though. You see. So that small gradient, it's not a very fair experiment because you've got to get on a larger scale to see a big difference in the gravitational field.
Do you not see his point though? Like if we take gas and it's in a vacuum on the surface where the gravity is the strongest, it goes in all directions.
I know, but
so how would it stop it next to a vacuum where gravity's weaker?
The gravitational field of the reason that's because you see less gas up there, right? So that's the reason why there's more pressure at sea level because it does have less.
That's a non sequitur to the question, though.
It isn't. This is why you're getting close to a vacuum at 100 kilometers up. It's almost a vacuum.
Yeah, you're repeating the same thing.
So this gradient is because of gravity. That's why the gravitational field decreases with altitude. That's why less and less you get.
That's a begging the question fallacy.
Well, what are you trying to? I don't understand what you're trying to.
We're saying it. Listen. If we have gas pressure in a container on the surface and it's next to a vacuum, once we open that box, it's going to fill the vacuum violently, right? It's immediately going to seek equilibrium. Second law of thermodynamics. Second law of thermodynamics. The gas is going to fill the vacuum because high pressure goes to low pressure, right?
Kind of like this railroad tank truck, how it just implodes like this.
Has nothing to do with what we're talking about, but
yeah. Why can't you just hear me out and answer?
Just listen to Austin.
I'm just trying to understand what you're saying.
So listen to Austin. Just listen to him. He's going to explain something. Just listen and take it in.
Yeah. So like if we have a container of gas on the surface of the Earth, and then we have a vacuum chamber, and we open the gas next to a vacuum chamber, that gas from the container, once we open the lid, it's going to fill the vacuum violently, right? It's going to immediately seek equilibrium and fill that vacuum, fill the available space. And that's on the surface where gravity is the strongest.
I know, but the gravitational field is still acting on all those particles, but there's other things going on. Again, the gases they have a lot of motion and energy. So
that's what we're saying. Yeah.
Actually, I know the reason, because at the surface of the Earth, the temperature actually makes gases move faster. So that's the problem. When you have something like a gas, you've got a higher temperature. That's where they're going to move around. So gravity's still pulling on them, but there's other factors at play there besides just gravity.
Vacuum chambers are actually not very warm, bro. So even on the surface level, when we have a vacuum chamber where it's not warm, the gas is still going to immediately fill the vacuum. The point is that it's filling the vacuum, and if it's at the
isolated experiment, if you want to send me the experiment, fine.
You can do it a million times, man. Do you not see the intrinsic contradictory nature of what you're saying?
Did you see the contradictoriness of what you're saying?
You're using one little isolated thing.
It's not an isolated thing. We're trying to explain to you that gravity isn't sufficient to hold down gas when it's adjacent to a vacuum.
Gases have kinetic energy, and they're moving around.
That's what we're saying.
I know, right, but I'm saying when you've got a large scale of a huge 6 sextillion ton Earth, that creates this gradient of different pressures, So yes, you've got a lot of movement going on at every. Nobody doubts we have storm systems. I mean, we've got all kinds of stuff going on. But as a whole, the gravity is keeping everything.
But it's not. It doesn't keep it down on the surface where it's the strongest. And the strongest vacuum we can replicate is like 10 to the -6 torr, right? They claim space is 10 to the -17 torr. So that's where gravity is the weakest. It's next to a much different pressure differential.
But vacuums aren't sucking things out. I mean,
no one said that. Gas fills the space. Vacuums don't suck. That's another non sequitur.
The gravitational field is what's keeping everything in place. That's why.
So why doesn't it keep that air in that box in place?
Okay, so well, again, I haven't done that experiment.
Okay, but you don't even need to do the experiment. Just think about it and let's pretend.
Yeah, use your mind and
let's pretend.
I'm using my mind, but you're using a little tiny room.
Okay, no, hold on.
Instead of like entire huge, a huge. I mean.
So you're saying that the little tiny room gas or the little tiny room vacuum is stronger than the vacuum of space?
I'm saying that gravity is pulling down on those gas molecules, but they also have a kinetic energy, and there's a lot going on there that you're just.
So why doesn't the kinetic energy of our atmosphere go off into fill the void of space?
It actually does. We lose atmosphere every day.
And who told you that? And where? How did you measure this? This is just a theory. This is just a theory.
I've actually heard Dave Murphy saying this. Is it some kind of like you're losing atmosphere? I'm like, yeah, you're right, Dave. We are. But we got about 150 million years based on this calculation of atmosphere still left.
A theory.
We can. One of your own flat Earth people has brought this up at a debate.
Okay. Why you're appealing to? Yeah, they're talking about how your model has a theory.
I'm saying that we do lose atmosphere every day, and it's actually a lot. But it's compared to how much atmosphere there is, it's a small amount.
That's what we're saying. That doesn't make sense. That's not how the second law works.
I know, but it's.
Why does some escape and not all?
It's because again, it's a little. Gravity's holding it. It's a statistical thing. You got a little bit of gas at the fringes.
Statistical? Is it like rolling? Like gravity's out here shooting dice, bro?
No.
Like
you just have because there's a lot less up there. There's not that much that's going to come out. But yeah, because the pressures are so low, there is going to be some of this that will escape out. But it's.
But then the stuff lower down is being held by the gravity, right?
Percentage, yeah, to what's left. So.
Okay. Yeah.
This debunks the model, bro.
It doesn't debunk the model.
It does. It's physically impossible. It's contradictory to natural law.
It's not though. I mean,
it literally is.
Gravity works just perfect to keep you can't have a pressure gradient.
But we just explained. We just gave it a thought experiment that shows that gravity doesn't.
Really? Do it. You think electrostatics?
Electric gradient on the Earth. Yeah.
Austin, what was the difference again?
The electric gradient falls off a lot faster than gravity does. It doesn't work.
How much stronger, Austin? I want to hear it again. How much stronger is the electrical?
I know.
10 to the 36 power stronger than gravity even claims to be.
It's also electrically, because it's so strong, it attracts like that. Everything's neutral because of that.
That's such a non sequitur. The electric force on the Earth. I just now quoted MIT 4-decade-long professor Walter Lewin telling you that all observations we see on the Earth are electric, and the only time gravity begins to account for anything is out in space on the planetary scale.
Well, you have electrical phenomena on the Earth, but for the most things that we deal with in everyday life, everything's electrically neutral for the most part.
But it all has electrostatic potential, and it's all electric, and the air's electric, and everything's electric.
But the point is that the 9.8 meters.
Not gravity, bro.
9.8 meters per second squared is uniform. We can measure this uniform across the planet.
Yeah.
The electric field varies wildly. There's no way that can account for the 9.8 meters per second drop. Not only that, the electric field becomes basically zero at about 30 or 40 kilometers up. Again, measurably so.
What?
Yes.
It goes up 100 volts per meter. It gets stronger as you go.
No, it doesn't.
Where did you come up with it gets weaker?
It gets weaker.
What are you talking about?
The electric field at 100 volts per meter, as you go up in altitude, that drops off.
Mm-mm.
When you get to like the ionosphere where it becomes highly... look it up.
The ionosphere?
No, I'm saying there's a highly conductive realms within the atmosphere that then the electric field gets blocked. The electric field drops.
How high is that?
It's pretty high up, but it's not out into space where gravity still works.
Gravity's not real, man. So the point is
there's no electric fields up there. What's pulling things towards the Earth? I mean,
No, okay. We said it's up and down. We've explained it, but I got a question. Would you like to admit you misspoke when you claimed that all this stuff to do with trains and cars and stuff has to have gravity exist? When I just now quoted from your own paradigm, MIT professor, right?
I watched Waterloo.
You said you watched it, but you keep denying what he said.
No, I don't. I'm not denying electromagnetism. I'm just saying that when you actually build structures like bridges and buildings, you always use Newton's laws of motion and gravitation.
Cool story. It's just nothing to do with downward acceleration. That's all it is. Coulomb's law is the same thing, except you replace your little fairy tale of gravity with a charge. You have a constant velocity and the same thing.
The known values of the electric field vary wildly across the planet, where we know the gravitational.
That's a non sequitur, bro.
It's not.
You don't understand it then.
It debunks the electrostatic model, is what it does.
No, it doesn't. All molecule. Do you agree that all matter is electrostatic?
You just agreed that the uniform acceleration across the surface of the Earth is uniform, and I just showed you that you can easily find out that it's not.
Do you agree that all matter is electrostatic?
All matter is electrostatic?
Yeah.
Why would you say the word electrostatic?
All matter that exists is electrostatic.
I would not put it that way.
Can you name one thing that isn't?
When you say electrostatic, I mean, electrostatics, it deals with just, I used to teach this, right? It's Coulomb's law, where you're dealing with just pure charges without magnetism. So when we study electrostatics, we're not using magnetism at that point. We're just looking at Coulomb's law without a magnetic field. So no, it's not all electrostatic, because there is magnetism, there is mass, and there is other forces.
Can you name one piece of matter that's not electrostatic?
What do you
one
mean?
type of matter?
That's not how you define matter, electrostatic.
Can you name one type of matter that's not electrostatic?
That doesn't make any sense.
All molecular and intermolecular attractive forces are electrostatic in nature. All matter is electrostatic.
Matter has, again, it's got, that matter it has mass, charge, spin. So there is charge in there. Yes, I'm not denying that there is not a charge on elementary particles.
In all matter.
But there's also mass, and there's also spin, and there's also other things. It's not.
Yeah, you get charge to mass ratio. You're always looking at charge, and that's what holds the matter together. And that means everything that falls down to the Earth is electrostatic.
No, it's not. You can't.
Oh my gosh.
Show me a model. Okay, with your electrostatic theory, I'll give you a challenge. Show me how you can calculate 9.8 meters per second down. Give me an equation where I can use your electrostatic model to verify that things fall at 9.8 meters, because with Newton's laws, I can do that.
Okay, we can use the same exact equation. We just have to properly define mass. Gravity is nothing more than downward acceleration. Little g is downward acceleration.
That's just rebranding gravity. You're just
wait, listen, buddy. You don't understand that little g is just downward acceleration. It isn't a cause claim. Newton literally said that anyone that claims mass attracting mass to the vastness of a vacuum on innate brute matter without some medium acting between it is incompetent beyond belief.
Whatever it is, I mean, yes, I agree. We have a law of gravitation that gives us powerful tools to make calculations, to build things. But the theory
based on downward acceleration, so it doesn't mean
it's a constant across the surface, and it decreases very, very predictably with altitude, based on the 1/r² drop off of gravity. That does not happen with the electric field. It provably does not happen.
Provably all matter is electrostatic, and so you have incoherent electrostatic acceleration.
No, if you're trying to give a model that talks about electrostatics being the downward reason that things fall down, I'm telling you that the electrostatic field of the Earth does not match the 9.8 meter drop. It just doesn't. It drops off very quickly, and it becomes
so you don't understand. It's not that electrostatics is pulling stuff off in a vacuum down to the Earth. That's not how it works. It just sets the up and down. I don't want to take over the whole thing and make it real realistic.
But again, around a lightning storm, I had a
not listening.
Lightning strike hit my house. That's a 30,000, like a 20 to 30,000 volt reversal. So why didn't I go up into the clouds?
Because your house is grounded. It went into the ground. That's why.
Yeah, it had to be really strong. You'd probably die.
I know, but if you stand near, if you're in a lightning storm with that kind of potential, you don't start levitating up.
We can levitate things with electrostatics.
You're telling me that people are levitating all the time around lightning storms?
People have gotten hit by lightning and go flying in the air. All sorts of stuff happens.
I know.
All right, so hang on. I know you have a bunch of other things you want to get into. We're gonna come up on 3 hours. So would you like to, let's agree that we don't agree and let's go on to something else.
You guys got to rework your electrostatics model because it doesn't work. It just doesn't.
We disagree. We disagree.
Agree to disagree.
So you're telling me that your little balloon experiment, Dave, where you have it go to the ground and you can stick it to the wall, gravity doesn't get stuck to. I don't.
Because gravity is a fake force.
I know, but
yes.
if I take this lead ball, a little piece of wood, this is more dense than that. It should stick to the lead.
No.
It goes down. But
no one thinks that. Why are you saying that? No one thinks that.
I understand, but electrostatics, you can stick a balloon to the, or if your little experiment, you can also put that near a wall and it will stick.
Why doesn't gravity pull it down?
Yeah.
What do you mean, why doesn't gravity?
Why doesn't gravity pull it down if gravity's real?
If there's because there's other forces at play.
Because electrostatic is
So
way stronger.
There's all sorts of electrostatic forces that we can lift things off the ground with. We haven't been able to do it with gravity because we can't figure out what gravity is. Let's move on.
Because when it falls, it's still electrostatic and never goes away. So agree to disagree.
You know what a free body diagram is? You got to draw all the forces acting on the body. So with the balloon on the wall, there's going to be an electrostatic attraction from the van der Waals dispersion force. There's going to be a downward force of gravity. Okay, so you got to get the resultant force to see what's going to happen. In that case, the resultant force is stronger from dispersion or the van der Waals than it is from gravity. Okay, because you're adding charges by rubbing the balloon on your sweater. You're transferring charge. Okay. I'm saying in general, when we're not doing these things to create charge, you're not going to get electrostatics to create the downward 9.8 meters.
Even when it falls, it's electrostatic after it loses its charge and comes off the wall. So just agree to disagree, bro.
I know, but I wanted to say one more thing because if you're going to
get the final word. Go ahead, Bryant.
If you're going to use electrostatics, you've got to use Maxwell's equations to actually calculate 9.8 meters per second or Coulomb's law. If you can do that, then I'll believe electrostatics is real. But you got to have some equation besides.
I believe it's real.
You're basically just taking the gravitational equation and saying that that's electrostatics.
All right.
You really are.
He said you have the final word.
Yeah, that was the final word. Agree to disagree. Do you want to? You want to do? You were talking about you could show a horizon drop, and you don't like the.
I don't want to do that.
You don't want to do that one?
Well, because the perspective stuff, we're just gonna get.
Oh yeah, I was really hoping for some proof of curvature. I mean, I've been looking for 7 years.
You had an image that on your sheet that was quite interesting, of a lake or something where you could see below it, you could see the drop. I think this image right here. This image right here.
Which one?
Can you see my screen?
Yeah. Oh yeah. I did the calculations on that, right?
So you did the calculation. I have to ask you a question. Where's the horizon? Is it right here?
The horizon is below eye level. It's a little.
Is it? But is this the horizon here?
The horizon. Well, that's the apparent horizon.
But this is this the horizon you're measuring, saying that it's below eye level?
Right, because eye level it's a drop, and again, you got to look at the calculations because the geometric drop. What he did.
But where are you putting the?
I'm asking you a question. Is this the horizon?
Where did you calculate it from?
Horizon.
Is this the dropped horizon that you're talking about right here?
Well, let me see what you.
Jeran, am I big so you can see?
You're small.
Oh, can you make me big, please?
It's not really my job, but all right.
But in your paper, I was looking, and I think you were talking about this being the dropped horizon.
Yeah, so you're looking right. So
is this the horizon?
Yeah, so you're looking down, right? So that would be
all right.
The
so
horizon.
That's not the horizon. This is the horizon. Okay,
that's
this is
eye level. That's
no.
Yeah,
this is eye level horizon. Exactly. If you can see, everything is mirrored here, right? So this is an apparent horizon, but this is mirroring. Now, if there was no land here, if there was just ocean there, you would think that this was the curve of the Earth, but it's not. It's just mirrored. And now this is just an image, but if we actually look and we see. This is a boat going beyond that horizon where there's no land past it. So let me just fast forward here a little bit. This boat is floating in the air because your horizon's right here.
Well, let's look at some of my boats now, Dave.
But first I'm showing you the image that you showed us is where you thought the horizon was, where all your calculations were done, is not. This is the actual horizon, not this. And by the way, having land or something in the background, it's super easy to see. Having nothing in the background makes it an argument that we can never win.
Right.
Okay, because you'll be like, no, that's not, but I'm showing you on this other image on this video, this boat is going far over that. It's floating, but you see the horizon here. If these trees weren't here, this boat would be flying in the air.
That's
okay.
Not too close, though. That's way too close.
It doesn't matter. The farther it goes out, the worse it gets. And by the way, if you see the horizon here, if let's say the boat went another 50 miles out there, it would just get harder and harder to see, and it would mirror the sky, and you would think that this is a physical horizon. This is an optical horizon. The real horizon's out here.
Send me that video and I'll look at it. I can't see it here.
Okay.
It looks
well,
like
you have my app. Go to Boats Over the Horizon. There's 100 of these videos.
Okay, let's look at some of my boats over the horizon.
All right. Beautiful.
Bring on the waves.
Small,
what do we got?
Okay, can you see my? Okay.
Yeah.
I see a big wave in the foreground, but go ahead.
It's not a big wave.
Oh, it's not. Okay, go ahead.
You think that's a wave? That's the bulge of the Earth. So how? I mean, this is the.
You can't just say it.
Well, this is the problem: is you guys will take boats that are not over the horizon, and then you can bring them back with the zoom. But if they actually go over the horizon, like this one with critical things.
So, do you think that any boat can be seen to go over the horizon with just your naked eye?
No, you got to.
I asked a question. Can you see boats?
What does it matter if an optical?
Because it matters because they tell us that that's the way that they figured out that the Earth was round hundreds of years ago, which is ridiculous because they would have never seen any boat go over the actual horizon. They would have seen it disappear from their eyesight. If they would have had a zoom camera, they would have pulled it back.
Bottom up every time. I mean, it disappears from the bottom up.
Just like your sun does, right? So here's a building, okay, where the bottom few floors are missing. But if you look, these balconies, which are all the same, are getting compressed. And hang on, there's waves here in the foreground. This horizon, this apparent horizon, is dozens of miles closer than this. And these little waves, again, it's the same way the sun sets. It's being blocked. My finger can't hide my face if it was a wave, but if my finger was closer, I can set behind it. It disappears behind it.
But little waves can't explain this. So
yes, a millimeter above your eye level can knock out an entire
Dave,
city skyline.
Where's your Lego?
100%.
Where's your Lego video?
This is not from.
I don't know where it is.
Oh, that was a good Lego video.
No, I'm just showing that when you zoom, when this is zoomed out, when you zoom it in, it doesn't matter if you can take the original screenshot and just zoom that original. It still gives you the same. So you're not able to bring this back from a zoom. Because when you take that image and just zoom in the actual image of the distance, it's still the same as if you actually zoomed in with the camera. And that is very much over the horizon. Those are not.
Well, but see, that's what you don't understand. That horizon that you're seeing is called the wavefront edge. It's a horizon that is way closer to you than those objects.
Okay,
and
well,
hold on.
The maximum distance is like 3 miles, right? Of the waves.
If this was a boat, right, and this is the wavefront edge, which makes it look like it's at your eye level. This boat is just going to go beyond it, and it's just going to disappear behind it, right?
From the bottom up.
From the bottom up.
Correct.
And that's just perspective.
Okay, it's not. But show me a paper.
Okay, it's not.
Well, no, show me a.
He's
show
throwing
me
it's not.
Show what do you want to say? Go ahead.
No, show me what you're talking about, the wavefront occlusion or whatever it is.
So again,
so
in the app, just watch the Boats Over the Horizon. It explains it for you.
Brian, if you can only see the edge of the edge of the sphere is 3 miles away, right?
Showing you.
It's not. You're showing me tricks. I mean, all these things.
They're not tricks.
I'm showing you tricks.
They're 3 miles away would be the furthest you could see the edge of the Earth, right? The curvature of the Earth. So if there's waves there, what?
This is a huge boat. Little waves are not going to include it. This is a big steamliner.
Oh boy!
It's going to hide the whole thing. That steamliner is going to get smaller and smaller and smaller until its angular size is too small for you to see. That wavefront edge is going to block it for miles in front of it.
Okay, you see what I'm doing right here, right? This is getting off in the distance where your angular resolution can't see it very well. And we're taking this original image and blowing it up, and it's still the same as if we actually zoomed in. It's no different. So it's both cases. It's over. You can't bring back a ship.
What kind of camera was this? Can I ask what kind of camera was this? What kind of zoom? What kind of zoom optics were you looking at here?
This is probably a P900. I mean, I didn't do it, but I mean.
Okay. So obviously you've seen one P900 still image that you're fixed on.
No,
Have
it's
you seen
not
the wait. Let me finish.
Many,
Have you seen the thousands and thousands of others that bring the boat back into view?
Right.
Have you? No,
know
yes
what
or
that
no?
is?
Have you seen them?
I've seen a lot of them, and I'll tell you what it is. It's boats.
Why are you picking on one, Bryant? Why are you
Listen,
picking on one? What
it's
about the
boats-
thousands that bring it back?
And
It's
Brian, the
boats-
ones that when you can't see the boat, it's always a
hell is-
rough, windy, wavy day.
No,
It's
those
always
boats
a
that
rough,
are
windy,
coming
wavy.
back- Those boats that are coming back are not over the horizon. They're small boats that are near the edge of the horizon. But when you actually get a boat that's over the horizon, you can't bring it back. But yes, you can bring
That's
back.
because it's behind a wave that you cannot get behind. You can't see through
That's
it.
not a wave. That's the curve of the
Absolutely
earth.
is
That's exactly how
wave.
perspective works.
It's, I showed you with my flat Earth sunset and my kitchen sunset. That's exactly the same on
That's
the
a
water.
homemade experiment. It doesn't prove anything. But
Science experiment doesn't prove anything, but your memes that you found on Google does.
no, these memes are based on science that has peer-reviewed studies where you have independent labs validating the stuff you guys are.
So what kind of science have you done, Bryant, with boats over the horizon? Can we see what you have done? Because we've done freaking tons of stuff. Can I see what you have done?
When you say science, it's nothing but
No.
just sheer
A
images.
science experiment, I said. Have you done one with boats over the horizon? And if you have, which it sounds like you have many, I mean, you're bringing it up. Can we see it?
Dave, can I show the Legos?
I'm just
Yeah, you have it, Andy?
Yeah, I have it.
Okay.
I mean,
Let's
unless
just move
all
on
these-
then. No, it's okay.
unless
Let's
all
just move
these
on then.
videos I see are lies. I mean,
let's just
I
move on
can't
then.
imagine that they're making up all these boats over the horizon.
Jaren's going to show. Hold on.
Well,
Give
give me
us
one
a
second.
moment.
It's going to take a second for me to get it.
Oh, Brett, he's pulling it up. But again, when we look at large boats, when they disappear, some of the times, when they disappear, they don't always disappear like that. It's because there's waves in the foreground, and those waves, just like those waves.
Here's my biggest problem.
Will block an entire city skyline. See, these are big waves out here, right? And this boat is going to disappear behind them, right? There's all sorts of optical effects going out here, and it's never the same. It changes every day.
Yeah, I live in California, so I go out to the beach sometimes, Brian.
I'm sorry, guys. That's the curve you're seeing.
Well,
right
I'm sorry that's not, because I've been out there, and here's the problem I have with it. Because you know what? Eventually, the boat does appear to go over an edge. Eventually, it looks like that. I've been out to the beach and looked at it. Right. But the problem I have is, why do they continue telling people that the reason they knew the earth was curved is because they saw boats go out and go over the edge? Because that is not true. Because when I go out to the beach with my plain eyes, I see boats disappear, and I can always bring them back with a zoom in camera. Now, eventually, you're right. Yes, but listen, eventually the boat go. What do you mean? You don't think with your eyes, you think you can see a boat go over the curve?
I'm not saying that. I'm saying you can't always bring these boats that are well over.
Right, because
no, you're not listening to what I said.
You're
not listening to what I said.
Jaron finish.
It's not what I
Jaron
said.
finish what he's saying, bro.
I said.
Front edge doesn't make sense.
I said that with my eyes.
Let him finish.
With my eyes, I always see the boat look like it disappears. Then I pull out the camera and I can pull it back. So if that's true, then there's no way that Aristotle or Ptolemy or any of these guys saw boats go over the edge and then knew that the earth was curved, because that's impossible. They couldn't have seen boats go over.
Well, but there were some pretty big boats, though, right? I mean,
Bryant, this is the wavefront edge right here. I don't have the video. I wish I did. But the entire deck of where these fishermen are, you can't even see it because it's behind this wavefront edge. When I zoom out, hold on. When I zoom out, all of this water beyond the boat becomes unseeable, and the boat is missing from half down, and it's behind the wavefront edge. Now, we know this isn't curvature because we can see water back here. Right. Okay, this is the wave. Hold on, this is the wavefront edge right here. Zoom out. This is going to look like a horizon right here. This boat's going to look like it's behind it. Hold on. If that boat was out here, way out here, it would be totally gone, right? You wouldn't be able to see it. And big boats, the same thing. A big boat in the distance will get as small as a small boat closer. It doesn't matter. And the farther out you go, the worse it gets, because that wavefront edge doesn't keep moving away from you. It stays close.
Do you have a paper that goes over wavefront edges?
You have to have a paper, Dave. You have to have paper.
No, just anything. But I mean, this does nothing to back it up.
No, we don't.
The government doesn't back it.
We don't.
No, I just want to see something.
We don't write papers. We go out and make observations.
Brian, do you understand?
Just because there's a small wave in front of a small boat doesn't mean that a wavefront edge.
Okay, Dave, which one do you want me to show?
Brian,
this one?
you'd rather see a paper.
Anyone you
Brian,
want, Jeran.
This one.
You'd rather see a paper, Bryant, than an actual experiment done, or go do it yourself. You'd rather see a paper.
How you're proof that a wavefront edge can include a
watch
huge
this.
boat?
Watch this. Watch this.
Wait, I don't see that. I don't. You're not sharing, Jeran.
Yeah, I am. It's on the screen.
Is it?
It's
oh, okay. Yeah. There you go. It's not.
The yellow brick in the distance.
So it's just showing you that all these bricks are falling behind this blue brick here.
You break.
What?
You were breaking up for a second.
Oh. Those are all very level, but just because the way you look,
It can be a mile away.
you can see this blue block covers all the white bottom pieces
I
of
can't
the.
really see it. I mean, if
Okay,
send me
well,
the
I mean-
video, I'll look at it.
All right.
Can you make it
I'm
bigger?
not sure that's the case, but
Well, just I'll look at it. Just send it to me. I'll take a look at it.
okay. And then here's another one.
There you
There
go.
you go.
I've seen some of these videos. Yeah.
So there's your wavefront edge. Those blue bricks they're covering up 5 or 6 layers of higher
I know, but
levels.
But the camera is.
No, you can still see the table. You can still see the table. I'm above the table.
But you know that sometimes the actual lenses, when you put a bigger zoom.
But my eye sees it. My eye sees it the same way. My point is those blue, the blue line there, that's the wavefront edge right there. I can't see any of the counter beyond it because the wave is blocking it. Okay, and then as those Legos get smaller into the distance, they disappear behind the blue Lego wavefront edge.
Days where the water is calm, Dave, and when the water is calm, there's no wavefront edge to block these boats.
You're right, and you can see them much farther. However, there's the what is it? What does Karen call it? The there's the thickest part of the atmosphere, the thickest moist is right above the water, and it becomes opaque.
Mm-hmm.
It'll mirage the boat out.
Well,
opacity.
Yeah,
depending on pressure and temperature.
The non-uniform.
Yeah, but always it would be the
transition
case,
zone,
right?
something
It
like
always happen.
You can get but the effects can vary wildly.
Sure,
depending on
but it always happens.
You understand? We're saying that the horizon is just an apparent horizon that fluctuates based on atmos, but the globe claims it's a physical place. But we know it's not a physical place. Just there's water and you can't see forever, and it changes drastically throughout the day. That's our position.
But maybe I forgot to put this slide in. It's not it's nobody says it's a physical place. The horizon is just where the eye. Again.
So, are you saying on a ball there's not a physical horizon?
Well, it's based on a circle around a sphere around you, and you looking
but
at a certain point that sphere cuts off the rest of the globe. So you see.
Brian, do you know where the word horizon comes from, Brian?
Appears to be a horizon.
Do you know what the word?
Brian, you'll have to share again. If you want to share again, I think it took you off.
Brian, look here. This is Skunk Bay. This is Skunk Bay, right? And Glober would say, okay, well, those houses are hidden. But then as we move throughout the day, we can see the beach. The buildings disappear. This is all just apparent horizon. Okay. Yeah. This is just showing you how it looks different all the time.
Yeah, but there's a lot of mirage going on there. I see all kinds of.
Yeah, there's a lot of things going on.
There would always be mirage. There would always be mirage.
That's our point.
Way out in the distance.
The thing, I don't think any scientist would say the horizon's a physical thing.
You're claiming that the Earth is blocking.
You just said the Earth is blocking buildings.
You're saying
is blocking buildings.
But the big boats are going over the curve. That's a physical horizon.
What's blocking it?
But again, it's where your eyes are. If you're higher up, then yes. If you're this is why you got to use the curvature calculators, because then you can. So if you're at about 6 feet, then your eye level is going to be different than if you're up 100 feet. So yes, but the curve that is kind of where things disappear over the tangent of that point on the sphere. You can't see beyond that.
We can't. Well, show them Canada. Show them all the places we can see.
But that tangent will vary as you go up in elevation or down.
What about like
it varies at the same height?
Brian, there's this mountain, Mount Canigou, that is 175 miles away, and from 1,000 feet up, you can see it when it should be about a mile below the curve. Is that
what's his name? Who is in the beyond the?
Here it is, right here. It's right here. It's right here. As the sun moves away, appears to go down, all of a sudden it backlights the mountain and you can see it. And it's not a mirage, right? Your only excuse is that the mountain and the sun are already over a physical curve and they're refracting up perfectly to stop at eye level.
Wait, I don't. This is going below the horizon. I'm not sure.
So that mountain right there is called Mount Canigou.
blocked.
It's 9,000 feet high, but from 1,000 feet, if you use your curve calculator, you'll see it should be 16,000 feet or something below.
The top of this mountain should be over half a mile below the curve, but it's not. It's right there. But people on a normal day will look out and go, look, you can't see it because it's below the horizon. Now you would claim this is your physical horizon, but the light that's bouncing off of Mount Canigou doesn't have the power to push back all the way to your eyes because the atmosphere blocks it. However, the sun is much brighter than the reflected light coming off the mountain. And as the sun moves beyond it, it does have the power to push back 175 miles. And all of a sudden you can see the mountain. Now, there's two answers for what this means. It means the earth is flat or the earth is 1,000 times bigger than they're telling us.
Yeah, but is that what's his name? Media. What's the guy that did
Jay Tolan Media.
Jay Tolan Media. Yeah, he's been soundly by the science guy. I mean, I watched some.
No, he hasn't. No, he hasn't.
You say the science guys, you mean like Fight the Tight Shirt and Simon Dan.
Bob the science.
Oh, Bob the science guy.
Bob the science guy, the pedophile or whatever.
Well, whatever. I mean, I've read through it, and it's very convincing.
Allegedly.
Allegedly, yes.
Yeah, but Bryant, here's the problem with like peer review. You're explaining the problem with peer review. Peer review is a problem because you're saying anything that comes from Bob the science guy, oh, it's so soundly put together. Hold on, but
you're saying the same thing. You're saying one person doing this is a proof. It's
no, we're saying thousands of people have seen this observation. It happens twice a year.
Okay, but if I use it in my debunk curvature calculator, I'm positive I could find the reason why.
Let's do it. Let's do it.
Do it then. Let's do it right now.
Let's do it right now.
Do it right now. Let's do it right now.
Let's
go. I
go.
don't want to do it now because you guys.
Oh, come on.
You just said you'd be able to figure it out.
Listen, I'm not there, so again. They've debunked that Jay Tolan Media guy because he doesn't report.
Oh yeah, because you're right. Because
you don't have the right numbers.
Because as soon as we started to see too far, they added refraction.
I know, but if you're fudging the numbers like he's been
nobody's fudging the numbers.
What? You're gonna get different.
I always err to the side of the globe.
I got a whole
always
scrolling page on Jay Tolan Media how he basically misrepresents.
Well, of course they're going to say that. Otherwise, Bob the science guy's out of a job.
Dave or Psyop Man Dan.
Neither of them. I mean, it's a long page.
Fight the fat shirt.
It's definitely like Bob the science guy or Wolfie or whatever their names are.
Yeah, but they do very careful and like
no, they don't do very careful.
Known liars. They're down on anything.
Very careful psychological
and they all hold the same thing. They all believe all of the same nonsense.
I caught you guys in so many lies too.
What lies? Name one.
Name one lie.
Name one lie.
You can't say that without naming one.
I'm not saying you specifically.
You just said you guys. I've caught you guys.
I'm saying flat Earth community.
Okay, well I can't.
We don't know the whole flat Earth community, you know. So you're talking.
I'll put an end to that right now, guys. Flat Earth, knock it off. Stop lying. All right, there.
You stop lying.
I put an end to it.
We don't lie.
I'm talking about these images right here. I'm showing on the screen.
What images?
You have to share your screen.
You have to share your screen again.
Oh.
I'm gonna get Dave off here. He's scaring me.
I'd scare myself.
Don't look at me.
Mount Canigou scary.
Mount Canigou is scary.
That's the specular reflection impossible on a globe, by the way.
Okay. Well, no, actually, that's just basically a reflection on a shiny surface.
Yeah.
You got a shiny
it can't be convex or concave. You can't get a specular reflection that way.
I know, but you will agree that this I can show you the original footage from this video, and then the thing is bobbing up and down.
I was talking about your wallpaper.
What?
Your wallpaper debunks the globe. You can't have specular reflections on a body of water with any convexity or concavity. It has to be flat. So.
Oh, the specular reflection. I did a whole video on that. That's actually you can disprove that with like a little. It's because you got to not use a shiny surface. If you got like a rough piece of aluminum foil over a basketball, you can see the shine. The light comes all the way to your eyes. Where if you have just a shiny surface, then you get what looks like a hot spot.
No. I'm saying on your wallpaper. Okay, like if you have a body of water and you have mountains and you can see the mountains in the water with a perfect specular reflection, that's impossible if the water is concave or convex at all. Like it has to be flat.
I don't think that's anything.
Okay, well,
that's a fact, but it's all right.
It's a fact. Go check it out. Go get a reflective piece of plastic or a mirror thing and bend it a little bit, and it changes. It doesn't.
Do the same.
You haven't done this because then you would agree with us.
No,
Ryan.
I've seen.
What are you talking about? You haven't done that.
That it's not a flat surface. If you get that same experiment with like a basketball and put like aluminum foil, it's got ripples in it, like the the water, you will see the light come all the way to your eyes. It doesn't just stop at a spot.
Do you want to bet money right now that you can get a specular
you.
reflection on a curved body of water?
Hold on, let me just bring up my video. I can see.
Please.
I think we need to remember though, we are standing on the shoulders of giants like Bob the Science Guy and McToon.
Oh,
Bob the Science. I'm just saying, debunking some of those. I've gone through them, and it's pretty clear that like Mount Shasta.
Yeah, it's crazy. That's the CIA is crushing, bro. The CIA is really good.
It was even shown to be not even Mount Shasta. You guys are saying.
I hope
aren't these same guys pushing another agenda? Just saying.
Yeah, for sure. And so Dave's quick with it. You see Dave's picture, right? You understand what we're talking about? I was just letting you know that you might want to change your wallpaper. It debunks the globe. I was just trying to help you out.
It doesn't debunk the globe.
All right, bro.
Let me see.
You see how pretty that picture is Dave has? That's a perfect specular reflection, man. That water can't be bending, or you wouldn't get that perfect reflection, like that mirror effect.
So, I mean, are you talking about like this here? Hold on.
Hello, this is Bryant Meyers.
Your channel name is Debunking Flat Earth.
No. I'm talking about. Is this what you mean by just seeing like on one spot here versus like?
Well, that is a local reflection, which is interesting, but just a specular reflection of a reflective mirrored image. So that's not quite what that is. But yeah, I mean, even the local reflection is interesting. I don't see.
So what is your answer on the picture on the right there?
Yeah, how's that work?
I'm just saying you can get like a little ball and put like the. I mean, the point is that water's not perfectly. You see that it comes through like this.
What?
Well, the point is that it wouldn't be a local reflection like that if it was 93 million miles away.
It's just light. It doesn't matter how far. Light is light coming in at that angle.
It would be 90 degrees spread across the whole sky.
No, it's coming in from this is your angle of vision. You're looking right at it. So it doesn't just hit a spot and not come all the way to your eyes because the water surface is not, it's got some texture to it. So when you add some texture, you can get the light to come all the way and not just to.
Okay, we're talking about specular reflections, and that's interesting in my opinion. I think that's a local reflection, which is impossible if the sun's 93 million miles away. But that's a different thing. Specular reflection's a mirrored reflection. And I was just not even trying to debate about it. I was just letting you know your wallpaper debunked the globe. So I don't know what you were about to bring up.
I don't see that at all. But.
All right, well. Oh well, specular reflection. Well, dude, you can come hang out with us though, man. Flat Earth is way cooler, bro.
It'll take. We don't expect you to change your teams tonight. It'll take you a month or two, and then you'll have a couple of restless. No, never, because I know because it would call into.
Well, listen, electrostatic theory. I know electrostatics very well. I know electrodynamics very well, and it doesn't work to describe 9.8 meters per second squared. It absolutely
So you've spent literally zero time on it, and you say it doesn't work?
Oh, I'm saying that you can provably show the electric field falls off a lot faster than 9.8 should be falling off.
So you're not understanding it yet, but maybe we can talk again later.
It's not we're not saying it pulls things through the earth. We're not saying it pulls anything to the earth.
Show me.
Yeah, we're not saying it pulls things.
You know why you want a model so bad, Bryant? The reason you want a model so bad is because you were handed one as a little kid and you hold on to it. Where's your model?
Something that can make.
Why do you need a model? We're giving you facts and science here and experiments. And you're like, where's your model?
Jaron, read Jaron, read the George Ellis quote.
You've got nothing that makes a prediction anywhere.
George Ellis or Hubble?
Only NASA could do that.
You mean the one that says
we're going to see Canada
can't predict anything
miles away if the Earth's flat? That's my prediction.
You guys think that you don't need a model to make actual predictions to be science? You think you can just make stuff up and it be?
No one's making anything
we're
up.
not
Observations and common sense.
Look, here's what we thought. We thought that when
scientific method.
Don't you understand? But hold on, Brian.
Hold on, let Jeran talk.
Brian, don't you know that if it was a deception, that look at what a great job they did by convincing you guys all that we have a model and everything works perfect, then anybody else who comes along down the road who says, I think that maybe it's wrong, you're going to, well, where's your model? How does everything in the universe work? Well, I don't know. I'm just saying that these things are wrong. Well, if you don't have everything known, if you don't know everything, then you can't be right. That's what your position.
The electrostatic theory is provably wrong.
You aren't even understanding what it means. We don't.
I understand electrostatics very
Okay, time
well.
out. Do you think that we think that electrostatics is pulling things to the ground?
It's density, buoyancy plus electrostatics somehow.
Yeah, something sets the down, but then
right.
Density and buoyancy works out.
You keep straw manning us like we're saying it's pulling it down, but we're not saying that. We're saying it sets the up and down. There is an up and down set with the electric gradient on Earth.
I can put a balloon on my wall. It doesn't set any up and down. That's
Brian, listen, okay. Hear me out, okay? If you take the balloon and rub it on your head, right? It'll stick to the wall. Eventually, it'll fall back down. When the balloon falls down, you're claiming it's because gravity pulls it to the Earth. The problem is that balloon that falls to the Earth, it's still electrostatic. It didn't all of a sudden stop being electrostatic.
It lost its charge. Electrostatic means it has a surplus of charge. It's probably neutral by the time it hits the ground. Now you're trying to say at the atomic level there's electrons. Well, guess what? Those electrons are tied up in chemical bonds, and overall the object is electrically neutral.
It still has potential. It still has potential, and I'm not claiming electrons.
It provably doesn't have potential. It provably doesn't.
It doesn't have electrostatic potential.
When it's neutral, no. I mean, if I rub it on my head, it's going to. No. Yes.
Oh, so it does have potential.
When you transfer electrons from, you know what that means? You transfer.
I know electrons is pseudoscience, but yeah, I understand it. See, okay, if you believe in particle physics, you believe that electrostatics is.
Physics. This is just simple. I mean, this is like 18th century.
Oh, yeah.
You believe that it's virtual photons? Okay, I'm just saying that they claim in quantum mechanics and virtual particle physics.
It doesn't matter if it's photons.
Dude, I'm just trying to let you know, man. Okay, everything's intrinsically electrostatic. It's actually dielectric field. There's only charge and discharge. That's electrical field theory. It was thrown out because they said the Earth was a spinning ball. That's a whole bunch of stuff. You have to open your mind to hear the truth, man. I can't.
We can measure.
I can't do it for you, man.
Measure what?
You can go up to the top of Mount Everest and measure how long it takes your ball to hit the ground. Calculate 9.8 or 9.7.
But you've never done that. You're just going to say everybody else. Yeah.
And that was predicted before Newton. That was predicted before Newton.
It's the inverse square law from gravity. The electric
was predicted before Newton.
The electric field of the Earth drops off a lot quicker than that. It can't
I'm going to cite it for you in the chat that was predicted and explained before Newton on a flat Earth model. On a flat Earth, it was explained why you would get downward acceleration consistently long before Newton.
So just so you. It wasn't on a flat Earth. No, it wasn't.
Yes, it was. I'll show you the model.
I'm telling you that they use you guys like to quote that NASA study of non-rotating flat sphere Earth by what's his name?
It's not a NASA study. It's what NASA claims they test their stuff over as this non-rotating Earth. What do you mean? It's in all their documents. You're saying that they don't say that?
They have it in, I'll tell you what it is. They have that in quotes because it's an approximation.
No, they don't have that in quotes.
Yes,
you are literally lying to your audience.
Whatever it is, it's an approximation.
Stop lying. We don't lie to you, so don't lie, Bryant.
I'm not lying.
Don't lie, Bryant. That's all. Please don't lie. It's not in quotes, Bryant.
I've seen it.
It's not in quotes. It's multiple documents. NASA, the military. Why are they saying this?
The military has ballistics manuals that talk about the Coriolis.
Dude, I have a ballistic missile right here I can drop in the chat that says that it's a flat, non-rotating surface. A ballistic missile's document.
Documentation. You love your documents so much. Might as well show them a few.
And if it's a deception, we shouldn't be surprised if they throw it in some manuals, but nobody ever uses it.
The Earth rotates so slowly.
Maybe we can talk to him about that. Can we talk to him about that? You think the Earth is spinning?
Non-rotating.
Okay, let's talk about this.
Not slow rotating.
Can I show you at the edge?
You said earlier that the air is connected to the Earth. Coriolis claims the opposite, right? Coriolis claims that you have to have an accelerative and an inertial frame, inertial systems, and then that you see a difference, right? So then how is it that you're now claiming a singular system where the air moves in lockstep with the Earth at the same time as it being disconnected from?
You can talk about relative velocity. There's nothing wrong with that. But the thing is, the atmosphere and the Earth do move together overall. Now, again, we're looking at the overall large scale. I'm not talking about local storm systems that are going. I'm talking about at the global level, the atmosphere is moving with the rotating Earth.
Because it has to.
No, but Coriolis claims the opposite of that. It claims that there's an inertial and accelerative system, right? And that's how you get Coriolis effects.
The Coriolis force it's actually imparted by the rotating Earth. So when you go north from the equator, you shoot a ballistics north, it's going to get deflected to the right because the initial velocity has it's got a higher velocity at the equator.
So why doesn't the air do that? Why doesn't the air do that?
That's what we're saying. So why isn't the air? It's saying it's detached with the air. That's the whole point.
No, it's not. The air, it's like it's all moving together, but it's that the air is a little faster up there than it is when you fire it away.
How does the air outrun the spin of the Earth at 40,000 feet?
You're using that again. I already showed you that diagram that the atmosphere doesn't go.
No, it's outrunning ground speed by 150 miles an hour or more.
Yeah, you go north.
So the Earth is spinning to the east.
But where do you get that number? Where do you get that number? I done the calculation.
There's wind charts that show it, and they admit it. FAA uses it, but it's outrunning
which means it probably is faster
the spin
than
of the Earth.
That's not true. The spin of the Earth I did the calculations. When you actually look at how
you did the
Hold on a second.
calculations
Hold on a
based
second.
on your
Hold on.
your
You said
globe.
that
you can do the calculations based on the fact that
what's the
Hold
number?
on.
atmosphere.
You said
What's
the
the number
atmosphere
then?
is spinning with
The
the Earth.
number
If
is
it's
only 12 miles an hour faster at the Kármán line than it is at the
That's
surface.
not what he's
Okay,
asking
now
you. That's
what's
not what
the
he's saying.
mechanism?
So
What's the
there is a
mechanism that
little
makes it
bit-
go
So-
faster? What's
But
the
it's
mechanism
12
that makes it
miles
go
an
faster?
hour.
Gravity is the gravitational column is holding it. Wits it. Come on.
That doesn't
But-
work. Gravity doesn't
I'll
work.
tell you why. Because at that level, there's very little particles. You got to.
So
at that
here's the
level, there
question I
hardly
have.
Anything up
You said it's spinning and the higher it's only 12 miles an hour faster. Great. How come that molecule that's at the Kármán line that's going 12 miles an hour faster in the spin just to keep up with it? How come it's going an additional 100 to 150 miles an hour faster than that, outrunning the spin of the Earth?
Well, that doesn't make sense.
No, you're right. It doesn't make sense because the Earth isn't spinning. The Earth is flat.
The jet streams. The jet streams. How do the planes?
Can you pull up the
Hold on.
jet stream?
But ask him. Okay, listen. Hold on, Bryant. Bryant, you just said earlier. Bryant, you said earlier that planes go faster one direction than the other. Why is that? Why do they go faster one direction than the other?
That was based on wind currents. You know.
Okay, so hold on. That's what he's saying. That the wind currents that blow to the east.
Listen, I know that there's I'm not talking about local weather. I'm talking about the global atmosphere as a whole.
Okay, but there's winds inside the global atmosphere that are moving faster than the Earth spins.
Right here. Here it is. These are these white and pink ones. I think are 150, 200 miles an hour, and they're outrunning the spin of the Earth. They're going east. Can you see?
It doesn't. Yeah, but where do those forces come from? You guys don't.
What do you mean? Where do the forces come from?
It doesn't matter.
We need a model. We need a model.
Shifting over to a
That's a flat Earth, though, model.
Where's your model?
That's flat Earth.
I thought you said there is no flat Earth model.
You're right. This is a flat Earth model, but on the globe, they're heading east, right?
Yes.
It's the same thing. They're heading east. They're outrunning the spin of the Earth. You have no explanation for that.
We're just showing you a real version.
Yeah, we're showing you reality where it actually
is.
You guys don't
going in perfect circles.
Okay, hold on. I just want to say you said that we spin very. You said we spin very slowly.
Okay, let's go over this.
I just want to show you. This is what 1,000 miles is going to. I mean, 1,000 miles per hour looks like.
Okay, let's talk about that.
Hold on. Okay, so just saying that it spins slowly. Well, this is 50 miles per hour, and then I'm going to multiply it by. Okay, hold on. Here's 1,000 mile per hour edge velocity. Tell me how the atmosphere. Wait till it gets. Hold on, you're not even listening.
Not listening. I'm not listening.
When it goes 1,000 miles per hour, you're saying.
I know this.
You know what?
You've never seen this.
You know what? What do you know?
Something he's never seen. He already knows, Jeran.
Okay, I guess so. So here it goes.
He
Now
already
this is
knows.
1,000 miles
It's all
per
right,
hour.
man. Just chill,
look at,
bro. We're
look
gonna
at,
be your friend.
Brian,
Like,
look
you
at.
can hang out with us.
Look
We
at
can
that.
take it, bro.
That's the edge velocity.
I understand. Okay, but let me just talk about why those speeds are not what you guys think they are.
What do you mean? 1,000 miles per hour is 1,000 miles per hour. That's the edge velocity.
No, it's not. Rotation is measured in radians per second.
Of course it is. But you can. But can you not figure out the edge velocity?
Let me ask you this: is your engine measured in miles per? No, it's RPMs. That's revolutions per minute.
Okay, so we can do. You can. So
let's just go through this. So Dave loves to pull this helical model of the universe or of the solar system up. But do you know, Dave, that this is 1,000,000 times faster than the real thing?
Yes, it's a.
This is not anywhere near.
It's a visualization to show the different vectors.
That's what happens.
It's misleading though because it's going way too fast.
Doesn't matter.
That doesn't matter.
It actually doesn't matter a lot.
Well, it's misleading because it's actually not going 1,000 miles per hour. It's only a little tiny representation. So the actual thing is way worse.
Let's just go through. So first of all,
you know, and when you point this out, though, when you point this out, it actually disproves
that
it.
The Earth doesn't. You guys love to say the Earth spins at 1,040 miles.
Because it does.
No.
We don't love to say that. That's what they taught us.
No,
Yes.
it doesn't. It spins at 0.006.
What is the circumference of the Earth?
What's the difference in that and 1,037 miles per hour at the equator?
It's because it has to do with forces. You know, inertial.
It sounds smarter.
It doesn't sound smarter.
It makes it sound less significant.
Yes.
Listen,
Brian, if you were on a merry-go-round that's 20, that's the size of the Earth, the width, the equator, and you're sitting at the outside horse, it's going 1,000 miles an hour, and it's going off of your trajectory at a mile a minute, okay, or more.
It's not the same thing.
It's the exact same thing.
It is
How
not
fast
exactly
is that? A
the same.
train, Bryant? How fast is that train going?
This train is going 200 or 300 kilometers an hour.
And what would happen if it slowed down or sped up or turned?
Well, then
and what
it's
if you
gonna-
took the roof off of it?
Then you're actually getting an acceleration. See, I'm talking about
Brian, but this isn't a curved trajectory.
But the Earth is spinning.
What are you
It's
talking?
not.
What
It's
are you-
never going in a straight line.
What kind of science experiment is this, bro?
No,
This is not replication of anything.
No, listen, I've done the
What are you
math
doing?
on the actual forces. Okay, so when you actually, so the Earth is rotating twice as slow as the hour hand on your clock. Okay, it's a very slow rotation. When
No,
you actually
no,
do
no,
it-
no.
Well, yes, it is.
What is going on? We just pointed out to you that you had a constant
I've
speed
seen
on a
those-
straight path. That's not synonymous with moving in a circle. That's
we're-
acceleration.
In a
It's
curved trajectory.
rim
Where's the curved
velocity.
That's
It's
where's the
rim
curved
trajectory?
velocity.
With the train.
Tangential speed. Okay.
Listen, you're bringing up all the points from these known
All that-
liars.
Yeah,
Right?
he's
This whole thing,
I can-
twice the speed.
you
It's
can
not
tell
twice.
me- Can I
Listen,
just talk about
listen.
this?
Hold on.
Or-
Let me say
I
one
wanna
thing, and then you can
explain
go
to you
on.
what
I'm
you
gonna
feel.
say one thing. It's angular velocity, and here's a simple experiment
Yes.
you can do if you want to do an experiment.
not
Go
angular
outside.
velocity.
I'm going to
It's
tell
not
you it's
angular
angular.
velocity.
He doesn't
No, it's
like
not.
experiments. He
Listen,
likes memes.
Here's an experiment, and I encourage everyone to do it. Get a string, tie it onto a
Angular
weight,
velocity, Dave.
right? And start spinning it around. Start spinning around and let out line and get it to the point where it may be 20 feet of line out there. And you'll see that it'll be pulling out. It won't touch the ground. And you just spin around and you'll be going around at a good pace. And then get another, then get another string that's only a foot long and hold it right with your hand. That string, that one will barely go out, right? It's going around at the same angular speed, right? But its rim velocity is so slow that it doesn't even swing out. The other one is pulling my arms as I spin around. Okay,
Hey,
but
right,
the one,
but-
but the one right here that's hanging, it just hangs. It doesn't even.
Hey, but-
it barely swings out.
let me
That's
just-
rim
let me-
velocity.
Let me just explain to you, but we don't feel velocity, Dave. We feel force. Let me just explain this to you. So we actually have a very slow angle. This is our angular velocity. This is angular velocity, not this, guys. This is angular velocity. Angular velocity is radians per second, not miles per hour. So when you actually calculate the actual centrifugal force, you end up with 0.03 centrifugal acceleration, and this is a very small force.
But Brian, you're just reciting numbers and beliefs. Go outside and spin.
Brian, what is
listen, let me finish. Spin a rock on a string. The farther out it goes, the harder it pulls at the same rate. Okay, the farther out it goes, and so why should I believe that if I double the distance, it's making a huge circle now? Why would it pull less? It pulls more and more and more and more.
Brian,
Okay, you can calculate all you want, but you can in real life, the farther out it goes, the faster its rim speed is, and the more power it has.
On a rotating system, but I'm telling you.
Yeah, well, you're living on a rotating system, and it's a curved trajectory.
You're going by the tangential speed, Dave.
Yeah.
The tangential speed, we don't feel.
You accelerate.
Yes, we do. Curving is acceleration.
No, and I'm showing you the actual forces of acceleration.
Okay, let me ask you though, the equations that you're using. Hold on, centripetal and centrifugal. Can you tell me the equations for each one?
Yeah, it's omega squared r. So
they're
when you take,
but
when
what
you
about
take
the other
the
one?
angular-
But what about the other one?
What do you mean? What other one?
I said centripetal and centrifugal. What is the equation for each?
Well, they're just in opposite directions.
Oh, so the equations are equal. They're the same equation.
Equal and opposite.
Same equation.
Do you have proof the Earth is spinning? Can I get some proof?
Because that seems weird that the two equations are the same. So the equation for being thrown out from a circle and throwing in from a circle are both the same?
It's just like outward force.
No,
what's
the angular velocity is this angular speed that a rotating body is going, and it's measured in radians per second, not miles per hour. The tangential.
Okay,
speed,
so let's drop miles per hour.
We don't feel constant speed. Just that's why.
But wait, hold on a second. You're going in a straight line at 1,000 miles an hour, 100 miles an hour. It doesn't make a difference. You're not going to feel it. Your quarter will balance. Your water will sit. Hang on. But if you take the slightest turn, now the Earth is curving. At no point are you going in a straight line. You are curving. That is acceleration. Okay.
You want to see how fast the Earth is rotating? Look.
No. I know how fast it's going. 1,024 miles per hour. I'm not. Hold on.
0.0694 RPMs, Dave. That's how angular speed is measured.
But no, it's again. Get the rope with the rock on it, and you feel it.
We don't feel the tangential speed. We feel the acceleration.
How about this? I disagree to disagree with you.
Yeah, and also you always feel acceleration. Any rotation is always accelerating, and we have an elliptical orbit. We would feel the big of it. But dude, here's the question. Brian, here's a question, man.
What if we're in a plane
spinning? I asked you that because I know for a fact everything you're about to bring up is not going to prove the Earth is spinning.
Okay. Well, what about this then?
So you want to skip your whole first page? You agree? You got
nothing. Because you already got your arguments for the ring laser gyroscope. Because Bob has brought up so many.
No. But hey, I want to tell you something. Let me tell you something. So according to Einstein in relativity, okay, if the sky was moving around the Earth, you would experience centrifugal and Coriolis effects with the Earth as the rest absolute frame of reference because of a thing called the Machian principle. And Einstein himself integrated this into relativity for the Arthur Eddington experiment where they saw the eclipse with the star behind it. And he wrote a letter to him explaining that would be the case. So according to relativity, which is your current theory for gravity, you just talked about how it was so awesome earlier, remember? Yeah. None of that stuff you just showed on your page would prove that the Earth is spinning. According to relativity, it could be that the sky is moving around the Earth. No, it is true. I have no letter right here.
Let's go through which one of them it is. So let's see. There's Aries theorem.
Aries failure, which showed that the Earth is stationary.
So which
showed that the Earth is stationary. Sagnac effect shows that the Earth is stationary.
It's called Aries failure for a reason.
Yeah, it's a failure on the science's point to prove what they wanted to prove. That's why it's a failure.
Do you understand
the opposite every experiment?
You guys are trying to say that the ether is still a thing.
It is. What do you mean? Yeah, even quantum mechanics says it is. By the way.
You've put so much of your beliefs in other men. It's so scary.
Yeah, quantum mechanics is saying quantum fluid.
Brian, life is so much better when you know
fluctuations are not ether. If you want to call quantum fluctuations ether, you're just rebranding quantum fluctuations.
What's quantum fluid, Bryant?
What, like superfluids?
What's quantum fluid? No, not like superfluids. No. So you don't know. Okay. What is dark matter?
I admitted earlier that dark matter and dark energy, we don't, just because we don't have answers to everything.
It's ether, buddy. Dude, everything they're talking about is
show me a paper that proves
Why does it have to be a paper?
Why a paper?
Brian, do you understand?
Go look outside, Brian.
Show anything that proves
Brian, I'll give you 5 quantum physicists saying we have to reintroduce the ether. 5 of them. Yeah, like I have them right here, PDFs.
They
5 of them.
Don't have very much published research. That's
because that's what dictates.
This is hidden
that's
information.
What dictates.
Brian.
I know, Brian. This is why they have peer review. This is why there's peer review. Peer review protects your guys' science from ever being questioned by anybody else. That's why. No, that's why. Because guess what?
You can validate something
Sorry, no. Scientists don't. No scientist ever wants their theories told that they're wrong.
Otherwise, it's just one person making a claim, and then there's no validation.
Well, let's talk about Michelson-Morley. Okay, do you know what happened? Okay, so they had a prediction with the Earth moving through the ether. So they shot the interferometry. They got 1/6 of what was predicted, less than 1/6 of the orbital motion around the sun assumed, right, of 30 kilometers a second. So they had an option, which 2 options, which either throw out the ether or throw out that the Earth was rotating, revolving. Wait. I'm almost done. I don't want to take up a lot of time. I'm just trying to do fast. Okay. So then they went and did the Michelson-Gale-Pearson, where they also used interferometry to look at the rotation, right? And it matched the predictions within 98% of the sidereal rotation. Every time it can be done 1 million times. It works every time. What that proves is that the interferometry does detect the motion if it's there. It's detecting the motion of the Earth. I mean, the sky around the Earth. Right, in the sidereal rotation, and it does not detect an orbital motion
at all.
Those 2 combined debunk the fact that the Earth is spinning, and so it's just been hidden. And the Sagnac effect is what's used for gyroscopes, and Sagnac said it was a vortex in the ether. So there you go.
What Austin said.
I know what Sagnac said.
Bex.
But they found they discovered the effect after that. So he was wrong when he said what he initially said.
Well, you're just saying that, but are you going to address the Michelson-Morley combined with the Michelson-Gale-Pearson?
The Michelson-Morley experiment there was a allowed tolerance for error, and that was within the allowed tolerance.
So what do you mean?
No,
so they still didn't detect it?
That it didn't detect the motion of the orbit, but using the same methodology, it detects the sidereal rotation within 98% accuracy.
They got 1,200 miles per hour.
Which means that it does detect the motion of the sky around the Earth.
Send you what? It's the Michelson-Morley experiment. Go look at it. Pull the papers.
Yeah, it's
a paper. You love it. It's actually a paper.
I mean, the thing is, though, if you're
I'll
looking
look
for a
at it
paper
again.
to be,
I'll take a look at
imagine,
it again.
Brian, imagine that you
That's a
started to
good answer. Good answer.
imagine
Brian.
you started
I'll
to
take
agree
it.
with us and you wrote a paper and you turned it into a publication. Do you think they would publish that paper, or do you think that they would trash your name until you weren't able to show your face again? Which one do you think's true? Because you're telling us we need to go submit a paper.
The latter.
That's just conspiratorial.
Oh boy.
What? Are you
Good
thinking
luck,
if I
dude.
posted
Good
a
luck.
paper saying the Earth's flat and the ether exists, that
Wow.
they're going to peer review it and be like, prop this guy up for a Nobel Prize?
And it means
You think
everybody
that's
that
what
you're
happens?
giving that paper to is all going to be signing away their entire research, their entire careers is garbage. Yeah, they'll just sign right off. Oh yeah, let's publish this.
That's
That'll
not
happen.
a conspiracy
But
theory. That's a fact.
But just the stuff that you say with the electric field, I mean, I know that that's wrong. The
You
forces
still don't
that-
get it, though.
You just don't get it.
I
You
do
know it's
get
wrong
it.
because you don't get it.
I do get it. You guys don't understand Maxwell's equations at all. You just don't.
Oh my
What do you
gosh!
think,
Now you're
bro?
bringing up Maxwell's
Bro.
equations.
Right.
That's what defines electrostatics, my friend. I mean,
Brian, is there
killing me, bro.
any other
Next
topics
topic,
you want to
Brian. Yeah,
any
next
more you want to
topic.
cover? Because
Wait,
Can we do
I-
Antarctica before we go? Can we please do
Yeah.
Antarctica?
You just
Please.
brought-
Wait,
Brian.
can we talk about the
I can't.
how about
I
the
can't-
equinox? The equinox
Wait.
and the 90 degrees. Let's talk about that so we can at least get that out of the way.
Well, it's just going to be. You already have your answer, even though I don't.
Well, because
we
the
have our
answer's-
answer
the
because
answer's
we've been
important.
studying this
I
forever.
know, well, you come up with. Really
No, there's no coming.
clever-
Let me
No one
explain this
came
to me.
up with it.
We're going to show you.
Let me show
stuff
you something.
and stuff that you've never seen, and
'Cause
then
you-
maybe you can think.
Just
have
try
new
not
ideas.
to say no before.
Yeah,
it's
just
over.
listen for a
Yeah.
second and just follow me and see why this is. So you're saying that at night at the equinox.
Yeah, wait, hold on, Jared. Put
Oh,
it on the big screen. So
It is on the
he
big
can
screen.
unshare. Oh, is it? Is it?
I don't
Oh,
know
there
if
you are. All right, never mind. Sorry, my bad.
Okay. So north and south, if somebody is north of you and are you south of them? Yes, right?
Okay, yeah.
What about east and west? Are they the same as north and south? So if somebody's east of me, I'm west of them?
Okay, yeah.
Okay, so what if I showed you that that's not the case at all? If we took somebody who's north and south, yes. If we draw this guy and we go south at 180 degrees right there, then if we drew this line back up, let me save this, and we drew this line back up, now it's going to be exactly north. Okay, this guy is going to be exactly at 0 degrees, right? Okay, great.
So what he's showing is the guy at south is south of the guy north, and the guy north is north of the guy south.
But
just like you would expect.
East-west, if I were to draw a line and say, okay, I'm here in California, and I'm going to go 90 degrees east over here
You
to the east
can't use a
coast.
straight line there. That's a great circle. You're using a straight line.
No, I'm not. I'm using
We're using Google. We're
Google Earth
going
draws it.
exactly 90 degrees east.
That is a great circle. Okay, so 90 degrees.
Yeah.
See that? So I'm going to hit save on that one. We've got 90 degrees. So now, is this guy going to be 270 to this guy? Because when I draw from here and I go 270, 270 is down here. Okay, so what that tells you is that north and south are consistent. You're always north and south, but east and west vary, right? So now if you start drawing lines, let me save this. Okay, so
I'm just not following all what you're trying to do.
I know,
Right,
because
they didn't
it's
teach
not
you
what
this.
you believe.
It's not what they taught
it's not
you.
about what I
Watch
believe.
again. The guy. What he's saying is the guy. If somebody is 90 degrees east of somebody, the other guy is not 270 degrees west.
Right.
It's completely different because the globe is not real.
Yeah, you're watching it. You're seeing it on a false
I know,
model.
but-
We're
look at-
showing it. Their model doesn't work.
I know, but I can't just. I don't know. It
So here's
looks
the
like
thing. This
I
guy,
don't
if,
see.
if this
Show
guy's
him
looking
again.
east,
Just listen. Watch again. Jaron's good at explaining this.
well, if this guy's looking east, 90 degrees east is here. Okay, move out of the way, box. 92, 90.
90 degrees east. I don't know what.
90 degrees is dead east.
Yes. See how it
Okay,
says
but
90?
90. Okay, it's just east.
So when you're looking
East.
east, yes,
Okay.
90 degrees is east.
So I'm going to save that one. So now you'll kind of notice something weird as we keep drawing lines of everybody looking 90 degrees. They're all looking at the equator. 90 degrees here is here. Nope, 91, 90. Okay. So now if I keep going with these lines and I go down to the south, every line I draw is going to be pointing at the equator. So if we spin the globe this way, and now we look at what everybody's doing, when it's the equinox, everybody is looking at the equator. So it shouldn't be a shock that we see the sun rise in the east for everybody, because east is everybody's looking the exact same to the exact same point, the equator.
When the sun is
You
at the
guys think-
center,
You guys think
east is all directions.
I just drew it for you.
The
He's
sun-
literally
the
showing
sun-
it to you.
I'm showing you.
Okay, but that's not.
Yeah, because you think east is this way.
Listen. You send it to me and I'll play with it. And I'll
No,
see
you
what's
can
wrong.
do it on Google Earth
It's
yourself.
your own
Tell me
Google
this,
Earth.
Brian.
You have
Brian.
Google Earth.
We're not doing any tricks, bro.
Brian, if I'm up here in California and I start walking east, can I walk in a straight line? And
Let me just look. Okay,
No,
just
please
hold
answer
on.
Jaren's simple question.
Just follow
please,
him.
Jeran.
You
I'm
can
just-
Jeran,
But
please
this
ask it
might
again,
not be-
Jeran.
I'm not going to believe this unless I can look at it.
Just ask the question again, please.
So if I'm
see what Google Earth is doing, because I can't just
if I'm in California and
it does not look okay.
Let's say I'm in California, I'm at 35 degrees north or something, and I start.
Can you at least give me time to play with this myself?
Absolutely, we're showing you now, and then check it out. We'll have another conversation.
Check it out, because I'm not gonna buy this.
Just soak it in, though.
I'm not asking you to buy it.
Quick, simple question, please, Jeran.
It doesn't look right. It's
gonna be all right,
Google
man.
Earth.
They lied to you about the Earth, brother. It's all.
I'm
good.
just.
It's not that big of a deal.
Do you think if you went east from here that we would come back to where we started?
But you're drawing. That's a straight line across.
Simple question.
I'm not asking. Pay no attention to lines.
East.
Here's
Go
the
straight
lines.
east.
Lines are gone. There you go. There are no lines.
Again, on a curved surface, you got to follow a great circle to go. I mean, it's not the same as a straight line.
Okay, now I'm not talking about a straight line. I'm saying if I
no more lines.
So you're saying if I am going to start in California and end up in California, I have to do a circle.
No, I'm just saying that you have to follow a great. You know what a great circle is?
Yes.
Yeah, circles are on flat Earths too, by the way. But he's trying to make a point to you.
I know, but that's how you draw a line on a spherical object. Is if you want to find the shortest distance, it's along a great circle.
Okay, no more lines though. If you just go east, will you get back to where you started from?
I was just asking
if you just head east.
If we go east, if I go 90 degrees east from California, do I come back to where I started?
I mean, you're using this map, but I mean, yes.
It's not a map, it's the globe.
It's Google Earth, it's the globe, bro.
If you go down a street that's east-west, really long street, you're going to go down that street and come back to your same location. I don't care,
What?
If it's east-west. If you have an east-west street.
I don't understand.
You're trying to tell me that if I go east and come back west, that I'm going to end up in a different location here?
Yes.
No, I'm asking you if you go east.
Not here. Let me tell you why the answer is no. Is because on a flat Earth, which is where you live, by the way, your compass always adjusts to the north. So yes, you would come back to where you started.
Yeah, exactly.
Which is the wandering north, by the way, which the flat Earth doesn't seem to have an answer for.
Oh yeah, we don't have an
We're
answer.
not
So
allowed
therefore,
to
it's
go to the
false. Yeah. So I mean, if you don't know, Austin, if you don't know about the wandering North Pole, then the Earth can't be flat.
It's illegal to fly within 500 miles of each direction of the North, man. We just address Jaren's point, though, bro.
But
just think about
he's
it.
not listening.
If you go east and come back west, you're going to end up in the same spot.
No. Okay, I'm talking about
if you go east. Look,
so I'm saying if I'm in California and I'm going to go.
He's trying to show me, but I'm saying I'm not going to buy it until I can look at it and see. Because it doesn't make any sense what you're showing.
So look.
What am I showing you? I'm showing you the globe. It doesn't make any sense. You're exactly right.
It doesn't make sense.
This is a particular thing I haven't been able to look at and see if there's some.
But I'm asking you your general knowledge. You're a physicist, so I'm asking you. Okay, let's pretend I'm a student. Pretend I'm a student. Pretend I'm a student. Hold on. I'm just a student. I'm a student. I'm trying to learn. I'm not saying anything.
Well, let us show you so you know what to look at later.
If a student asked you, hey, teacher, if I'm in California and I go east, can I walk straight east and stay 90 degrees the whole way and come back to where I started? Is that a straight line or is it a circle? If I'm in California, does this person walk in a circle?
If you're California, do you have to keep turning to the left or do you go straight?
Again, this is spherical geometry, so you can't talk about a straight line exactly on a sphere. It doesn't work.
What
you
about
understand what he's saying?
Okay, but what about the equator?
So
the equator's not a straight line?
Lines. Stop saying lines.
Is the equator a straight line? You said there's no straight line on the globe. What about the equator? If I walk on the equator, isn't that a straight line?
I kind of see what you're getting at, and if I look at it and play with it, I'm sure I'll be able to figure out what's going on.
Okay.
Thank you for that.
It doesn't make any sense. But bro, it's gonna be okay. They lied about the Earth, but bro, it's not that big of a deal. It's really not. Like you start to figure out stuff makes sense. You can trust your senses. You know what I mean? And overall, it's a good thing because all of a sudden you can start to understand where you really live, maybe put together proper physics and stuff like that. It's not a big deal, bro.
Proper physics, and you're trying to tell me proper physics with electric field that I can prove can't be the 9.8 meters per second. I mean, easily prove.
Particle physics and quantum mechanics can't explain magnetism, electrostatics, or electricity. So that you need to acknowledge that. No, you call them virtual photons, which don't exist. I'm just trying to help you out, man.
Like, we can measure the forces
of virtual photons.
No, the forces between charged particles and charged objects. We can.
What about virtual photons?
That's what it's what they use to try to explain the force, but it doesn't take away from the fact that we can empirically use Coulomb's law, which is what.
That's electrostatics. Welcome to flat Earth, my man.
I'm saying exactly. We use Coulomb's law to disprove that things can't fall 9.8 meters per second squared.
Gravity.
It absolutely does. It absolutely.
No, it doesn't.
You can't use electrostatics to explain gravity. That's
I'd be down to talk to you about it. I'm just trying to talk to you about the macro now. We've talked to you about a bunch of stuff. I'm trying to talk to you. I'm trying to level with you, bro. Pun intended.
You guys have no answer for why things fall 9.8.
My dude, it's okay. They lied to you about the Earth, but it's not a big deal, bro. It's not a big deal. Like the government did all kinds of crazy operations, went and looked at Antarctica, came back, said you're not allowed to go there, founded NASA, and then they've been lying to you, bro. And they've been showing you cartoons.
Let's just go through that.
It's all right, bro. I'm just saying, like,
let's do it Antarctica.
Brian, I just one other question though. So why is it when we listen to Feynman and these other guys that they say if something doesn't match experiment, then it's wrong, right? If a theory doesn't match experiment or observation, then it's wrong. You got to throw it away. So why?
I'm telling you, some of the other stuff I can look at, but electrostatics is definitely
okay. So I'm not talking about that anymore. So explain to me though why then when they looked out at the galaxies and saw that gravity wasn't working, then instead of throwing away the theory as they're supposed to do, they added something that we've never observed and said it must be there.
No, that's not how science works. You don't throw away a theory. You find if it doesn't work, you either can refine it, like I told you, general relativity.
So is refining gravity adding dark matter and dark energy?
Again, just because we don't know it, you guys have the same problem. You're whatever magic disc.
We've never added anything.
There's no disc. What disc are you
there's no void,
about, bro?
I'm sorry, whatever you want to call it.
You keep showing this disc in space. You know we don't believe that we're a disc in space, right?
Where are you?
Earth.
Dave, can you pull up the pond?
We're like the
give him a
basement.
freaking vision. That's it.
I've seen the
Because this
pond.
guy thinks we're a disc in space. I wasted 4 hours if he thinks that.
The pond is just a huge.
Come on, man.
What is
it looks like a fluid-like medium. If you want speculation station, it looks like there's a fluid-like medium, super fluid behavior, which will give you perpetual electromagnetic energy without any type of impedance.
Electromagnetic energy.
Photoluminescence would give you the stars. It looks like we are an electromagnetic vortex of the ether. If you wanted the real gravy, bro, I could give you the gravy, bro.
No, he wants what's in the physics book. Austin, what's in the physics book only?
If you drop a magnet in an electric field, it will drop at a different rate than something that's not magnetic.
All right, it works on a flat Earth really well.
Look at Dave's screen.
Meters per second squared. You're going to have different velocities for different materials. That doesn't work with electrostatics. Gravity works just fine.
Brian, look at Dave's screen real quick, and I don't know, just so you get rid of this disc thing.
We live in the Antarctic basin. Antarctica is the highest land on Earth. It's a container of our pond.
It's not the highest place on Earth.
It is the highest land on Earth. What are you talking about, man? Do you just say stuff out loud?
Not that it's the highest point.
Not the highest point, but its land plateau is higher than all the others.
Those are not. You do realize that the Antarctica doesn't have an ice shelf. Those are just ice shelves, by the way. There's ice shelves in Greenland, ice shelves in.
Great, but not the ones that we're showing you that are in Antarctica. Those aren't in Greenland.
Those walls you show. I've seen your pictures of the ice wall. They're just an ice shelf.
That's in Antarctica.
It's the shoreline of our pond. Period. That's it.
If you go all the way around Antarctica, it's not.
It's 60,000 miles.
Yeah, Captain Cook did it.
Yeah,
Brian, why don't you research Captain Cook?
There's places where there's no ice shelf that you can go into Antarctica without an ice shelf.
Have you ever researched Captain Cook, Brian? Do you know what he did?
Well, there's a lot of people.
He navigated around the Earth and went 60,000 miles. Excuse me, hold on. Let me finish one sentence. He went 60,000 miles around the Earth. No way to get in. Can you explain that on your 24,000 mile circumference ball?
And 13,000 mile around Antarctica.
I can tell you many expeditions to Antarctica that I have on my image, but I'm not on the screen right now. But
you need to share your screen.
This is one.
Click share.
Approved guided tours where you can only go where the government tells you to go is really not going to in any way.
One of the ones you're going to show us, Brian, is this woman. She went here, and then she said she went here to the South Pole, and then she went here, and then she went back there, and they call that crossing the South Pole. She just went to here and turned around and went back. And by the way, this is like 1,000 miles or 2,000 miles. This is huge. 3,000 miles. I doubt she actually did it.
Same thing as
she did.
ZQ
it's right
pilot,
here,
right? The guy who has the record for flying around the South Pole circumnavigation.
Look at my image. People go to the South Pole all the time. I mean, you can book it.
But see, you don't understand what you're seeing there. Go back to that image. Go back to that image.
It's one image.
Go back to that image. Go back.
We're trying to help you.
Go back. So this spot that's
look at the lines drawn on the right.
Yeah, you're calling the South Pole. It's right here. This is it. Okay, they've wrapped it around. Now there's no images of the south of Antarctica in the center. Yes, there are bases along here. Okay, but there's no images of the center because they brought it all together, and it's fake.
Okay, but still, how does light wrap around? I mean, we know there's 20.
Dude, I can show you right here. I'm gonna show you a live time demonstration. Okay, you want to know? It's called the coffee cup caustic. Are you ready? Look at this. Look at this. You see how the light is lighting up all the way around it? You see that?
But
You see it?
that's not how our world works.
Oh,
It's a coffee cup cost, buddy.
But
You
that's your
said
experiment.
you said it couldn't happen. I just did it for you.
But that is not. That's literally your experiment.
But he just showed you that
I'm
it
just
could
showing
happen.
it's possible to
nothing.
literally have
I know,
a
but you're
24-hour
taking a little
sunlight.
toy and you're trying to show that this.
That's what a globe is.
Dude, you just said it was impossible. I just showed that you can effortlessly do it with a container. It's called a coffee
it's
cup
impossible on
caustic.
the actual Earth, not using refractive index plastics that can. Again, we don't live in plastic. We live in atmosphere.
Bryant, globes are not for educational purposes. You do agree with that, right?
But everything.
No. Yes or no? Do you agree with that statement? Globes are not for educational purposes. Period.
What do you mean they're not for education?
They're not. No. That statement exactly. They're not for education.
I don't agree. I don't agree with that.
Go to the store, buy a globe, and look at the bottom of it. It says not for educational purposes. It says
They
for
have to.
critical
legally.
purposes.
They have to. It's bullshit.
Well, it's not. There's always. So you guys try to take things like that, like the non-rotating. I mean, that's just an approximation.
Right? Can you admit that when you
NASA said that, bro.
when you said
NASA
that
used
it's
it in their
not
studies as an approximation. They didn't mean that.
They didn't say the word approximate
And
anything.
and
You're
they
making
actually,
up words.
In those same documents, they talk about the spherical Earth and the.
No, they don't.
No, they don't.
You made that up.
You're literally
So, but
making
Brian-
stuff up. Okay.
I'm not making
Brian,
stuff
Brian,
up.
I'll drop
Okay.
you. I'll send you like 50 documents I have, but
I've seen
even
those
ballistic
documents.
missiles, electromagnetic propagation
just
for
say
flat Earth
stuff,
for ground weapon
I've got
systems.
the documents for ballistic.
Dude, they
missiles.
used
Can you share them?
electromagnetic
Can you show? Oh,
weapons.
no,
yeah,
Austin,
let's-
let him show it. Can we see it?
Okay, yeah.
We show his
Electromagnetic
documents that say
propagation, just so
sphere-
you know, but
Yeah.
you would think you would
You see-
enjoy this stuff if you were study electromagnetism.
Yeah.
Yeah,
He has never studied it, obviously.
I have.
They taught it.
No, I can do experiments. That's the nice thing about science. So. let's see.
Yeah. Yeah. All magnetism has
remember-
inertial planes.
Okay, so
Remember
right
the
here,
scientific method too, Brian.
This
Don't
is the
forget the
field
scientific
artillery.
method.
Field Artillery Manual Canyon Gunnery. They talk about the rotation of the Earth. Throughout the whole document, they're talking about the rotation of the Earth.
Yeah, we've seen this alleged Coriolis. What's the spin of the bullet exiting the muzzle?
Well, now you're going to say that's what it is. There's also.
Well, I'm asking you, what is it? Which one's stronger?
Well, if it was the muzzle, then why in the southern hemisphere does it go? Like the whole thing.
So why have we talked to shooters who say they've never used that
the
ever?
English Navy actually, when they attacked Germany in the southern hemisphere.
Oh my God, he's repeating the Neil deGrasse Tyson story that's been debunked 1,000,000 times over.
Oh my God.
I'll show you. I'll give you article after article. That's a
Okay,
Brian, you
joke.
gotta help
That's
us
a
out
whole
here, man.
joke,
We're
dude.
trying
That's
to
not
help
even a
you
real
out, bro.
story. Think about what you're saying, that they're launching cannonballs and missing, and they just kept doing it, and they never thought. That's not how army work. If you shoot a cannonball and you miss a boat, you aim to the right until you hit it.
You account for wind way stronger than any of this nonsense you're talking about.
I know, but you do account for wind, but you also have to account for long range ballistics for the Earth-Bus effect, and well, the Earth-Bus is just another component.
I have long
so
range
funny that you
ballistics
think
saying
that.
the Earth's flat right here. They have to treat the Earth like it's
And
flat.
I've got documents that say that the Coriolis is got to be accounted for, and there's
I
No
told
one
you that-
accounts for it. Nobody accounts for it.
No one counts for it, and
Zero
I told you even
people.
if that was hypothetically
there
real, the
really
sky
are
could be causing
there are a
it.
lot of studies on proving that the spin is Earth spinning.
No, there's not.
Anyone can print a study, right?
I know, but this is like 14 studies. You guys don't have one study.
I literally what?
We've talked to snipers, and then none of them ever account for it.
Oh,
wait, hold on. We got to account for the curvature.
None of
Hold
them.
on,
There's
guys.
one video of one sniper who's probably not even a real sniper.
It's
There's
the same
one,
video
and that's
all
what
the time.
everyone. Yeah, everyone goes on that. But
And
if
he
you
doesn't
talk
even
to
make
real-
sense what he's saying. He
Short
doesn't even make
range,
sense.
yes,
No, long range
No, like
snipers.
2.5
So,
miles.
Bryant, have
Yeah.
you talked to real snipers,
I
Bryant?
will, now I will. Now that you
Okay.
guys got inspired. I
Okay.
promise you I'll find a couple if I ever.
Yeah, go ahead.
Please.
And,
Brian,
and
if
then,
the Earth were
welcome to
truly,
Flat Earth.
if the Earth were
I've
truly
seen
flat and
interviews
stationary,
I've
would you
seen
want to know?
interviews- I've seen interviews on
Dude, Brian,
I
if the
haven't
Earth
met-
were
just
truly
because I haven't
flat and
met him in-
stationary, would you want to know?
I would want to know, but it's like I can easily prove that it's not.
No,
Well, you would
can't.
want to know.
You
if
haven't
it
done
was.
that yet. So
I have. I mean, to me, all these things, the sunset.
Well, watch this video back,
the
my guy.
sunset proves we're a globe.
It just,
Did you not see the sunset kitchen test? That's literally replicated in real life.
The sunset.
Show me a
test,
NASA sunset that's replicated in real life. It's all
the
composite.
sunset
Wait,
kitchen
what about-
test proves that the perspective.
Dude, we have stuff that debunks the globe all the time. The impossible eclipse, the Selenilian eclipse.
Oh, the possible eclipse. Actually, there is an explanation for that.
Oh,
we know you claim that the sun and the moon are just refracted up
Oh,
in the
it is
air, and it's
reflected.
not
Yeah,
really
it is.
there.
That's what's happening. That's what's happening.
Hey,
Can
did
you
anyone
say
notice?
that?
You can do the math on that and see that that's what's
Hey,
happening.
Slightly,
Oh my
I wish
God.
I
Those Selenian eclipses have to be taken
Just
from a higher.
hang on a second. Last night, the moon came up, and I don't know if I don't know in chat if you noticed this. The moon, the sunlight was on the wrong side of the moon. The sun went down over there, the moon was up, and the other side of the moon was lit. Not just like partially. I'm talking the opposite side of the moon yesterday was lit.
Those things are always explainable. I mean, whenever I look into something like that, you can see the explanation. They make
the explanation has nothing to do with Earth.
Yo, Brian, by the way, when you
let's
said
wrap
that you
it
did
up.
the
I mean-
math, Brian, you need to understand what you're doing is basic remedial fallacies. When you said we did the math, you get the globe model, you predict where the sun should be, you do the math on base where it really was, and you say, oh, it must have refracted this much. That's not proving something. That's ad hoc fallacies to dismiss the geometric impossibility of the stellar eclipse, which happens in November again, by the way. Your model gets debunked on a regular basis in the sky.
You can't explain that. I mean, I saw your attempt, but we can easily explain the
polarized lenses show you exactly what could happen during an eclipse. Dun dun dun.
Well, how can you guys explain a lunar eclipse? That's another big
polarized lenses. I just told you.
A polarized lens explains.
Yeah, polarization with an electromagnetic field.
No, you got. The Earth has to be between the sun and the.
Has to be between. Has to be between.
It has to be refracted up where we don't actually see it.
And how do you cast a shadow on something 250,000 miles away? You can't take a basketball, hold it against a wall, have the shadow on it, and then move it away. 10 feet away, there's no shadow anymore. There's no sharp edge. There's nothing. Shadows don't travel like that and make that little curve. And
they only do in the heliocentric model. That's the only time something like that would happen.
This is the actual to scale. You see, a lot of those charts with the eclipses are not to scale. You have to use a multi-scale diagram because
that's a cool graphic.
By the way,
we have real videos of real life.
Brian, I'm putting
the moon above.
Brian,
why is the moon shadow? Oh, that's a solar eclipse. I'm sorry. Never mind.
Brian, I put in the chat for you
the sun and the moon above the earth during the eclipse.
This is
not cartoon memes that beg the question. We have real life videos, Brian.
That was sun and moon. I saw some fake pictures of the sun and the moon on the same side.
The Selenilian eclipse has been well documented for many hundreds of years.
Can be explained, though. That can be explained.
No, he just explained to you why that's not explanation when you take the math and then make it match by saying, oh, well, then it's refracted this much so that it fits the model. That's not proof.
From a higher altitude. You got to take those pictures from a higher altitude.
No, you don't. You can be on the ground level. Taken at the ground. And by the way, if you claim that, Brian, if you claim it's refraction, you have to claim that we never see the actual sun ever. That's what you have to claim.
Selenium eclipse or the impossible eclipse now?
The Selenilian is the impossible eclipse.
So there's versions of the Selenilian that are not the impossible, actually.
The Selenilian eclipse is always impossible. You can't have the sun and moon above the earth. There are just worse versions, more egregious versions where the shadow comes from the wrong side.
There's refraction from a sunset. You know, a sunset, you can see it further than what. It's the same thing that's happened with the impossible eclipse. You can explain all those shadows. But and I know this because a guy brought it up and it stumped me for a little while, but then I finally figured it out. You can explain it.
Go ahead.
Magic, ad hoc magic. That's all it is. You're saying.
I'm still waiting for an explanation
somewhere else.
Brian, and I put in the chat for you it's from Stack Exchange. I'm talking about the fact that it's a completely made up story about the Royal Navy and the Coriolis effect and all that. It's garbage.
Okay, well, whatever. Maybe that I don't know about. I'll look into that.
Okay.
Fact check.
Thank you.
I have seen that.
You got a lot of stuff to look into, bro.
Not just. Well, so do you guys. Electromagnetism.
No,
can't
we
explain
don't.
Gravity.
I've looked into everything you brought up, bro,
you
for
really
many
think
years.
the electric field can explain 9.8 meters per second? Because that is so easy to debunk.
Yeah, everything's intrinsically electrostatic. It isn't a field pulling it down. It just sets the up and down, and then density separates the rest for the 50th time.
Density is just a relative that doesn't have a vector to it.
Yeah. No, but the vector comes by the electrostatics.
Electromagnetism works in all directions. It doesn't work. I'm sorry. It doesn't go. Like I said, you can.
Do we have an electric gradient on the Earth? Yes or no?
The electric gradient, like I said, it increases a lot.
Non sequitur.
But you said it comes in every direction.
It's not a non sequitur because
it doesn't matter the strength. It doesn't matter what the strength is. It's that it sets it up and down.
It varies wildly, and gravity doesn't
matter. Doesn't matter. It's always more. It's always more. It's always more positive above the Earth everywhere on the Earth.
Even if it varies wildly across the planet, it can still account for a stable 9.8.
Wait, no, but 9.8 meters per second varies greatly across.
Brian, let me ask you a question. I know you said Brian. You said that the electrostatic force isn't equal all over the Earth, and you're ignoring the fact that the number of times stronger than gravity is an unfathomable number. So wait, hold on a second. Let's pretend gravity. Hold on. Let me finish. let's pretend gravity is real. We know the electrostatic force is real. So why do things fall at 9.8 meters per second when the electrostatic field is also pulling, also doing it?
100 volts per meter where it is very, it's a very weak electric field.
Doesn't matter.
It's stronger than gravity.
He's missing the whole point, though.
But if the point is, your gravity falls apart because you got your gravity and the proven electrostatic field, the myth of gravity, and the proof. But why do things go down at the speed that you say?
Can I just talk? I don't want to talk to Austin anymore for a minute.
Yeah, I don't want to talk.
I'm just intellectually eviscerating.
I wouldn't want to either.
I'm going to mute.
You're not listening to me. I just want to talk to Dave because.
All right, go ahead.
Talk to Dave.
No, you haven't proven.
I'll go on mute, bro.
The electrostatic field, Dave. Can you agree that it varies wildly across the planet with lightning strikes and the electrical activity?
But that you're not understanding. Austin tried to explain it to you a whole bunch of times. It just determines the up and down. Frequency and density. So, okay. I can agree that we completely disagree on this. I agree that you don't understand.
You had absolutely nothing with any substance, so
nothing. We have nothing.
That's it. You know what?
You know who has all the substance though is physics. Physics books.
I know, but
they got all the substance.
The electric field is so.
Bob the science guy, McToon.
But hey, I gotta say this. It's really funny that you have such a high standard for what I'm explaining, which is objective, and you've yet to understand. But you don't apply the same standard to the theory of relativity, which has been debunked. So it's just a hypocritical standard because you have a cognitive dissonance bias towards the globe Earth. That's objectively what we're all observing.
You understand laws and theories make accurate predictions. If they're proven to think
so what is okay? So hold on. If it makes
it doesn't take away from that. It makes accurate.
All right. So space time is predicted, right? Space time is predicted. So tell me, what is being bent in space time? Because I thought space was the absence of everything, but you are saying it's bent.
This is a model. It's a math. You understand that?
Wait. So it's not reality.
So it's not real.
All theories are models that actually will give you accurate predictions about the reality.
But it doesn't. It doesn't give us accurate predictions.
It says.
Are you kidding me?
It's off by 95% on the cosmological scale, and it's off on the quantum scale.
Well, that's a different thing. I'm talking.
No, it's not a different thing. It's the same thing. It's literally the same thing.
You're talking about astrophysics now. I'm talking about general relativity has never really been falsified.
It literally has, though.
Well, show me what's
okay. Dark matter, dark energy, expansion rate, the lack of
general relativity.
What? Because you added something to make your model work, and then
relativity made a prediction. It was
wrong. But your model doesn't even come close to explaining.
Gee, we've been we're a bunch of guys in our house. We're a bunch of guys in our houses.
Why things fall 9.8 meters per second?
Here we go.
It's not our job to prove our model. You have to prove your positive claim of the globe. And so far, there's been zero proof.
I'm saying that Newton's gravity makes accurate predictions that we can use to actually build things.
Okay.
The whole world around you is based on.
Yeah, it's decent. Listen, it's accurate on the local scale because it's downward acceleration, which is an agreed upon average. That is
the electric field. Absolutely
cannot be.
You're afraid to hear me lay out.
Cannot be,
man.
Listen, you can have a magnet and a diamagnetic object, right? The magnet's going to get bent by an electric field and it's going to slow down.
Non sequitur.
It's not a non sequitur. You can't. We know that things fall at the same. I mean, come on. Electric fields don't work.
If I drop a magnet over top of an area, the ground that has more metal composition, does it drop faster or slower? Or exactly 9.8?
If there's no air resistance, it's all going to drop at 9.8.
That's incorrect. If I drop a magnet over top of
magnet. Oh, I'm sorry. Yeah. If you,
okay. So stop talking about magnets.
No, listen. That's when you draw a free body diagram. You have two forces you got to account now: the electric force, the magnetic force, and the force of gravity. There's more than just one force in some.
Gravity's a pseudoscientific fairy tale that needs to explain the convexity of the ocean bending around the ball.
Debate Austin. Is that why you brought him on, Dave? So you got some ace of the whole flat earther.
It doesn't matter. He's actually better at explaining these things than me. So
I'll disengage. I don't want you to get triggered, man. I'm just trying to help you.
Listen. We've been going round and round on this.
I could easily explain to you that the electric field can't work, but you won't listen to that.
No, you can't because it just sets the bias. If you'll give me 15 seconds, I don't
want to talk to you anymore.
15 seconds.
You're not listening though.
I'm not.
Trust me. 15
seconds. Can we change to like the stars or something?
Or
slitting my wrists?
15 seconds, just so you
15
understand.
15 seconds.
I'll stop after 15 seconds, Brian. You gotta trust me.
I'll mute him after 15 seconds.
I'll mute myself. All right, listen. So yeah, the electrical field changes drastically across the Earth. It's not exactly the same, but the fact it always increases at all creates the up and down, which is all that's
with
needed.
altitude.
It's over. It's all right. I'm done. I'm done.
It
If
does.
you
It
heard it, you
provably
didn't hear
does.
it. I don't say.
No, look it up.
What
the
does?
electric field
Didn't hear it.
increases with altitude. It does. I'm telling you, you just look. It does.
All right, bro. All right, bro.
All right.
Agree to
Other-
disagree.
It's a
Agree to
fact.
disagree.
I mean,
Agree to disagree, Brian.
it's not
Brian.
about you can measure it and decrease.
Let's bring it back
Listen.
home. Let's say our goodbyes. Let's be nice to each other and let's go our separate ways.
Listen, I want to point out one thing. No
boy.
insults were thrown, some joking around, some heated conversation. This is how globe believers and flat earth believers should have a conversation. I think Bryant, was willing to come on with all four of us. And no, Austin, well, yeah, he is my ace in the hole. He explains that stuff better than I do. That's why I had him on, because I want to give you the best answers, right? I had Sean, I had Jeran, myself. Together, I think we gave you the best arguments, because by myself, probably wouldn't have done as good of a job. So I just want to thank you for being a reasonable, reasonable, a polite guest.
Yeah. Okay.
All right. So hats off to you for that. We violently disagree on this stuff, and there was a whole bunch of I got to look into that. I hope you do look into that.
I'll look at it so I can see what's going on. I just couldn't follow what's going on.
And we didn't talk about NASA because I don't know, that one would be pretty scary. I mean, the litmus test, normally we don't really talk to people that can't look at this thing and go, this is not a spaceship.
I don't want to I don't want to talk about the moon landing.
Yes, of course you don't.
Well, no, it's just because
no duct tape, Dave.
No, listen, I know you guys have so many answers. I got to look into everything.
You know what? You're right. If you haven't looked into it, unfair. So I have one question for you. One question for you. Knowing about pressure and water and everything,
it all works.
Could I put you in this and submerge you in a lake? Would you let me do that? Would you go into this thing and let me submerge you underwater? Because it is airtight, right? It has to be airtight. I mean, look at that. That tinfoil and those curtain rods.
You can do it to me,
that
Dave.
paper
I'll do
mache.
it. I'll go ahead and do it. Go ahead and put me in the
I won't do it to you, Jeran.
Right. I'll be fine.
Come on. So but here's the thing. Just this alone debunks NASA, which debunks all space.
A picture doesn't debunk anything, Dave. I'm sorry.
The lunar module debunks
the lunar module.
It debunks. It makes so the Earth is flat. I mean, because of the
they had to fake
but
the moon landing.
They certainly
to
wanted to get that view.
All right, listen. He doesn't listen. We've gone 3.5 hours, 4 hours. We've gone 4 hours. He doesn't want to talk about the moon landing. I don't blame him.
I haven't spent a lot of time with it, but I've spent enough time to see some good evidence. But I'm not going to pretend. You guys have every single talking point. I know this is what the top flat earthers do. They know how to respond to everything.
Because we looked into everything. I mean,
we've been studying it. We've been looking into it for years.
Electrostatics cannot work to describe why things.
Again, you don't understand. Again, you don't understand it. By saying that, you don't understand it.
No, I do understand it. I just wrote a book that was based on me spending a year restudying electricity and magnetism. I understand it very well.
If you spent 10 years on it, it doesn't mean it's right.
Electric. It can't.
All right, bro.
Again, if things fell 9.8 meters per second and dropped out by 1/r, the electric field of the Earth literally comes near zero at a certain altitude, but gravity doesn't stop there.
Brian, show me the curvature, please.
I showed you plenty of curvature.
No, you haven't.
Where? What?
Show me.
Is that what I left?
Show me the pond.
The pond.
Go look outside.
Go outside, brother.
No,
go outside.
No.
Go on an airplane and look
no,
around.
Listen, you're demanding whole Earth images. I'm demanding a whole pond image.
Excuse me. I don't make $330 billion a year to go prove these things to you. They do, and they've never proved it. Because if they proved it, Bryant, we wouldn't be having this conversation.
I know, but all those high altitude balloons, I've been able to see easily that they're
Brian, but you can't see that far. You can't see forever.
He also doesn't make whole Earth claims, right?
I thought it was 3 miles we could see. So how far are you talking here?
Right.
You said earlier 3 miles is the farthest.
It depends on your eye.
There's only one side making whole Earth claims, Brian. Right? The government claims exactly what the Earth is, exactly what it looks like. They claim they go to space. They're making the whole Earth.
Remember
whole Earth pictures. That's
remember
right.
Jeran said, "Put yourself in a room, make it 10 miles wide with a 10-foot high ceiling." Could you take a picture of that whole room? No, you couldn't, because a half a mile away, the ceiling would touch the floor. Okay, so you can only take pictures of parts of it.
The perspective equation says otherwise. Actually, it doesn't ever.
What? I was at the Bellagio in Vegas, and the lights
but
were
Dave,
touching
the equations
floor
don't
at the
say
other
that.
end of the.
No, the equations
lights
don't say
were
that.
touching the floor at the other end of the hallway.
Not according to my math, they weren't.
It's not about that. You're just.
It's perspective.
You're taking one example.
Those damn flat earthers love perspective.
It's what everybody sees every day, every bit
that
of.
doesn't prove anything. That's inside of one place, and you're saying that proves
That's where we live. Yeah.
All right. Here's my final statement. It's okay to have your entire life destroyed with new information, because then you have a whole new life. All right.
Again, your whole foundation is based on the electric theory of gravity. Is absolutely
that's our whole
wrong.
thing. Yeah.
That's our whole thing. You know what?
One of the things, bro.
But without
Man, that proves curvature. Good job.
But your entire world is set that an atom at the very center of the earth says, I'm the center. Everyone come to me. But the atom that's halfway between the center and halfway between the center and the surface, he goes, no, I am the center. Everybody come to me. And then they fight it out, and the guy at the middle always wins.
No, Dave, that's how equilibrium is established.
That's how how does gas turn into a gravitational ball and leave a void in between? Okay, how does that happen?
It's an energy density. It's not
energy density. Damn it! I should have known that,
man.
Well, it is.
I should have looked into that.
That's how relativity explains.
So nothing exploded, became everything. All the rocks stuck together, and all the gases turned into giant balls, and they left a void in between. And somehow they hold on to each other, and they ignore the 3-body problem. They go into the 100 billion body not problem, and they repeat every year. Everything repeats. The eclipses repeat every 18 years.
I understand chaos theory, by the way. The 3-body problem. Do you know what the prediction, the predictability horizon is within the 3-body problem? Within
my question is, how do all of these planets and stars and everything maintain perfect order like a clock?
Okay, let me counter that with the same question for you. Where in the world is the pond? What's around it? What's beneath it?
We're not allowed to go there.
I don't know.
Brian.
We're not allowed to go there.
But you got, and that's just, it's all.
What's at the end of your universe that's expanding faster than the speed of light?
Listen, we had a conversation before. You kind of know my views as a more spiritual view of everything. But this physical universe, we don't have. So there's a lot of.
Let me ask you a question. What makes more sense? What makes more sense? That we're on a non-moving level plane, like every observation tells us, and that we're not allowed to explore the outer land, so we don't know, or we live in this heliocentric space void that's expanding faster than the speed of light into nothingness. Okay.
But the Hubble model is not perfect. I agree. There's a lot of things not known.
But perfect.
But you guys don't have anything. But you guys don't have anything.
Yeah, we were lied to as children.
Dude, you're like bragging about the fact that the world's countries got together and said we can't go past the 60th south latitude. You're like, you guys don't even know what's past. Yeah, the world's governments are working together, Brian. You didn't know that?
The Antarctic Treaty. I've read it actually, and it doesn't.
Brian,
we can go there.
There's two things that all of the major governments in the world agree upon. Can't go to Antarctica because we have to protect the ice and the penguins, and everyone needs to get a shot in the arm.
Wait, what about wearing a mask?
They agree on those two things. They agree on the boogeyman thing, and they agree on Antarctica. That tells you something. That should tell you something.
I know, but the Antarctica, people go there all the time.
No, but they go there. There's 100 companies, all run by the same guy. There are a whole bunch of shell companies. It's out of most people's price range, and you barely get off the ship.
Yeah,
and if they did, even if they let you go, how far are you going to go? You're going to walk 100 miles and come back? You're still on the ice shelf.
But the Antarctic Treaty doesn't prohibit people from going there. It prohibits dumping,
No, we have to turn in a report. We'd have to turn in a report.
Exploration is forbidden. You have to be approved. You have to go.
Absolutely is.
Brian, book something to go explore Antarctica. Tell me how the process works. Once you get denied, we can have that conversation, because you don't know what you're talking about. You've never tried to go to Antarctica and explore, Brian. You've never tried to do that.
Yeah, they go on a cruise ship. They spend $30,000 to go to the edge.
Have you been there to explore?
We can't go there.
My wife's grandparents were for 30 grand.
I understand, but
we have friends that have gone.
Why don't you try to book one of those Antarctic tours?
Brian, I'll tell you what. We've done all the work for you. One of our flat earther guys, who's a lawyer, put all of the information together in a 30-minute video. It's in the app under the Antarctica button on the FAQ page. Hit it. It's called Antarctica's Closed. Watch that. He did all the work for you. It would take you 6 months to get this amount of research. He did it in 30 minutes for you. Watch that, and then go double check it. Go
and then
verify it.
I found out
because
that
there's papers on all of it.
all the cruise ships are all owned by the same person.
The other thing that's a problem is that with these high altitude.
Did you hear what Jeran said?
Let Jeran say something again. What was that?
I just said all the cruise ships, or most of the cruise ships that go down to Antarctica, are all owned by the same guy, and he's the guy that Obama put in charge of NOAA back whatever that was 10-20 years ago.
I'd like to fact check that.
Okay.
I'll look at.
Please do.
You got a lot to fact check. You might want to come back and watch this video again and then remember all the stuff that you want to fact check. We're not lying to you.
Spinras. Nina
I know,
Spinras, I think is her
the
name.
electric. You just go back to the drawing board with the electric, because that doesn't work. I mean,
you're obsessed with that, man. It's because
I'm obsessed with it because
it's the only thing that you have, because you can argue it all day long.
We've explained everything else.
He didn't argue it actually. He got
gravity just annihilates the flat Earth. That's the problem. Why you guys have
gravity?
Gravity. There is no ball without gravity. It's a hypocritical statement.
That's the only proof for gravity is that it has to exist if the Earth's a ball.
That's why
it's something that we can actually know. That I explained to you the difference between a law and a theory. Laws are things we can use to actually get calculations, make predictions, then we can get things that we can then make. Then we can use that to make things in this world.
Great.
If there was an applied science of flat Earth, nothing would be getting made. There'd be no innovation.
Oh boy.
What do you guys?
So we would have never figured out that things fell 9.8 meters per second squared if the Earth was flat. We wouldn't have figured it out.
It was predicted before Newton.
You're just rebranding. I know, but you're just rebranding gravity.
Into a true model, not the fake one that's telling everybody we're spinning and flying through space.
Newton didn't even offer a mechanism for gravity. He said, "Do not ever attribute that to me, because any man with competent faculty of thinking in philosophical matters could never fall into the absurdity of thinking that it could be something."
Hey, what if when that apple fell, some kid let go of a helium balloon? What would have Newton come up with?
The helium balloon is actually just gravity pulling the atmosphere down hard. Well, Dave,
I mean, what would he come up with gravity?
Brian, what would happen if Newton saw the apple land in water and it just floated there?
And the helium balloon went up.
Mess everything up for him.
The same thing would have happened, actually. But
another fake story, guys. Another fake story never happened.
1666 with 666 Newtons. Oh my God, bro! You think that's a coincidence?
But you guys have all these great little stories. It's pretty nice. It's like a religion almost.
Listen.
They're cute. They're cute stories.
They're cute.
If you get a helium balloon and then you're in a car and you slam on the brakes, which direction does the helium balloon go?
It goes to the. We've seen this before. We saw the guy from Smarter Every Day do it, but it made sense why I did, because the air gets pushed forward, so it goes back. Wait, I'm trying to.
Well, the air. It's all about, again, because the atmosphere. The reason the helium balloon rises up is because the atmosphere is pulling down the denser air below and it pushes it up.
Oh, you mean it has an electric gradient?
Gravity.
Wait.
Yeah, the electric gradient.
But where is it pulling?
Welcome to flat Earth, Brian.
We can measure the electric field, guys, at higher altitudes. And
wait, hold on. If I'm holding I'm holding a helium balloon.
Absolutely.
Hold on, Brian. I'm holding a helium balloon. I'm holding a helium balloon in a string.
Doesn't matter a lot.
And I let it go. What are you saying, that the Earth is pulling the gravity, the air from where?
No, yes. So the air is more dense than helium, right? You know.
Thank you.
Right?
Yes.
Okay, so the air that's displaced so the amount of air that was in where the helium balloon is. So you got a helium balloon right here. Right?
Yes. Density.
So that air inside that's getting displaced is denser than the helium. So that's Archimedes' idea. So
what happened to gravity?
Well, gravity's pulling the atmosphere down. That's what creates the pressure.
But pulling what atmosphere down? The balloon's there.
The atmosphere we live in. It's the gravitational force.
No, I'm talking about the balloon. Why is the balloon not going down? Why are the clouds not going down? These are questions that you can't answer.
The balloon will go up to where it gets to its same density as the air, and it will stop.
No. You think that the clouds with the down
balloon doesn't keep going up,
with
guys.
trillions of tons of water?
It pops.
Yeah, are they lighter than balloons?
It doesn't stop. It pops.
Wait,
you ever been clouds? Like, have you ever been in a downpour, like a heavy deluge downpour? Where's all that water? Why is it floating up there?
Clouds
Can you explain it?
Okay, clouds are mysterious. I'm not going to try to explain something.
They're not mysterious. We know what they're doing.
We know what they're doing.
But you don't have any. Your answer is electrostatics.
That's the actual answer. Why don't you look it up?
It doesn't work, guys.
All right. We're on the same thing.
All right, guys.
Brian, just say you have a final statement.
You even agreed to me that it varies wildly, and somehow it still
doesn't matter. Just
funny. I'm looking up electrostatics, and it says right here, the presence of surface charge imbalance means that objects will exhibit attractive and repulsive forces. It says right there.
During a lightning storm, the electric field switches polarity. You know that, right?
Why are you getting? It doesn't matter. It sets you up and
Yes,
down.
it does. You just said it sets up and down.
He doesn't understand what that means, Austin. That's all.
I guess not, dude.
He doesn't understand what I'm saying.
You said the clouds weren't held together by electrostatics, man. I think it might be time to call it a night, bro. It might be time to call it a night, bro.
During an electrical storm, the polarity reverses and it increases by like 10,000 fold. So you're saying that electrostatics defines the direction of gravity. How can it reverse
gravity
like
doesn't
that?
exist. What do you?
Gravity it's always down. Well,
gravity is incoherent dielectric acceleration. I'll send you some stuff. All right, I'll send you some stuff, and you can read it or you cannot read it. I don't know.
Answer this one thing.
Answer this.
How, if the electrostatic field is given the direction to why things fall, how is it that during a thunderstorm the electric field switches from positive to negative and increases? Why don't things start floating up during an electrical storm?
You just get dielectric like pulses, dielectric discharges towards technically counter space, and you think the entire electric gradient on the Earth flips over? Is that what you think?
It provably does during a lightning storm.
The whole entire Earth's electric gradient flips upside down. That's what you think?
From the clouds to the ground.
It's a lightning bolt for a split second.
Yeah,
that's it.
The dielectric discharge.
It doesn't matter. There's no variations like that with gravity, or 9.8 meters per second. 9.8 meters per second stays the
That's
same.
an average. It doesn't stay the same. How do you keep saying that?
He doesn't understand it.
And wait, have you ever gotten a scale and then stood exactly where lightning striked and to see if the weight on the scale changed? Have you ever done that? I don't think anyone's ever done that.
Well,
okay.
I don't think that's going to show much.
You can make things flow with electrostatics, bro. Come on.
Yes.
But again, electrostatic field of the Earth stops.
We're back.
I know, but
this is go on forever, bro.
It's 1:15 in the morning.
I gotta get out of. Yeah, I mean,
we gotta wrap it up.
We'll talk to him
it's
about
so
it
obvious,
for 5
you're
hours.
denying the obvious. I mean, you're saying
Listen,
like
This actually hurts worse than my broken tooth.
Brian,
Brian, we all love you, by the way. We all love
We do
you.
love you.
Very nice.
We feel
man.
bad for you.
Listen, go back, listen to this. All the things that you said you're going to look into it. If you need us to send you any documents, we'll send you some. What's it? I'll give him your email. He'll send you some stuff.
I want to see how electrostatics can give a uniform at the surface of the Earth, a uniform 9.8 meters per second, when we know it varies wildly and it reverses polarity.
All right,
which means you got to explain.
He'll get it over to you.
We'll
get it over to you.
I got you.
And then
go sub to my channel too.
Welcome to Flat Earth.
But good luck trying. Yeah.
We'll get it over to you. No worries.
I'll send you some stuff.
Thank you. And
all right, well.
All right, let's say our goodbye. All right. So it's nice. Thank you for coming in. And I know it did.
What I was worried about.
I know 4-on-1 was not kind. Or
wait a minute. Hold on a second. I think we were very good to you.
Yeah, we were. We didn't call you names.
It's not that you were not bad. It's not that you were. I just didn't want to talk to Austin most. I wanted to talk to
Nobody wants to talk to Austin when it comes to this stuff.
But he's not listening. He's got his strong idea of electric.
But you don't. You really don't have any strong ideas that are
I do,
overwhelming.
but I can prove easily that the electric field varies wildly. It's so simple to prove this.
Okay, but he didn't say that doesn't have anything to do
with
with
But we're not saying that matters.
When it switches polarity, it does. You're saying that
for a split second with the dielectric discharge for the millionth time.
Again, but that means gravity would have to have an impulse that you could measure, and it doesn't. For the 9.8
gravity has nothing.
You're missing the
whole
point.
electric gradient doesn't flip on the whole Earth.
No. Actually, during an electric storm, that potential reverses for quite some time. But the lightning is a split second. You're right.
It doesn't flip across the whole Earth.
And people
He said you're right. Just move on from there. Let's just.
All right, whatever.
You said you're right.
It doesn't work, guys. Absolutely doesn't work.
All right, man.
You did this curvature, but
he said
agree to disagree.
We can talk. I'm just saying that's one thing that's just very easy to debunk.
I know. The spinning of the Earth doesn't work. Neither does the lack of curvature. It just doesn't
it works.
exist.
It works.
Brian, you did say there were some things that you should look into. Please do.
I will send you got my email. So.
All right, man.
And
thanks for coming.
Just send me the most convincing ones.
Okay, wait. I sent you in the chat. Do you see in the chat before you go away? There's a couple things I put in there.
Hit the chat button.
You wanted to know where the cosmologist faked the LIGO. That's the second link there.
He doesn't want to say that.
And then
well,
he just said it didn't happen. He didn't
so
believe
go
it,
in the chat before you exit.
But we already know what these guys will do. He'll come back and he'll be like, "Oh no, but they faked it on purpose." Like, yeah, that's what we're saying. But they did it to test their systems.
Okay, you're saying that, but let me look at it. Okay, I'll look at it.
Okay, and then the one below that is the British Navy never existed. It's
okay.
a dumb thought.
I'll concede that one, but it doesn't mean that Coriolis.
Just get his email, Austin.
All right, I got it for you.
Yeah.
Let me check super chats real quick. I just want to say thank you to those people who did that.
Brian, take a nice breath. You did a great job.
1,073 people listening. We got to keep going. People like the good professor. My best show ever.
We went 4 hours and 15 minutes, so we're good.
Time flies when you're
when you're having fun. Time flies.
Yeah, we're all having fun. Come on, man.
Time dilates and then slows down.
It's just don't, Austin. No more talking.
We should get McToon here. See what he thinks, though.
Yeah, that would be fun.
Bob the science guy. We got to get him on. He'll tell.
Yeah, not gonna happen.
Well, yeah. At least listen. At least next time, if we do this ever again, at least get one other. Let me have at least one other person.
Get as many as you want.
Absolutely, bring them on.
Fine.
Bring them on.
That doesn't
the more,
bother
the merrier.
us at all. We weren't trying to bother you.
We want to have,
but it doesn't bother us
because
a fully rounded conversation. So if you got somebody that can explain it better, bring them.
Sure.
Bring all the credentials you can find, ideally.
Yep. Yeah.
Bring some college professors, whatever you like.
Yep.
But listen, for Globers out there and flat earthers, this is how you have a conversation. We had fun. We got a little heated. And that's it. We didn't call each other names.
That part was
let's hope that nobody in the super chats did, because
you know what, I was watching the chat. People were pretty good. A few people got frustrated out there, but
Brian, I swore once, and I'm just apologizing for it, Brian. I did swear once, so I'm sorry about that.
I said I was going to cut my wrists in the chat, so I apologize for that.
We did.
I really wasn't going to do that, but I did say that.
Oh, that's great.
I'm sorry if you got mad at me, bro. It's all
it's impossible. Electrostatics impossible.
I spent several days actually deconstructing the whole electromagnetism, and I'm telling you, it doesn't work.
Hates Austin.
It's not that I hate Austin. It's just that you can't describe why things fall.
You hate his beard?
With 9.8 seconds squared.
Right. So when you can't explain something, then you look into it. You don't just dismiss it. Oh, I can't explain it. It's gone. I mean, imagine if everybody did that.
If it's the electric field, we have all kinds of. You can measure
Austin, you're banned next time.
Yeah.
It's not
dude, I said we'll talk about it later, brother.
Austin, banned.
It doesn't work.
All right, let me read these.
Brian, we love you, man. We thank you for doing this.
Thanks for coming, and we'll continue the conversation.
You can leave if you want. I'm just going to read the super chats.
All right, I'm going to let you go.
Maybe we could do it again in the future, Brian. Why don't you look at a couple of these doors we showed you and see if you could walk through them?
But it's impossible.
I'm not going to do it on this type of form again, though.
Okay, we're sorry.
Sure, no worries. Understandable.
Hey, I'll let you come on my show and we can talk about electricity.
He'll be on tomorrow.
Yeah.
Dave, would you go on a show with Professor Dave, Simon Dan?
What?
No, I don't talk to
look at the way those guys. Come on, hold on. You can't
Come
compare us to them.
No,
that's rude. Yeah, that's kind of rude.
That's rude. We didn't call you names.
No, I didn't.
Brian, you got to watch the fallacy breakdown of Professor Dave and I. Did you watch that video yet? I'm gonna send it to you.
275 to 5.
If they acted with manners, if somehow they act with manners,
that'll never
he
happen.
got 275 fallacies to my 15 telling him.
Brian, here's the difference. The difference between us is we can have a conversation and we actually attack your real arguments. We don't make straw men. Those guys just attack our character. They call us names and they build straw men. And
I don't like that either.
Okay, well, that's what they do. So don't compare us to them.
That's why
we don't like that either. We
have
haven't
that
done
conversation.
That's why we like you.
I was turned off by Professor Dave the way he.
Well, he's not a professor either. So
listen, he's not a real professor.
Does that bother you? Does that bother you?
He did teach chemistry actually for one at a college.
While we're at it, we'll just point out Professor Dave is clearly scared to debate me and only wants to debate me on an unfair platform. Just want to throw that out there
so that he can berate you.
Yeah, I mean.
All right, you can. Upside Down Guy says you can confine and raise a kid to believe anything. If confined enough, you can show and tell them dragons are real, and they will come and eat them, and they all misbehave. Sorry, I don't know what that is.
Yeah.
Sacred Knowledge says belief is something you do when you lack info necessary to know. We don't believe. We know it can't be a ball because we measured it. Globers believe. Okay, thank you. Awareverse, thank you very much for the $2. Eric H says Bryant is just gonna tie his own self into a knot. This is great. THC says smoke some more indoctrination, Bryant. Come on, be nice, guys.
Come on.
Hey, I'm not. Hey, Dave. He didn't hear a conversation before the call. So.
Yeah, he's got a little bit. He's kind of on our side and on everything, but of course,
on everything but these two topics, which is
I'm wide awake when it comes to that.
Well, you think photons are real, though, so I don't agree with you on that.
Again, whatever you want to call them, we can use them to model what happens in reality.
Okay.
You guys are hung up on names. We can. I mean.
The difference between
quantum mechanics is based on all the computers that we're using right now are based on photons, whether you want to call them photons or not. I mean,
all right,
Brian, you're don't compare yourself to those guys that you just mentioned because you actually believe what you're saying, and that's fine. Yeah. Those guys don't believe what they're saying. They know that they're scamming, and they do what all psychopaths do. They just call other people exactly what they are, right? it's amazing.
So
I'm
thank you.
Totally turned out. Yeah, I'm totally.
406 findings and Reggie P56 and Paraplegic Bear and Homie the Handyman. Thank you guys for these super chats. All right, it's good. Now we can go.
All right. That's all, everybody. Thanks for coming.
Guys, do your own research. When you do, you'll never again believe like Bryant does. Till next time, jeranism. Peace.
All right, Brian. Thanks. See ya.
All right, peace out.
Bye-bye.
It is the world that has been pulled over your eyes to blind you from the truth.
Just don't understand, how do you not believe in any conspiracy theories? I understand not all of them, not most of them, but you don't believe in any conspiracy theory? You just think the government's just batting 1,000 and telling us the whole truth?
In a cave sits a group of prisoners, detained with their faces turned towards the inner wall. From the entrance of the cave, the sun is shining and casting shadows on the wall in front of the prisoners. These shadows are the only things the prisoners have ever seen and will, for them, represent reality. The shadow world is all that exists for the prisoners, and they talk to each other about the things they see. If any of the prisoners could free himself and escape out into the real world, he would immediately be dazzled by the sun, which he had never seen before. When his eyes got accustomed to the light, he would see that what he believed to be reality was merely shadows or copies of something more real. We are all these prisoners, Plato said, trapped in our material world. What we think of as reality is actually only shadows thereof.
It starts with so unreal.
It is the world that has been pulled over your eyes to blind you from the truth.